Chapter 11, Part 1 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook by the FAA. Transition to complex airplanes. High performance and complex airplanes. Transition to a complex airplane or a high-performance airplane can be demanding for most pilots without previous experience. Increased performance and increased complexity both require additional planning, judgment, and piloting skills. Transition to these types of airplanes, therefore, should be accomplished in a systematic manner through a structured course of training administered by a qualified flight instructor. A complex airplane is defined as an airplane equipped with a retractable landing gear, wing flaps, and a controllable pitch propeller. For a seaplane to be considered complex, it is required to have wing flaps and a controllable pitch propeller. A high-performance airplane is defined as an airplane with an engine of more than 200 horsepower. Wing flaps. Airplanes can be designed to fly fast or slow. High speed requires thin, moderately cambered airfoils with a small wing area, whereas the high lift needed for low speeds is obtained with thicker, highly cambered airfoils with a larger wing area. See Figure 11-1. Many attempts have been made to compromise this conflicting requirement of high cruise and slow landing speeds. Since an airfoil cannot have two different cambers at the same time, one of two things must be done. Either the airfoil can be a compromise, or a cruise airfoil can be combined with a device for increasing the camber of the airfoil for low-speed flight. One method for varying an airfoil's camber is the addition of trailing edge flaps. Engineers call these devices a high-lift system. Function of flaps. Flaps work primarily by changing the camber of the airfoil since deflection adds aft camber. Flap deflection does not increase the critical, stall, angle of attack, and in some cases flap deflection actually decreases the critical angle of attack. Deflection of trailing edge control surfaces, such as the aileron, alters both lift and drag. With aileron deflection, there is asymmetrical lift, rolling moment, and drag, adverse yaw. Wing flaps differ in that deflection acts symmetrically on the airplane. There is no roll or yaw effect, and pitch changes depend on the airplane design. Pitch behavior depends on flap type, wing position, and horizontal tail location. The increased camber from flap deflection produces lift primarily on the rear portion of the wing. This produces a nose-down pitching moment. However, the change in tail load from the downwash deflected by the flaps over the horizontal tail has a significant influence on the pitching moment. Consequently, pitch behavior depends on the design features of the particular airplane. Flap deflection of up to 15 degrees primarily produces lift with minimal drag. The tendency to balloon up with initial flap deflection is because of lift increase, but the nose-down pitching moment tends to offset the balloon. Deflection beyond 15% produces a large increase in drag. Drag from flap deflection is parasite drag, and as such is proportional to the square of the speed. Also, deflection beyond 15 degrees produces a significant nose-up pitching moment in most high-wing airplanes because the resulting downwash increases the airflow over the horizontal tail. Flap effectiveness. Flap effectiveness depends on a number of factors, but the most noticeable are size and type. For the purpose of this chapter, trailing edge flaps are classified as 4 basic types: plain, hinge, split, slotted, and Fowler. See Figure 11-2. The plain or hinge flap is a hinged section of the wing. The structure and function are comparable to the other control surfaces: ailerons, rudder, and elevator. The split flap is more complex. it is the lower or underside portion of the wing. Deflection of the flap leaves the trailing edge of the wing undisturbed. It is, however, more effective than the hinge flap because of the greater lift and less pitching moment, but there is more drag. Split flaps are more useful for landing, but the partially deflected hinge flaps have the advantage in takeoff. The split flap has significant drag at small deflections, whereas the hinge flap does not because airflow remains attached to the flap. The slotted flap has a gap between the wing and the leading edge of the flap. The slot allows high-pressure airflow on the wing undersurface to energize the lower pressure over the top, thereby delaying flow separation. The slotted flap has greater lift than the hinge flap, but less than the split flap, but because of a higher lift-drag ratio, it gives better takeoff and climb performance. Small deflections of the slotted flap give a higher drag than the hinge flap, but less than the split. This allows the slotted flap to be used for takeoff. The Fowler flap deflects down and aft to increase the wing area. This flap can be multi-slotted, making it the most complex of the trailing edge systems. This system does, however, give the maximum lift coefficient. Drag characteristics at small deflections are much like the slotted flap. Because of structural complexity and difficulty in sealing the slots, Fowler flaps are most commonly used on larger airplanes. Operational procedures. It would be impossible to discuss all the many airplane designs and flap combinations. This emphasizes the importance of the FAA-approved Airplane Flight Manual and/or Pilot's Operating Handbook, AFM-POH, for a given airplane. However, while some AFM-POHs are specific as to operational use of flaps, many are lacking. Hence, flap operation makes pilot judgment of critical importance. In addition, flap operation is used for landings and takeoffs, during which the airplane is in close proximity to the ground where the margin for error is small. Since the recommendations given in the AFM-POH are based on the airplane and the flap design combination, the pilot must relate the manufacturer's recommendation to aerodynamic effects of flaps. This requires that the pilot have a basic background knowledge of flap aerodynamics and geometry. With this information, the pilot must make a decision as to the degree of flap deflection and time of deflection based on runway and approach conditions relative to the wind conditions. The time of flap extension and degree of deflection are related. Large flap deflections at one single point in the landing pattern produce large lift changes that require significant pitch and power changes in order to maintain airspeed and glide slope. Incremental deflection of flaps on downwind, base, and final approach allows smaller adjustment of pitch and power compared to extension of full flaps all at one time. This procedure facilitates a more stabilized approach. A soft or short-field landing requires minimal speed at touchdown. The flap deflection that results in minimal ground speed therefore should be used. If obstacle clearance is a factor, the flap deflection that results in the steepest angle of approach should be used. It should be noted, however, that the flap setting that gives the minimal speed at touchdown does not necessarily give the steepest angle of approach. However, maximum flap extension gives the steepest angle of approach and minimum speed at touchdown. Maximum flap extension, particularly beyond 30 to 35 degrees, results in a large amount of drag. This requires higher power settings than used with partial flaps. Because of the steep approach angle combined with power to offset drag, the flare with full flaps becomes critical. The drag produces a high sink rate that must be controlled with power, yet failure to reduce power at a rate so that the power is idle at touchdown allows the airplane to float down the runway. A reduction in power too early results in a hard landing. Crosswind component is another factor to be considered in the degree of flap extension. The deflected flap presents a surface area for the wind to act on. In a crosswind, the flapped wing on the upwind side is more affected than the downwind wing. This is, however, eliminated to a slight extent in the crabbed approach, since the airplane is more nearly aligned with the wind. When using a wing-low approach, however, the lowered wing partially blankets the upwind flap, but the dihedral of the wing combined with the flap and wind make lateral control more difficult. Lateral control becomes more difficult as flap extension reaches maximum and the crosswind becomes perpendicular to the runway. Crosswind effects on the flapped wing become more pronounced as the airplane comes closer to the ground. The wing, flap, and ground form a container that is filled with air by the crosswind. With the wind striking the deflected flap and fuselage side, and with the flap located behind the main gear, the upwind wing will tend to rise and the airplane will tend to turn into the wind. Proper control position, therefore, is essential for maintaining runway alignment. Also, it may be necessary to retract the flaps upon positive ground contact. The go-around is another factor to consider when making a decision about degree of flap deflection and about where in the landing pattern to extend flaps. Because of the nose-down pitching moment produced with flap extension, trim is used to offset this pitching moment. Application of full power in the go-around increases the airflow over the flapped wing. This produces additional lift, causing the nose to pitch up. The pitch-up tendency does not diminish completely with flap retraction because of the trim setting. Expedient retraction of flaps is desirable to eliminate drag, thereby allowing rapid increase in airspeed. However, flap retraction also decreases lift so that the airplane sinks rapidly. The degree of flap deflection combined with design configuration of the horizontal tail relative to the wing requires that the pilot carefully monitor pitch and airspeed, carefully control flap retraction to minimize altitude loss, and properly use the rudder for coordination. Considering these factors, the pilot should extend the same degree of deflection at the same point in the landing pattern. This requires that a consistent traffic pattern be used. Therefore, the pilot can have a pre-planned go-around sequence based on the airplane's position in the landing pattern. There is no single formula to determine the degree of flap deflection to be used on landing, because a landing involves variables that are dependent on each other. The AFM-POH for the particular airplane will contain the manufacturer's recommendations for some landing situations. On the other hand, AFM-POH information on flap usage for takeoff is more precise. The manufacturer's requirements are based on the climb performance produced by a given flap design. Under no circumstances should a flap setting given in the AFM-POH be exceeded for takeoff. Controllable pitch propeller. Fixed pitch propellers are designed for best efficiency at one speed of rotation and forward speed. This type of propeller will provide suitable performance in a narrow range of airspeeds. However, efficiency would suffer considerably outside this range. To provide high propeller efficiency through a wide range of operation, the propeller blade angle must be controllable. The most convenient way of controlling the propeller blade angle is by means of a constant speed governing system. Constant speed propeller. The constant speed propeller keeps the blade angle adjusted for maximum efficiency for most conditions of flight. When an engine is running at constant speed, the torque, power, exerted by the engine at the propeller shaft must equal the opposing load provided by the resistance of the air. The RPM is controlled by regulating the torque absorbed by the propeller. In other words, by increasing or decreasing the resistance offered by the air to the propeller. In the case of a fixed-pitch propeller, the torque absorbed by the propeller is a function of speed, or RPM. If the power output of the engine is changed, the engine will accelerate or decelerate until an RPM is reached at which the power delivered is equal to the power absorbed. In the case of a constant-speed propeller, the power absorbed is independent of the RPM. For by varying the pitch of the blades, the air resistance and hence the torque or load can be changed without reference to propeller speed. This is accomplished with a constant-speed propeller by means of a governor. The governor, in most cases, is geared to the engine crankshaft and thus is sensitive to changes in engine RPM. The pilot controls the engine RPM indirectly by means of a propeller control in the cockpit, which is connected to the governor. For maximum takeoff power, the propeller control is moved all the way forward to the low-pitch, high RPM position, and the throttle is moved forward to the maximum allowable manifold pressure position. To reduce power for climb or cruise, manifold pressure is reduced to the desired value with the throttle, and the engine RPM is reduced by moving the propeller control back toward the high-pitch, low RPM position until the desired RPM is observed on the tachometer. Pulling back on the propeller control causes the propeller blades to move to a higher angle. Increasing the propeller blade angle of attack results in an increase in the resistance of the air. This puts a load on the engine so it slows down. In other words, the resistance of the air at the higher blade angle is greater than the torque or power delivered to the propeller by the engine, so it slows down to a point where the two forces are in balance. When an airplane is nosed up into a climb from level flight, the engine will tend to slow down. Since the governor is sensitive to small changes in engine RPM, it will decrease the blade angle just enough to keep the engine speed from falling off. If the airplane is nosed down into a dive, the governor will increase the blade angle enough to prevent the engine from overspeeding. This allows the engine to maintain a constant RPM, and thus maintain the power output. Changes in airspeed and power can be obtained by changing RPM at a constant manifold pressure, by changing the manifold pressure at a constant RPM, or by changing both RPM and manifold pressure. Thus, the constant speed propeller makes it possible to obtain an infinite number of power settings. Takeoff, climb, and cruise. During takeoff, when the forward motion of the airplane is at low speeds and when maximum power and thrust are required, the constant speed propeller sets up a low propeller blade angle, pitch. The low blade angle keeps the angle of attack with respect to the relative wind small and efficient at the low speed. See Figure 11-3. At the same time, it allows the propeller to slice it thin and handle a smaller mass of air per revolution. This light load allows the engine to turn at maximum RPM and develop maximum power. Although the mass of air per revolution is small, the number of revolutions per minute is high. Thrust is maximum at the beginning of the takeoff and then decreases as the airplane gains speed and the airplane drag increases. Due to the high slipstream velocity during takeoff, the effective lift of the wing behind the propeller is increased. As the airspeed increases after liftoff, the load on the engine is lightened because of the small blade angle. The governor senses this and increases the blade angle slightly. Again, the higher blade angle with the higher speeds keeps the angle of attack with respect to the relative wind small and efficient. For climb after takeoff, the power output of the engine is reduced to climb power by decreasing the manifold pressure and lowering RPM by increasing the blade angle. At the higher climb airspeed and the higher blade angle, the propeller is handling a greater mass of air per second at a lower slipstream velocity. This reduction in power is offset by the increase in propeller efficiency. The angle of attack is again kept small by the increase in the blade angle with an increase in airspeed. At cruising altitude, when the airplane is in level flight, less power is required to produce a higher airspeed than is used in climb. Consequently, engine power is again reduced by lowering the manifold pressure and increasing the blade angle to decrease RPM. The higher airspeed and higher blade angle enable the propeller to handle a still greater mass of air per second at still smaller slipstream velocity. At normal cruising speeds, propeller efficiency is at or near maximum efficiency. Due to the increase in blade angle and airspeed, the angle of attack is still small and efficient. Blade angle control. Once the pilot selects the RPM settings for the propeller governor automatically adjusts the blade angle to maintain the selected RPM. It does this by using oil pressure. Generally, the oil pressure used for pitch change comes directly from the engine lubricating system. When a governor is employed, engine oil is used and the oil pressure is usually boosted by a pump, which is integrated with the governor. The higher pressure provides a quicker blade angle change. The RPM at which the propeller is to operate is adjusted in the governor head. The pilot changes this setting by changing the position of the governor rack through the cockpit propeller control. On some constant-speed propellers, changes in pitch are obtained by the use of an inherent centrifugal twisting moment of the blades that tends to flatten the blades toward low pitch, and oil pressure applied to a hydraulic piston connected to the propeller blades, which moves them toward high pitch. Another type of constant-speed propeller uses counterweights attached to the blade shanks in the hub. Governor oil pressure and the blade twisting moment move the blades toward the low pitch position, and centrifugal force acting on the counterweights moves them and the blades toward the high pitch position. In the first case above, governor oil pressure moves the blades towards high pitch, and in the second case, governor oil pressure and the blade twisting moment move the blades toward low pitch. A loss of governor oil pressure, therefore, will affect each differently. Governing range. The blade angle range for constant-speed propellers varies from about 11.5 to 40 degrees. The higher the speed of the airplane, the greater the blade angle range. See Figure 11-4. The range of possible blade angles is termed the propeller's governing range. The governing range is defined by the limits of the propeller blade's travel between high and low blade angle pitch stops. As long as the propeller blade angle is within the governing range and not against either pitch stop, a constant engine RPM will be maintained. However, once the propeller blade reaches its pitch stop limit, the engine RPM will increase or decrease with changes in airspeed and propeller load similar to a fixed-pitch propeller. For example, once a specific RPM is selected, if the airspeed decreases enough, the propeller blades will reduce pitch in an attempt to maintain the selected RPM until they contact their low-pitch stops. From that point, any further reduction in airspeed will cause the engine RPM to decrease. Conversely, if the airspeed increases, the propeller blade angle will increase until the high pitch stop is reached. The engine RPM will then begin to increase. Constant speed propeller operation. The engine is started with the propeller control in the low pitch, high RPM position. This position reduces the load or drag of the propeller, and the result is easier starting and warm-up of the engine. During warm-up, the propeller blade changing mechanism should be operated slowly and smoothly through a full cycle. This is done by moving the propeller control with the manifold pressure set to produce about 1,600 RPM to the high-pitch, low RPM position, allowing the RPM to stabilize and then moving the propeller control back to the low-pitch takeoff position. This should be done for two reasons: to determine whether the system is operating correctly and to circulate fresh, warm oil through the propeller governor system. It should be remembered that the oil has been trapped in the propeller cylinder since the last time the engine was shut down. There is a certain amount of leakage from the propeller cylinder, and the oil tends to congeal, especially if the outside air temperature is low. Consequently, if the propeller isn't exercised before takeoff, there is a possibility that the engine may overspeed on takeoff. An airplane equipped with a constant speed propeller has better takeoff performance than a similarly powered airplane equipped with a fixed-pitch propeller. This is because with a constant speed propeller, an airplane can develop its maximum rated horsepower, red line on the tachometer, while motionless. An airplane with a fixed-pitch propeller, on the other hand, must accelerate down the runway to increase airspeed and aerodynamically unload the propeller so that RPM and horsepower can steadily build up to their maximum. With a constant speed propeller, the tachometer reading should come up to within 40 RPM of the red line as soon as full power is applied, and should remain there for the entire takeoff. Excessive manifold pressure raises the cylinder compression pressure, resulting in high stresses within the engine. Excessive pressure also produces high engine temperatures. A combination of high manifold pressure and low RPM can induce damaging detonation. In order to avoid these situations, the following sequence should be followed when making power changes. When increasing power, increase the RPM first and then the manifold pressure. When decreasing power, decrease the manifold pressure first and then decrease the RPM. It is a fallacy that, in non-turbocharged engines, the manifold pressure in inches of mercury, inches Hg, should never exceed RPM in hundreds for cruise power settings. The cruise power charts in the AFM-POH should be consulted when selecting cruise power settings. Whatever the combinations of RPM and manifold pressure listed in these charts, they have been flight tested and approved by the airframe and power plant engineers for the respective airframe and engine manufacturer. Therefore, if there are power settings such as 2100 RPM and 24 inches manifold pressure in the power chart, they are approved for use. With a constant speed propeller, a powered descent can be made without overspeeding the engine. The system compensates for the increased airspeed of the descent by increasing the propeller blade angles. If the descent is too rapid or is being made from a high altitude, the maximum blade angle limit of the blades is not sufficient to hold the RPM constant. When this occurs, the RPM is responsive to any change in throttle setting. Some pilots consider it advisable to set the propeller control for maximum RPM during the approach to have full horsepower available in case of emergency. If the governor is set for this higher RPM early in the approach, when the blades have not yet reached their minimum angle stops, the RPM may increase to unsafe limits. However, if the propeller control is not readjusted for the takeoff RPM until the approach is almost completed, the blades will be against or very near the minimum angle stops, and there will be little, if any, change in RPM. In case of emergency, both throttle and propeller controls should be moved to takeoff positions. Many pilots prefer to feel the airplane respond immediately when they give short bursts of the throttle during approach. By making the approach under a little power and having the propeller control set at or near cruising RPM, this result can be obtained. Although the governor responds quickly to any change in throttle setting, a sudden and large increase in throttle setting will cause a momentary overspeeding of the engine until the blades become adjusted to absorb the increased power. If an emergency demanding full power should arise during approach, the sudden advancing of the throttle will cause momentary overspeeding of the engine beyond the RPM for which the governor is adjusted. This temporary increase in engine speed acts as an emergency power reserve. Some important points to remember concerning constant speed propeller operations are: the red line on the tachometer not only indicates maximum allowable RPM, it also indicates the RPM required to obtain the engine's rated horsepower. A momentary propeller overspeed may occur when the throttle is advanced rapidly for takeoff. This is usually not serious if the rated RPM is not exceeded by 10% for more than 3 seconds. The green arc on the tachometer indicates the normal operating range. When developing power in this range, the engine drives the propeller. Below the green arc, however, it is usually the windmilling propeller that powers the engine. Prolonged operation below the green arc can be detrimental to the engine. On takeoffs from low-elevation airports, the manifold pressure in inches of mercury may exceed the RPM. This is normal in most cases. The pilot should consult the AFM-POH for limitations. All power changes should be made smoothly and slowly to avoid overboosting and/or overspeeding. End of Chapter 11, Part 1. Chapter 11, Part 2, a Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook by the FAA. Transition to Complex Aircraft Part 2. Turbocharging. The turbocharged engine allows the pilot to maintain sufficient cruise power at high altitudes where there is less drag, which means faster true air speeds and increased range with fuel economy. At the same time, the power plant has flexibility and can be flown at a low altitude without the increased fuel consumption of a turbine engine. When attached to the standard power plant, the turbocharger does not take any horsepower from the power plant to operate. It is relatively simple mechanically, and some models can pressurize the cabin as well. The turbocharger is an exhaust-driven device, which raises the pressure and density of the induction air delivered to the engine. It consists of two separate components, a compressor and a turbine connected by a common shaft. The compressor supplies pressurized air to the engine for high-altitude operation. The compressor and its housing are between the ambient air intake and the induction air manifold. The turbine and its housing are part of the exhaust system and utilize the flow of exhaust gases to drive the compressor. See Figure 11-5. The turbine has the capability of producing manifold pressure in excess of the maximum allowable for the particular engine. In order not to exceed the maximum allowable manifold pressure, a bypass or wastegate is used so that some of the exhaust will be diverted overboard before it passes through the turbine. The position of the wastegate regulates the output of the turbine and therefore the compressed air available to the engine. When the wastegate is closed, all of the exhaust gases pass through and drive the turbine. As the wastegate opens, some of the exhaust gases are routed around the turbine through the exhaust bypass and overboard through the exhaust pipe. The wastegate actuator is a spring-loaded piston operated by engine oil pressure. The actuator, which adjusts the wastegate position, is connected to the wastegate by a mechanical linkage. The control center of the turbocharger system is the pressure controller. This device simplifies turbocharging to one control, the throttle. Once the pilot has set the desired manifold pressure, virtually no throttle adjustment is required with changes in altitude. The controller senses compressor discharge requirements for various altitudes and controls the oil pressure to the wastegate actuator, which adjusts the wastegate accordingly. Thus, the turbocharger maintains only the manifold pressure called for by the throttle setting. Ground boosting versus altitude turbocharging. Altitude turbocharging, sometimes called normalizing, is accomplished by using a turbocharger that will maintain maximum allowable sea level manifold pressure, normally 29 to 30 inches Hg, up to a certain altitude. This altitude is specified by the airplane manufacturer and is referred to as the airplane's critical altitude. Above the critical altitude, the manifold pressure decreases as additional altitude is gained. Ground boosting, on the other hand, is an application of turbocharging where more than the standard 29 inches of manifold pressure is used in flight. In various airplanes using ground boosting, takeoff manifold pressures may go as high as 45 inches of mercury. Although a sea level power setting and maximum RPM can be maintained up to the critical altitude, this does not mean that the engine is developing sea level power. Engine power is not determined just by manifold pressure and RPM. Induction air temperature is also a factor. Turbocharged induction air is heated by compression. This temperature rise decreases induction air density, which causes a power loss. Maintaining the equivalent horsepower output will require a somewhat higher manifold pressure at a given altitude than if the induction air were not compressed by turbocharging. If, on the other hand, the system incorporates an automatic density controller which, instead of maintaining a constant manifold pressure, automatically positions the wastegate so as to maintain constant air density to the engine, a near constant horsepower output will result. Operating characteristics. First and foremost, all movements of the power controls on turbocharged engines should be slow and gentle. Aggressive and/or abrupt throttle movements increase the possibility of overboosting. The pilot should carefully monitor engine indications when making power changes. When the wastegate is open, the turbocharged engine will react the same as a normally aspirated engine when the RPM is varied. That is, when the RPM is increased, the manifold pressure will decrease slightly. When the engine RPM is decreased, the manifold pressure will increase slightly. However, when the wastegate is closed, manifold pressure variation with engine RPM is just the opposite of the normally aspirated engine. An increase in engine RPM will result in an increase in manifold pressure, and a decrease in engine RPM will result in a decrease in manifold pressure. Above the critical altitude, where the wastegate is closed, any change in airspeed will result in a corresponding change in manifold pressure. This is true because the increase in ram air pressure with an increase in airspeed is magnified by the compressor, resulting in an increase in manifold pressure. The increase in manifold pressure creates a higher mass flow through the engine, causing higher turbine speeds and thus further increasing manifold pressure. When running at high altitudes, aviation gasoline may tend to vaporize prior to reaching the cylinder. If this occurs in the portion of the fuel system between the fuel tank and the engine-driven fuel pump, an auxiliary positive pressure pump may be needed in the tank. Since engine-driven pumps pull fuel, they are easily vapor-locked. A boost pump provides positive pressure, pushes the fuel, reducing the tendency to vaporize. Heat management. Turbocharged engines must be thoughtfully and carefully operated with continuous monitoring of pressures and temperatures. There are two temperatures that are especially important: turbine inlet temperature, TIT, or in some installations, exhaust gas temperature, EGT, and cylinder head temperature. TIT or EGT limits are set to protect the elements in the hot sections of the turbocharger, while cylinder head temperature limits protect the engine's internal parts. Due to the heat of compression of the induction air, a turbocharged engine runs at higher operating temperatures than a non-turbocharged engine. Because turbocharged engines operate at high altitudes, their environment is less efficient for cooling. At altitude, the air is less dense and therefore cools less efficiently. Also, the less dense air causes the compressor to work harder. Compressor turbine speeds can reach 80,000 to 100,000 RPM, adding to the overall engine operating temperatures. Turbocharged engines are also operated at higher power settings a greater portion of the time. High heat is detrimental to piston engine operation. Its cumulative effects can lead to piston, ring, and cylinder head failure and place thermal stress on other operating components. Excessive cylinder head temperature can lead to detonation, which in turn can cause catastrophic engine failure. Turbocharged engines are especially heat sensitive. The key to turbocharger operation, therefore, is effective heat management. The pilot monitors the condition of a turbocharged engine with manifold pressure gauge, tachometer, exhaust gas temperature, turbine inlet temperature gauge, and cylinder head temperature. The pilot manages the heat system with the throttle, propeller RPM, mixture, and cowl flaps. At any given cruise power, the mixture is the most influential control over the exhaust gas turbine inlet temperature. The throttle regulates total fuel flow, but the mixture governs the fuel-to-air ratio. The mixture, therefore, controls temperature. Exceeding temperature limits in an after-takeoff climb is usually not a problem, since a full-rich mixture cools with excess fuel. At a cruise, however, the pilot normally reduces power to 75% or less and simultaneously adjusts the mixture. Under cruise conditions, temperature limits should be monitored most closely because it's there that the temperatures are most likely to reach the maximum, even though the engine is producing less power. Overheating in an en route climb, however, may require fully open cowl flaps and a higher airspeed. Since turbocharged engines operate hotter at altitude than do normally aspirated engines, they are more prone to damage from cooling stress. Gradual reductions in power and careful monitoring of temperatures are essential in the descent phase. The pilot may find it helpful to lower the landing gear to give the engine something to work against while power is reduced and provide time for a slow cool down. It may also be necessary to lean the mixture slightly to eliminate roughness at the lower power settings. Turbocharger failure. Because of the high temperatures and pressures produced in the turbine exhaust systems, any malfunction of the turbocharger must be treated with extreme caution. In all cases of turbocharger operation, the manufacturer's recommended procedures should be followed. This is especially so in the case of turbocharger malfunction. However, in those instances where the manufacturer's procedures do not adequately describe the actions to be taken in the event of a turbocharger failure, the following procedures should be used. Overboost condition. If an excessive rise in manifold pressure occurs during normal advancement of the throttle, possibly owing to faulty operation of the wastegate, immediately retard the throttle smoothly to limit the manifold pressure below the maximum for the RPM and mixture setting. Operate the engine in such a manner as to avoid a further overboost condition. Low manifold pressure. Although this condition may be caused by a minor fault, it is quite possible that a serious exhaust leak has occurred, creating a potentially hazardous situation. Shut down the engine in accordance with the recommended engine failure procedures unless a greater emergency exists that warrants continued engine operation. If continuing to operate the engine, use the lowest power setting demanded by the situation and land as soon as practicable. It is very important to ensure that corrective maintenance is undertaken following any turbocharger malfunction. Retractable landing gear. The primary benefits of being able to retract the landing gear are increased climb performance and higher cruise airspeeds due to the resulting decrease in drag. Retractable landing gear systems may be operated either hydraulically or electrically, or may employ a combination of the two systems. Warning indicators are provided in the cockpit to show the pilot when the wheels are down and locked, and when they are up and locked, or if they are in intermediate positions. Systems for emergency operation are also provided. The complexity of the retractable landing gear system requires that specific operating procedures be adhered to and that certain operating limitations not be exceeded. Landing gear systems. An electrical landing gear retraction system utilizes an electrically driven motor for gear operations. The system is basically an electrically driven jack for raising and lowering the gear. When a switch in the cockpit is moved to the up position, the electric motor operates. Through a system of shafts, gears, adapters, an actuator screw, and a torque tube, a force is transmitted to the drag strut linkages. Thus, the gear retracts and locks. Struts are also activated that open and close the gear doors. If the switch is moved to the down position, the motor reverses and the gear moves down and locks. Once activated, the gear motor will continue to operate until an up or down limit switch on the motor's gearbox is tripped. A hydraulic landing gear retraction system utilizes pressurized hydraulic fluid to actuate linkages to raise and lower the gear. When a switch in the cockpit is moved to the up position, hydraulic fluid is directed into the gear up line. The fluid flows through sequenced valves and down locks to the gear actuating cylinders. A similar process occurs during gear extension. The pump which pressurizes the fluid in the system can be either engine-driven or electrically powered. If an electrically powered pump is used to pressurize the fluid, the system is referred to as an electro-hydraulic system. The system also incorporates a hydraulic reservoir to contain excess fluid and to provide a means of determining system fluid level. Regardless of its power source, the hydraulic pump is designed to operate within a specific range. When a sensor detects excessive pressure, a relief valve within the pump opens and hydraulic pressure is routed back to the reservoir. Another type of relief valve prevents excessive pressure that may result from thermal expansion. Hydraulic pressure is also regulated by limit switches. Each gear has two limit switches, one dedicated to extension and one dedicated to retraction. These switches de-energize the hydraulic pump after the landing gear has completed its gear cycle. In the event of limit switch failure, a backup pressure relief valve activates to relieve excess system pressure. Controls and position indicators. Landing gear position is controlled by a switch in the cockpit. In most airplanes, the gear switch is shaped like a wheel in order to facilitate positive identification and to differentiate it from other cockpit controls. See Figure 11-6. Landing gear position indicators vary with different make and model airplanes. The most common types of landing gear position indicators utilize a group of lights. One type consists of a group of 3 green lights, which illuminate when the landing gear is down and locked. See Figure 11-6. Another type consists of 1 green light to indicate when the landing gear is down, and an amber light to indicate when the gear is up. Still other systems incorporate a red or amber light to indicate when the gear is in transit or unsafe for landing. See Figure 11-7. The lights are usually of the press-to-test type, and the bulbs are interchangeable. See Figure 11-6. Other types of landing gear position indicators consist of tab-type indicators with markings up to indicate the gear is up and locked, a display of red and white diagonal stripes to show when the gear is unlocked, or a silhouette of each gear to indicate when it locks in the down position. Landing gear safety devices. Most airplanes with a retractable landing gear have a gear warning horn that will sound when the airplane is configured for landing and the landing gear is not down and locked. Normally, the horn is linked to the throttle or flap position and/or the airspeed indicator so that when the airplane is below a certain airspeed, configuration, or power setting with the gear retracted, the warning horn will sound. Accidental retraction of a landing gear may be prevented by such devices as mechanical down locks, safety switches, and ground locks. Mechanical down locks are built-in components of a gear retraction system and are operated automatically by the gear retraction system. To prevent accidental operation of the down locks and inadvertent landing gear retraction while the airplane is on the ground, electrically operated safety switches are installed. A landing gear safety switch, sometimes referred to as a squat switch, is usually mounted in a bracket on one of the main gear shock struts. See Figure 11-8. When the strut is compressed by the weight of the airplane, the switch opens the electrical circuit to the motor or mechanism that powers retraction. In this way, if the landing gear switch in the cockpit is placed in the retract position when weight is on the gear will remain extended, and the warning horn may sound as an alert to the unsafe condition. Once the weight is off the gear, however, such as on takeoff, the safety switch will release and the gear will retract. Many airplanes are equipped with additional safety devices to prevent collapse of the gear when the airplane is on the ground. These devices are called ground locks. One common type is a pin installed in aligned holes drilled in 2 or more units of the landing gear support structure. Another type is a spring-loaded clip designed to fit around and hold 2 or more units of the support structure together. All types of ground locks usually have red streamers permanently attached to them to readily indicate whether or not they are installed. Emergency gear extension systems. The emergency extension system lowers the landing gear if the main power system fails. Some airplanes have an emergency release handle in the cockpit, which is connected through a mechanical linkage to the gear up locks. When the handle is operated, it releases the up locks and allows the gears to free fall or extend under their own weight. See Figure 11-9. On other airplanes, release of the uplock is accomplished using compressed gas, which is directed to uplock release cylinders. In some airplanes, design configurations make emergency extension of the landing gear by gravity and air loads alone impossible or impractical. In these airplanes, provisions are included for forceful gear extension in an emergency. Some installations are designed so that either hydraulic fluid or compressed gas provides the necessary pressure, while others use a manual system, such as a hand crank for emergency gear extension. See Figure 11-9. Hydraulic pressure for emergency operation of the landing gear may be provided by an auxiliary hand pump, an accumulator, or an electrically powered hydraulic pump depending on the design of the airplane. Operational procedures pre-flight. Because of their complexity, retractable landing gears demand a close inspection prior to every flight. The inspection should begin inside the cockpit. The pilot should first make certain that the landing gear selector switch is in the gear down position. The pilot should then turn on the battery master switch and ensure that the landing gear position indicators show that the gear is down and locked. External inspection of the landing gear should consist of checking individual system components. See Figure 11-10. The landing gear, wheel well, and adjacent areas should be clean and free of mud and debris. Dirty switches and valves may cause false safe light indications or interrupt the extension cycle before the landing gear is completely down and locked. The wheel wells should be clear of any obstructions, as foreign objects may damage the gear or interfere with its operation. Bent gear doors may be an indication of possible problems with normal gear operation. Shock struts should be properly inflated and the pistons clean. Main gear and nose gear uplock and downlock mechanisms should be checked for general condition. Power sources and retracting mechanisms should be checked for general condition, obvious defects, and security of attachment. Hydraulic lines should be checked for signs of chafing and leakage at attach points. Warning system microswitches, squat switches, should be checked for cleanliness and security of attachment. Actuating cylinders, sprockets, universals, drive gears, linkages, and any other accessible components should be checked for condition and obvious defects. The airplane structure to which the landing gear is attached should be checked for distortion, cracks, and general condition. All bolts and rivets should be intact and secure. Takeoff and climb. Normally, the landing gear should be retracted after liftoff when the airplane has reached an altitude where, in the event of an engine failure or other emergency requiring an aborted takeoff, the airplane could no longer be landed on the runway. This procedure, however, may not apply to all situations. Landing gear retraction should be pre-planned, taking into account the length of the runway, climb gradient, obstacle clearance requirements, the characteristics of the terrain beyond the departure end of the runway, and the climb characteristics of the particular airplane. For example, in some situations it may be preferable, in the event of an engine failure, to make an off-airport forced landing with the gear extended in order to take advantage of the energy-absorbing qualities of terrain. See Chapter 16. In which case a delay in retracting the landing gear after takeoff from a short runway may be warranted. In other situations, obstacles in the climb path may warrant a timely gear retraction after takeoff. Also, in some airplanes, the initial climb pitch attitude is such that any view of the runway remaining is blocked, making an assessment of the feasibility of touching down on the remaining runway difficult. Premature landing gear retraction should be avoided. The landing gear should not be retracted until a positive rate of climb is indicated on the flight instruments. If the airplane has not attained a positive rate of climb, there is always the chance it may settle back onto the runway with the gear retracted. This is especially so in cases of premature liftoff. The pilot should also remember that leaning forward to reach the landing gear selector may result in inadvertent forward pressure on the yoke, which will cause the airplane to descend. As the landing gear retracts, airspeed will increase and the airplane's pitch attitude may change. The gear may take several seconds to retract. Gear retraction and locking, and gear extension and locking, is accompanied by sound and feel that are unique to the specific make and model airplane. The pilot should become familiar with the sounds and feel of normal gear retraction so that any abnormal gear operation can be readily discernible. Abnormal landing gear retraction is most often a clear sign that the gear extension cycle will also be abnormal. Approach and landing. The operating loads placed on the landing gear at higher airspeeds may cause structural damage due to the forces of the airstream. Limiting speeds, therefore, are established for gear operation to protect the gear components from becoming overstressed during flight. These speeds are not found on the airspeed indicator. They are published in the AFM-POH for the particular airplane and are usually listed on placards in the cockpit. See Figure 11-11. The maximum landing extended speed, VLE, is the maximum speed at which the airplane can be flown with the landing gear extended. The maximum landing gear operating speed, VLO, is the maximum speed at which the landing gear may be operated through its cycle. The landing gear is extended by placing the gear selector switch in the gear down position. As the landing gear extends, the airspeed will decrease and the pitch attitude may increase. During the several seconds it takes for the gear to extend, the pilot should be attentive to any abnormal sounds or feel. The pilot should confirm that the landing gear is extended and locked by the normal sound and feel of the system operation, as well as by the gear position indicators in the cockpit. Unless the landing gear has been previously extended to aid in a descent to traffic pattern altitude, the landing gear should be extended by the time the airplane reaches a point on the downwind leg that is opposite the point of intended landing. The pilot should establish a standard procedure consisting of a specific position on the downwind leg at which to lower the landing gear. Strict adherence to this procedure will aid the pilot in avoiding unintentional gear-up landings. Operation of an airplane equipped with a retractable landing gear requires the deliberate, careful, and continued use of an appropriate checklist. When on the downwind leg, the pilot should make it a habit to complete the landing gear checklist for that airplane. This accomplishes two purposes. It ensures that action has been taken to lower the gear, and it increases the pilot's awareness so that the gear down indicators can be rechecked prior to landing. Unless good operating practices dictate otherwise, the landing roll should be completed and the airplane clear of the runway before any levers or switches are operated. This will accomplish the following. The landing gear strut safety switches will be actuated, deactivating the landing gear retract system. After rollout and clearing the runway, the pilot will be able to focus attention on the after-landing checklist and to identify the proper controls. Pilots transitioning to retractable gear airplanes should be aware that the most common pilot operational factors involved in retractable gear airplane accidents are neglected to extend landing gear, inadvertently retracted landing gear, activated gear but failed to check gear position, misused emergency gear system, retracted gear prematurely on takeoff, extended gear too late. In order to minimize the chances of a landing gear-related mishap, the pilot should use an appropriate checklist, a condensed checklist mounted in view of the pilot as a reminder for its use and easy reference can be especially helpful. Be familiar with and periodically review the landing gear emergency extension procedures for the particular airplane. Be familiar with the landing gear warning horn and warning light systems for the particular airplane. Use the horn system to cross-check the warning light system when an unsafe condition is noted. Review the procedure for replacing light bulbs in the landing gear warning light displays for the particular airplane so that you can properly replace a bulb to determine if the bulb in the display is good. Check to see if spare bulbs are available in the airplane's spare bulb supply as part of the pre-flight inspection. Be familiar with and aware of the sounds and feel of a properly operating landing gear system. Transition training. Transition to a complex airplane or a high-performance airplane should be accomplished through a structured course of training administered by a competent and qualified flight instructor. The training should be accomplished in accordance with a ground and flight training syllabus. See Figure 11-12. This sample syllabus for transition training is to be considered flexible. The arrangements of the subject matter may be changed and the emphasis may be shifted to fit the qualifications of the transitioning pilot, the airplane involved, and the circumstances of the training situation, provided the prescribed proficiency standards are achieved. These standards are contained in the practical test standards appropriate for the certificate that the transitioning pilot holds or is working towards. The training times indicated in the syllabus are based on the capabilities of a pilot who is currently active and fully meets the present requirements for the issuance of at least a private pilot certificate. The time periods may be reduced for pilots with higher qualifications or increased for pilots who do not meet the current certification requirements or who have had little recent flight experience. End of Chapter 11, Part 2.
Chapter 12, Part 1 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. Airplane Flying Handbook by the FAA. Transition to multi-engine airplanes. Multi-engine. This chapter is devoted to the factors associated with the operation of small multi-engine airplanes. For the purpose of this handbook, a small multi-engine airplane is a reciprocating or turbopropeller-powered airplane with a maximum certificated takeoff weight of 12,500 pounds or less. This discussion assumes a conventional design with two engines, one mounted on each wing. Reciprocating engines are assumed unless otherwise noted. The term light twin, although not formally defined in the regulations, is used herein as a small multi-engine airplane with a maximum certificated takeoff weight of 6,000 pounds or less. There are several unique characteristics of multi-engine airplanes that make them worthy of a separate class rating. Knowledge of these factors and proficient flight skills are a key to safe flight in these airplanes. This chapter deals extensively with the numerous aspects of one-engine inoperative OEI flight. However, pilots are strongly cautioned not to place undue emphasis on the mastery of OEI flight as the sole key to flying multi-engine airplanes safely. The inoperative engine information that follows is extensive only because this chapter emphasizes the differences between flying multi-engine airplanes as contrasted to single-engine airplanes. The modern, well-equipped multi-engine airplane can be remarkably capable under many circumstances. But, as with single-engine airplanes, it must be flown prudently by a current and competent pilot to achieve the highest possible level of safety. This chapter contains information and guidance on the performance of certain maneuvers and procedures in small multi-engine airplanes for the purposes of flight training and pilot certification testing. The final authority on the operation of a particular make and model airplane, however, is the airplane manufacturer. Both the flight instructor and the student should be aware that if any of the guidance in this handbook conflicts with the airplane manufacturer's recommended procedures and guidance, as contained in the FAA-approved Airplane Flight Manual and or Pilot's Operating Handbook, AFM-POH, it is the airplane manufacturer's guidance and procedures that take precedence. General. The basic difference between operating a multi-engine airplane and a single-engine airplane is the potential problem involving an engine failure. The penalties for loss of an engine are twofold: performance and control. The most obvious problem is the loss of 50% of power, which reduces climb performance 80 to 90%, sometimes even more. The other is the control problem caused by the remaining thrust, which is now asymmetrical. Attention to both these factors is crucial to safe OEI flight. The performance and systems redundancy of a multi-engine airplane is a safety advantage only to a trained and proficient pilot. Terms and definitions. Pilots of single-engine airplanes are already familiar with many performance V-speeds and their definitions. Twin-engine airplanes have several additional V-speeds unique to OEI operation. These speeds are differentiated by the notation SE for single-engine. A review of some of the key V-speeds and several new V-speeds unique to twin-engine airplanes follows. VR, rotation speed, the speed at which back pressure is applied to rotate the airplane to a takeoff attitude. VLOF, liftoff speed, the speed at which the airplane leaves the surface. Note, some manufacturers reference takeoff performance data to VR, others to VLOF. VX, best angle of climb speed, the speed at which the airplane will gain the greatest altitude for a given distance of forward travel. VXSE, best angle of climb speed with one engine inoperative. VY, Best rate of climb speed, the speed at which the airplane will gain the most altitude for a given unit of time. VYSE, best rate of climb speed with one engine inoperative, marked with a blue radial line on most airspeed indicators. Above the single-engine absolute ceiling, VYSE yields the minimum rate of sink. VSSE, safe intentional one-engine inoperative speed, originally known as safe single-engine speed, now formally defined in Title 14 of the Code of Federal Regulations, 14 CFR, Part 23, Airworthiness Standards, and required to be established and published in the AFM-POH. It is the minimum speed to intentionally render the critical engine inoperative. VMC, minimum control speed with a critical engine inoperative, marked with a red radial line on most airspeed indicators. The minimum speed at which directional control can be maintained under a very specific set of circumstances outlined in 14 CFR Part 23, Airworthiness Standards. Under the small airplane certification regulations currently in effect, the flight test pilot must be able to 1. Stop the turn that results when the critical engine is suddenly made inoperative within 20 degrees of the original heading, using maximum rudder deflection and a maximum of 5-degree bank. And 2. Thereafter, maintain straight flight with not more than a 5-degree bank. There is no requirement in this determination that the airplane be capable of climbing at this airspeed. VMC only addresses directional control. Further discussion of VMC, as determined during the airplane certification and demonstrated in pilot training, follows in minimum control airspeed. VMC demonstration. Figure 12-1. Unless otherwise noted, when V-speeds are given in the AFM-POH, they apply to sea level, standard day conditions at maximum takeoff weight. Performance speeds vary with aircraft weight, configuration, and atmospheric conditions. The speeds may be stated in statute miles per hour, mph, or knots, KTS, and they may be given as calibrated airspeeds, CAS, or indicated airspeeds, IAS. As a general rule, the newer AFM-POHs show V-speeds in knots indicated airspeed, KIAS. Some V-speeds are also stated in knots calibrated airspeed, KCAS, to meet certain regulatory requirements. Whenever available, pilots should operate the airplane from the published indicated airspeeds. With regard to climb performance, the multi-engine airplane, particularly in the takeoff or landing configuration, may be considered to be a single-engine airplane with its power plant divided into 2 units. There is nothing in 14 CFR Part 23 that requires a multi-engine airplane to maintain altitude when in takeoff or landing configuration with one engine inoperative. In fact, many twins are not required to do this in any configuration, even at sea level. The current 14 CFR Part 23 single-engine climb performance requirements for reciprocating engine-powered multi-engine airplanes are as follows. More than 6,000 pounds maximum weight and/or VSO more than 61 knots, the single-engine rate of climb in feet per minute, FPM, at 5,000 feet MSL must be equal to or at least 0.027 VSO squared. For airplanes type certificated February 4, 1991 or thereafter, the climb requirement is expressed in terms of a climb gradient, 1.5%. The climb gradient is not a direct equivalent of the 0.027 VSO squared formula. Do not confuse the date of type certification with the airplane's model year. The type certification basis of many multi-engine airplanes dates back to CAR 3, the Civil Aviation Regulations, forerunner of today's Code of Federal Regulations. 6,000 pounds or less maximum weight and VSO 61 knots or less, the single-engine rate of climb at 5,000 MSL must simply be determined. The rate of climb could be a negative number. There is no requirement for a single engine positive rate of climb at 5,000 feet or any other altitude. For light twins, type certificated February 4, 1991 or thereafter, the single engine climb gradient, positive or negative, is simply determined. Rate of climb is the altitude gain per unit of time, while climb gradient is the actual measure of altitude gained per 100 feet of horizontal travel, expressed as a percentage. An altitude gain of 1.5 feet per 100 feet of travel, or 15 feet per 1,000 feet, or 150 feet per 10,000, is a climb gradient of 1.5%. There is a dramatic performance loss associated with the loss of an engine, particularly just after takeoff. Any airplane's climb performance is a function of thrust horsepower, which is in excess of that required for level flight. In a hypothetical twin with each engine producing 200 thrust horsepower, assume that the total level flight thrust horsepower required is 175. In this situation, the airplane would ordinarily have a reserve of 225 thrust horsepower available for climb. Loss of one engine would only leave 25, 200 minus 175, thrust horsepower available for climb, a drastic reduction. Sea level rate of climb performance losses of at least 80 to 90%, even under ideal circumstances, are typical for multi-engine airplanes in OEI flight. Operation of systems. This section will deal with the systems that are generally found on multi-engine airplanes. Multi-engine airplanes share many features with complex single-engine airplanes. There are certain systems and features covered here, however, that are generally unique to airplanes with two or more engines. Propellers. The propellers of the multi-engine airplane may outwardly appear to be identical in operation to constant-speed propellers of many single-engine airplanes, but this is not the case. The propellers of multi-engine airplanes are featherable to minimize the drag in the event of an engine failure. Depending upon single-engine performance, this feature often permits continued flight to a suitable airport following an engine failure. To feather a propeller is to stop engine rotation with the propeller blades streamlined with the airplane's relative wind, thus to minimize drag. See Figure 12-2. Feathering is necessary because of the change in parasite drag with propeller blade angle. Figure 12-3. When the propeller blade angle is in the feathered position, the change in parasite drag is at a minimum, and in the case of a typical multi-engine airplane, the added parasite drag from a single feathered propeller is a relatively small contributor to the airplane total drag. At the smaller blade angles near the flat pitch position, the drag added by the propeller is very large. At these small blade angles, the propeller windmilling at high RPM can create such a tremendous amount of drag that the airplane may be uncontrollable. The propeller windmilling at high speed in the low range of blade angles can produce an increase in parasite drag, which may be as great as the parasite drag of the basic airplane. As a review, the constant speed propellers on almost all single-engine airplanes are of the non-feathering, oil pressure to increased pitch design. In this design, increased oil pressure from the propeller governor drives the blade angle towards high pitch, low RPM. In contrast, the constant speed propellers installed on most multi-engine airplanes are full feathering, counterweighted, oil pressure to decrease pitch designs. In this design, increased oil pressure from the propeller governor drives the blade angle towards low pitch, high RPM, away from the feather blade angle. In effect, the only thing that keeps these propellers from feathering is a constant supply of high-pressure engine oil. This is a necessity to enable propeller feathering in the event of a loss of oil pressure or a propeller governor failure. The aerodynamic forces alone, acting upon a windmilling propeller, tend to drive the blades to low pitch, high RPM. Counterweights attached to the shank of each blade tend to drive the blades to high pitch, low RPM. Inertia, or apparent force called centrifugal force, acting through the counterweights, is generally slightly greater than the aerodynamic forces. Oil pressure from the propeller governor is used to counteract the counterweights and drives the blade angles to low pitch, high RPM. A reduction in oil pressure causes the RPM to be reduced from the influence of the counterweights. Figure 12-4. To feather the propeller control is brought fully aft. All oil pressure is dumped from the governor, and the counterweights drive the propeller blades towards feather. As centrifugal force acting on the counterweights decays from decreasing RPM, additional forces are needed to completely feather the blades. This additional force comes from either a spring or high-pressure air stored in the propeller dome, which forces the blades into the feathered position. The entire process may take up to 10 seconds. Feathering a propeller only alters blade angle and stops engine rotation. To completely secure the engine, the pilot must still turn off the fuel, mixture, electric boost pump, and fuel selector, ignition, alternator/generator, and close the cowl flaps. If the airplane is pressurized, there also may be an air bleed to close for the failed engine. Some airplanes are equipped with firewall shutoff valves that secure several of these systems with a single switch. Completely securing a failed engine may not be necessary or even desirable depending upon the failure mode, altitude, and time available. The position of the fuel controls, ignition, and alternator/generator switches of the failed engine has no effect on aircraft performance. There is always the distinct possibility of manipulating the incorrect switch under conditions of haste or pressure. To unfeather a propeller, the engine must be rotated so that oil pressure can be generated to move the propeller blades from the feathered position. The ignition is turned on prior to engine rotation, with the throttle at low idle and the mixture rich. With the propeller control in a high RPM position, the starter is engaged. The engine will begin to windmill, start, and run as the oil pressure moves the blades out of feather. As the engine starts, the propeller RPM should be immediately reduced until the engine has had several minutes to warm up. The pilot should monitor cylinder head and oil temperatures. Should the RPM obtained with the starter be insufficient to unfeather the propeller, an increase in airspeed from a shallow dive will usually help. In any event, the AFM-POH procedures should be followed for the exact unfeathering procedure. Both feathering and starting a feathered reciprocating engine on the ground are strongly discouraged by manufacturers due to the excessive stress and vibrations generated. As just described, a loss of oil pressure from the propeller governor allows the counterweights, spring, and/or dome charge to drive the blades to feather. Logically, then, the propeller blades should feather every time an engine is shut down as oil pressure falls to zero. Yet this does not occur. Preventing this is a small pin in the pitch-changing mechanism of the propeller hub that will not allow the propeller blades to feather once RPM drops below approximately 800. The pin senses the lack of centrifugal force from the propeller rotation and falls into place, preventing the blades from feathering. Therefore, if a propeller is to be feathered, it must be done before engine RPM decays below approximately 800. On one popular model of turboprop engine, the propeller blades do, in fact, feather with each shutdown. This propeller is not equipped with such centrifugally operated pins, due to a unique engine design. An unfeathering accumulator is an optional device that permits starting a feathered engine in flight without the use of the electric starter. An accumulator is any device that stores a reserve of high pressure. On multi-engine airplanes, the unfeathering accumulator stores a small reserve of engine oil under pressure from compressed air or nitrogen. To start a feathered engine in flight, the pilot moves the propeller control out of the feather position to release the accumulator pressure. The oil flows under pressure to the propeller hub and drives the blades toward the high RPM, low-pitch position, whereupon the propeller will usually begin to windmill. On some airplanes, an assist from the electric starter may be necessary to initiate rotation and completely unfeather the propeller. If fuel and ignition are present, the engine will start and run. For airplanes used in training, this saves much electric starter and battery wear. High oil pressure from the propeller governor recharges the accumulator just moments after engine rotation begins. Propeller synchronization. Many multi-engine airplanes have a propeller synchronizer, prop sync, installed to eliminate the annoying drumming or beat of propellers whose RPM are close but not precisely the same. To use prop sync, the propeller RPM are coarsely matched by the pilot and the system is engaged. The prop sync adjusts the RPM of the slave engine to precisely match the RPM of the master engine, and then maintains the relationship. The prop sync should be disengaged when the pilot selects a new propeller RPM, then re-engaged after the new RPM is set. The prop sync should always be off for takeoff, landing, and single-engine operation. The AFM-POH should be consulted for system description and limitations. A variation of the propeller synchronizer is the propeller synchrophaser. Prop synchrophase acts much like a synchronizer to precisely match RPM, but the synchrophaser goes one step further. It not only matches RPM, but actually compares and adjusts the positions of the individual blades of the propellers in their arcs. There can be significant propeller noise and vibration reductions with a propeller synchrophaser. From the pilot's perspective, operation of a propeller synchronizer and a propeller synchrophaser are very similar. A synchrophaser is also commonly referred to as prop sync, although it is not entirely correct nomenclature from a technical standpoint. As a pilot aid to manually synchronizing the propellers, some twins have a small gauge mounted in or by the tachometers with a propeller symbol on a disc that spins. The pilot manually fine-tunes the engine RPM so as to stop disc rotation, thereby synchronizing the propellers. This is a useful backup to synchronizing engine RPM using the audible propeller beat. This gauge is also found installed with most propeller synchronizer and synchrophase systems. Some synchrophase systems use a knob for the pilot to control the phase angle. Fuel crossfeed. Fuel crossfeed systems are also unique to multi-engine airplanes. Using crossfeed, an engine can draw fuel from a fuel tank located in the opposite wing. In most multi-engine airplanes, operation in the crossfeed mode is an emergency procedure used to extend airplane range and endurance in OEI flight. There are a few models that permit crossfeed as a normal fuel balancing technique in normal operation, but these are not common. The AFM-POH will describe crossfeed limitations and procedures, which vary significantly among multi-engine airplanes. Checking crossfeed operation on the ground with a quick repositioning of the fuel selectors does nothing more than ensure freedom of motion of the handle. To actually check crossfeed operation, a complete functional crossfeed system check should be accomplished. To do this, each engine should be operated from its crossfeed position during the run-up. The engines should be checked individually and allowed to run at moderate power, 1500 RPM minimum, for at least 1 minute to ensure that fuel flow can be established from the crossfeed source. Upon completion of the check, each engine should be operated for at least 1 minute at moderate power from the main takeoff fuel tanks to reconfirm fuel flow prior to takeoff. This suggested check is not required prior to every flight. Infrequently used, however, crossfeed lines are ideal places for water and debris to accumulate unless they are used from time to time and drained using their external drains during pre-flight. Crossfeed is ordinarily not used for completing single-engine flights when an alternative airport is readily at hand, and it is never used during takeoff or landings. Combustion heater. Combustion heaters are common on multi-engine airplanes. A combustion heater is best described as a small furnace that burns gasoline to produce heated air for occupant comfort and windshield defogging. Most are thermostatically operated and have a separate hour meter to record time in service for maintenance purposes. Automatic over-temperature protection is provided by a thermal switch mounted on the unit, which cannot be accessed in flight. This requires the pilot or mechanic to actually visually inspect the unit for possible heat damage in order to reset the switch. When finished with the combustion heater, a cool-down period is required. Most heaters require that outside air be permitted to circulate through the unit for at least 15 seconds in flight, or that the ventilation fan be operated for at least 2 minutes on the ground. Failure to provide an adequate cool-down will usually trip the thermal switch and render the heater inoperative until the switch is reset. Flight Director/Autopilot. Flight Director/Autopilot, FD/AP systems are common on the better-equipped multi-engine airplanes. The system integrates pitch, roll, heading, altitude, and radio navigation signals in a computer. The outputs, called computed commands, are displayed on a Flight Command Indicator, or FCI. The FCI replaces the conventional attitude indicator on the instrument panel. The FCI is occasionally referred to as a Flight Director Indicator, FDI, or as an Attitude Director Indicator, ADI. The entire Flight Director/Autopilot system is sometimes called an Integrated Flight Control System, IFCS, by some manufacturers. Others may use the term Automatic Flight Control System, AFCS. The FD/AP system may be employed at 3 different levels: off, raw data; flight director, computed commands; autopilot. With the system off, the FCI operates as an ordinary attitude indicator. On most FCIs, the command bars are biased out of view when the flight director is off. The pilot maneuvers the airplane as though the system were not installed. To maneuver the airplane using the flight director, the pilot enters the desired modes of operation, heading, altitude, nav intercept, and tracking, on the FD/AP mode controller. The computed flight commands are then displayed to the pilot through either a single queue or dual queue system in the FCI. On a single queue system, the commands are indicated by V-bars. On a dual queue system, the commands are displayed on 2 separate command bars, one for pitch and one for roll. To maneuver the airplane using computed commands, the pilot flies the symbolic airplane of the FCI to match the steering cues presented. On most systems, to engage the autopilot, the flight director must first be operating. At any time thereafter, the pilot may engage the autopilot through the mode controller. The autopilot then maneuvers the airplane to satisfy the computed commands of the flight director. Like any computer, the FD/AP system will only do what it is told. The pilot must ensure that it has been properly programmed for the particular phase of flight desired. The armed and/or engaged modes are usually displayed on the mode controller or separate annunciator lights. When the airplane is being hand-flown, if the flight director is not being used at any particular moment, it should be off, so that the command bars are pulled from view. Prior to system engagement, all FD/AP computer and trim checks should be accomplished. Many newer systems cannot be engaged without the completion of a self-test. The pilot must also be very familiar with various methods of disengagement, both normal and emergency. System details, including approvals and limitations, can be found in the supplements section of the AFM POH. Additionally, many avionics manufacturers can provide informative pilot operating guides upon request. Yaw damper. The yaw damper is a servo that moves the rudder in response to input from a gyroscope or accelerometer that detects yaw rate. The yaw damper minimizes motion above the vertical axis caused by turbulence. Yaw dampers on swept-wing airplanes provide another, more vital function of dampening Dutch roll characteristics. Occupants will feel a smoother ride, particularly if seated in the rear of the airplane, when the yaw damper is engaged. The yaw damper should be off for takeoff and landing. There may be additional restrictions against its use during single-engine operation. Most yaw dampers can be engaged independently of the autopilot. Alternator/generator. Alternator or generator paralleling circuitry matches the output of each engine's alternator/generator so that the electrical system load is shared equally between them. In the event of an alternator/generator failure, the inoperative unit can be isolated and the entire electrical system powered from the remaining one. Depending upon the electrical capacity of the alternator/generator, the pilot may need to reduce the electrical load, referred to as load shedding, when operating on a single unit. The AFM-POH will contain system description and limitations. Nose baggage compartment. Nose baggage compartments are common on multi-engine airplanes, and are even found in a few single-engine airplanes. There is nothing strange or exotic about a nose baggage compartment, and the usual guidance concerning observation of load limit applies. They are mentioned here in that pilots occasionally neglect to secure the latches properly, and therein lies the danger. When improperly secured, the door will open and the contents may be drawn out, usually into the propeller arc, and usually just after takeoff. Even when the nose baggage compartment is empty, airplanes have been lost when the pilot became distracted by the open door. Security of the nose baggage compartment latches and locks is a vital pre-flight item. Most airplanes will continue to fly with the nose baggage door open. There may be some buffeting from the disturbed airflow, and there will be an increase in noise. Pilots should never become so preoccupied with an open door of any kind that they fail to fly the airplane. Inspection of the compartment interior is also an important pre-flight item. More than one pilot has been surprised to find a supposedly empty compartment packed to capacity or loaded with ballast. The tow bars, engine inlet covers, windshield sunscreens, oil containers, spare chocks, and miscellaneous small hand tools that find their way into baggage compartments should be secured to prevent damage from shifting in flight. Anti-icing, de-icing. Anti-icing/de-icing equipment is frequently installed on multi-engine airplanes and consists of a combination of different systems. These may be classified as either anti-icing or de-icing, depending upon function. The presence of anti-icing and de-icing equipment, even though it may appear elaborate and complete, does not necessarily mean the airplane is approved for flight in icing conditions. The AFM-POH placards and even the manufacturer should be consulted for specific determination of approvals and limitations. Anti-icing equipment is provided to prevent ice from forming on certain protected surfaces. Anti-icing equipment includes heated pitot tubes, heated or non-icing static ports, and fuel vents, propeller blades with electrothermal boots or alcohol slingers, windshields with alcohol spray or electrical resistance heating, windshield defoggers, and heated stall warning lift detectors. On many turboprop engines, the lip surrounding the air intake is heated either electrically or with bleed air. In the absence of AFM-POH guidance to the contrary, anti-icing equipment is actuated prior to flight into known or suspected icing conditions. De-icing equipment is generally limited to pneumatic boots on wing and tail leading edges. De-icing equipment is installed to remove ice that has already formed on protected surfaces. Upon pilot actuation, the boots inflate with air from the pneumatic pumps to break off accumulated ice. After a few seconds of inflation, they are deflated back to their normal position with the assistance of a vacuum. The pilot monitors the buildup of ice and cycles the boots as directed in the AFM-POH. An ice light on the left engine nacelle allows the pilot to monitor wing ice accumulation at night. Other airframe equipment necessary for flight in icing conditions includes an alternate induction air source and an alternate static system source. Ice-tolerant antennas will also be installed. In the event of impact ice accumulating over normal engine air induction sources, carburetor heat, carbureted engines, or alternate air, fuel-injected engines should be selected. Ice buildup on normal induction sources can be detected by a loss of engine RPM with fixed-pitch propellers and a loss of manifold pressure with constant-speed propellers. On some fuel-injected engines, an alternate air source is automatically activated with blockage of the normal air source. An alternate static system provides an alternate source of static air for the pitot static system in the unlikely event that the primary static source becomes blocked. In non-pressurized airplanes, most alternate static sources are plumbed to the cabin. On pressurized airplanes, they are usually plumbed to a non-pressurized baggage compartment. The pilot must activate the alternate static source by opening a valve or a fitting in the cockpit. Upon activation, the airspeed indicator, altimeter, and the vertical speed indicator, VSI, will be affected and will read somewhat in error. A correction table is frequently provided in the AFM POH. Anti-icing/de-icing equipment only eliminates ice from the protected surfaces. Significant ice accumulations may form on unprotected areas, even with proper use of anti-ice and de-ice systems. Flight at high angles of attack, or even normal climb speeds, will permit significant ice accumulation on lower wing surfaces, which are unprotected. Many AFM POHs mandate minimum speeds to be maintained in icing conditions. Degradation of all flight characteristics and large performance losses can be expected with ice accumulations. Pilots should not rely on the stall warning devices for adequate stall warning with ice accumulations. Ice will accumulate unevenly on the airplane. It will add weight and drag, primarily drag, and decrease thrust and lift. Even wing shape affects ice accumulation. Thin airfoil sections are more prone to ice accumulation than thick, highly cambered sections. For this reason, certain surfaces, such as the horizontal stabilizer, are more prone to icing than the wing. With ice accumulations, landing approaches should be made with a minimum wing flap setting. Flap extension increases the angle of attack of the horizontal stabilizer, and with an added margin of airspeed. Sudden and large configuration and airspeed changes should be avoided. Unless otherwise recommended in the AFM POH, the autopilot should not be used in icing conditions. Continuous use of the autopilot will mask trim and handling changes that will occur with ice accumulation. Without this control feedback, the pilot may not be aware of ice accumulation building to hazardous levels. The autopilot will suddenly disconnect when it reaches design limits, and the pilot may find the airplane has assumed unsatisfactory handling characteristics. The installation of anti-ice/de-ice equipment on airplanes without AFM POH approval for flight into icing conditions is to facilitate escape when such conditions are inadvertently encountered. Even with AFM POH approval, the prudent pilot will avoid icing conditions to the maximum extent practicable and avoid extended flight in any icing conditions. No multi-engine airplane is approved for flight into severe icing conditions, and none are intended for indefinite flight in continuous icing conditions. End of Part 1 of Chapter 12. Chapter 12, Part 2 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. Airplane Flying Handbook by the FAA. Performance and Limitations. Discussions of performance and limitations requires the definition of several terms. Accelerate stop distance is the runway length required to accelerate to a specified speed, either VR or VLOF, as specified by the manufacturer, experience an engine failure, and bring the airplane to a complete stop. Accelerate go distance is the horizontal distance required to continue the takeoff and climb to 50 feet, assuming an engine failure at VR or VLOF as specified by the manufacturer. Climb gradient is a slope most frequently expressed in terms of altitude gain per 100 feet of horizontal distance, whereupon it is stated as a percentage. A 1.5% climb gradient is an altitude gain of 1.5 feet per 100 feet of horizontal travel. Climb gradient may also be expressed as a function of altitude gain per nautical mile, or as a ratio of the horizontal distance to the vertical distance, 50:1, for example. Unlike rate of climb, climb gradient is affected by wind. Climb gradient is improved with a headwind component and reduced with a tailwind component. Figure 12-5. The all-engine service ceiling of multi-engine airplanes is the highest altitude at which the airplane can maintain a steady rate of climb of 100 feet per minute with both engines operating. The airplane has reached its absolute ceiling when climb is no longer possible. The single-engine service ceiling is reached when the multi-engine airplane can no longer maintain a 50 feet per minute rate of climb with one engine inoperative, and its single-engine absolute ceiling when climb is no longer possible. The takeoff in a multi-engine airplane should be planned in sufficient detail so that the appropriate action is taken in the event of an engine failure. The pilot should be thoroughly familiar with the airplane's performance capabilities and limitations in order to make an informed takeoff decision as part of the pre-flight planning. That decision should be reviewed as the last item of the before takeoff checklist. In the event of an engine failure shortly after takeoff, the decision is basically one of continuing flight or landing, even off-airport. If single-engine climb performance is adequate for continued flight, and the airplane has been promptly and correctly configured, the climb after takeoff may be continued. If single-engine climb performance is such the climb is unlikely or impossible, a landing will have to be made in the most suitable area. To be avoided above all is attempting to continue flight when it is not within the airplane's performance capability to do so. Figure 12-6. Takeoff planning factors include weight and balance, airplane performance, both single and multi-engine, runway length, slope and contamination, terrain and obstacles in the area, weather conditions, and pilot proficiency. Most multi-engine airplanes have AFM POH performance charts, and the pilot should be highly proficient in their use. Prior to takeoff, the multi-engine pilot should ensure that the weight and balance limitations have been observed, the runway length is adequate, the normal flight path will clear obstacles and terrain, and that a definitive course of action has been planned in the event of an engine failure. The regulations do not specifically require that the runway length be equal to or greater than the accelerate stop distance. Most AFM POHs publish accelerate stop distances only as an advisory. It becomes a limitation only when published in the limitations section of the AFM POH. Experienced multi-engine pilots, however, recognize a safety margin of runway lengths in excess of the bare minimum required for normal takeoff. They will insist on runway lengths of at least accelerate stop distance as a matter of safety and good operating practice. The multi-engine pilot must keep in mind that the accelerate go distance, as long as it is, has only brought the airplane under ideal circumstances to a point a mere 50 feet above the takeoff elevation. To achieve even this meager climb, the pilot had to instantaneously recognize and react to an unanticipated engine failure, retract the landing gear, identify and feather the correct engine, all the while maintaining precise airspeed control and bank angle as the airspeed is nursed to VYSE. Assuming flawless airmanship thus far, the airplane has now arrived at a point little more than one wingspan above the terrain, assuming it was absolutely level and without obstructions. With, for the purpose of illustration, a net 150 feet per minute rate of climb at a 90-knot VYSE, it will take approximately 3 minutes to climb an additional 450 feet to reach 500 feet AGL. In doing so, the airplane will have traveled an additional 5 nautical miles beyond the original accelerate go distance, with a climb gradient of about 1.6%. A turn of any consequence, such as a return to the airport, will seriously degrade the already marginal climb performance. Not all multi-engine airplanes have published accelerate go distances in their AFM-POH, and fewer still publish climb gradients. When such information is published, the figures will have to be determined under ideal flight testing conditions. It is unlikely that this performance will be duplicated in service conditions. The point of the foregoing is to illustrate the marginal climb performance of a multi-engine airplane that suffers an engine failure shortly after takeoff, even under ideal conditions. The prudent multi-engine pilot should pick a point in the takeoff and climb sequence in advance. If an engine fails before this point, the takeoff should be rejected, even if airborne, for a landing on whatever runway or surface lies essentially ahead. If an engine fails after this point, the pilot should promptly execute the appropriate engine failure procedure and continue the climb, assuming the performance capability exists. As a general recommendation, if the landing gear has not been selected up, the takeoff should be rejected, even if airborne. As a practical matter for planning purposes, the option of continuing the takeoff probably does not exist unless the published single-engine rate of climb performance is at least 100 to 200 feet per minute. Thermal turbulence, wind gusts, engine and propeller wear, or poor technique in airspeed, bank angle, and rudder control can easily negate even a 200 feet per minute rate of climb. Weight and balance. The weight and balance concept is no different than that of a single-engine airplane. The actual execution, however, is almost invariably more complex due to a number of new loading areas, including nose and aft baggage compartments, nacelle lockers, main fuel tanks, auxiliary fuel tanks, nacelle fuel tanks, and numerous seating options in a variety of interior configurations. The flexibility in loading offered by the multi-engine airplane places a responsibility on the pilot to address weight and balance prior to each flight. The terms empty weight, licensed empty weight, standard empty weight, and basic empty weight, as they appear on manufacturers' original weight and balance documents, are sometimes confused by pilots. In 1975, the General Aviation Manufacturers Association, GAMA, adopted a standardized format for AFM-POHs. It was implemented by most manufacturers in model year 1976. Airplanes whose manufacturers conform to the GAMA standards utilize the following terminology for weight and balance. Standard empty weight plus optional equipment equals basic empty weight. Standard empty weight is the weight of the standard airplane, full hydraulic fluid, unusable fuel, and full oil. Optional equipment includes the weight of all equipment installed beyond standard. Basic empty weight is the standard empty weight plus optional equipment. Note that basic empty weight includes no usable fuel but full oil. Airplanes manufactured prior to the GAMA format generally utilize the following terminology for weight and balance, although the exact terms may vary somewhat. Empty weight plus unusable fuel equals standard empty weight. Standard empty weight plus optional equipment equal licensed empty weight. Empty weight is the weight of the standard airplane, full hydraulic fluid, and undrainable oil. Unusable fuel is the fuel remaining in the airplane not available to the engines. Standard empty weight is the empty weight plus unusable fuel. When optional equipment is added to the standard empty weight, the result is licensed empty weight. Licensed empty weight, therefore, includes the standard airplane, optional equipment, full hydraulic fluid, unusable fuel, and undrainable oil. The major difference between the two formats, GAMA and the old, is that basic empty weight includes full oil and licensed empty weight does not. Oil must always be added to any weight and balance utilizing a licensed empty weight. When the airplane is placed in service, amended weight and balance documents are prepared by appropriately rated maintenance personnel to reflect changes in installed equipment. The old weight and balance documents are customarily marked superseded and retained in the AFM-POH. Maintenance personnel are under no regulatory obligation to utilize the GAMA terminology, so weight and balance documents subsequent to the original may use a variety of terms. Pilots should use care when determining whether or not oil has to be added to the weight and balance calculations, or if it is already included in the figures provided. The multi-engine airplane is where most pilots encounter the term zero fuel weight for the first time. Not all multi-engine airplanes have a zero fuel weight limitation published in their AFM-POH, but many do. Zero fuel weight is simply the maximum allowable weight of the airplane and payload, assuming there is no usable fuel on board. The actual airplane is not devoid of fuel at the time of loading, of course. This is merely a calculation that assumes it was. If zero fuel weight limitation is published, then all weight in excess of that figure must consist of usable fuel. The purpose of a zero fuel weight is to limit load forces on the wing spars with heavy fuselage loads. Assume a hypothetical multi-engine airplane with the following weights and capacities. Basic empty weight, 3,200 pounds. Zero fuel weight, 4,400 pounds. Maximum takeoff weight, 5,200 pounds. Maximum usable fuel, 180 gallons. 1. Calculate the useful load. Maximum takeoff weight, 5,200 pounds, minus basic empty weight, 3,200 pounds, equals useful load, 2,000 pounds. The useful load is the maximum combination of usable fuel, passengers, baggage, and cargo that the airplane is capable of carrying. 2. Calculate the payload. Zero fuel weight, 4,400 pounds, minus basic empty weight, 3,200 pounds, equals payload, 1,200 pounds. The payload is the maximum combination of passengers, baggage, and cargo that the airplane is capable of carrying. A zero fuel weight, if published, is the limiting weight. 3. Calculate the fuel capacity at maximum payload, 1,200 pounds. Maximum takeoff weight, 5,200 pounds, minus zero fuel weight, 4,400 pounds, equals fuel allowed, 800 pounds. Assuming maximum payload, the only weight permitted in excess of the zero fuel weight must consist of usable fuel, in this case, 133.3 gallons. 4. Calculate the payload at maximum fuel capacity, 180 gallons. Basic empty weight, 3,200 pounds, plus maximum usable fuel, 1,080 pounds, equals weight with maximum fuel, 4,280 pounds. Maximum takeoff weight, 5,200 pounds, minus weight with maximum fuel, 4,280 pounds, equals payload allowed, 920 pounds. Assuming the maximum fuel, the payload is the difference between the weight of the fueled airplane and the maximum takeoff weight. Some multi-engine airplanes have a ramp weight, which is in excess of the maximum takeoff weight. The ramp weight is an allowance for fuel that would be burned during taxi and run-up, permitting a takeoff at full maximum takeoff weight. The airplane must weigh no more than a maximum takeoff weight at the beginning of the takeoff roll. A maximum landing weight is a limitation against landing at a weight in excess of the published value. This requires pre-flight planning of fuel burn to ensure that the airplane weight upon arrival at destination will be at or below the maximum landing weight. In the event of an emergency requiring an immediate landing, the pilot should recognize that the structural margins designed into the airplane are not fully available when overlanding weight. An overweight landing inspection may be advisable. The service manual or manufacturer should be consulted. Although the foregoing problems only deal with weight, the balance portion of weights and balance is equally vital. The flight characteristics of the multi-engine airplane will vary significantly with shifts in the center of gravity, CG, within the approved envelope. At forward CGs, the airplane will be more stable, with a slightly higher stalling speed, a slightly slower cruising speed, and favorable stall characteristics. At aft CGs, the airplane will be less stable, with a slightly lower stalling speed, a slightly faster cruising speed, and less desirable stall characteristics. Forward CG limits are usually determined in certification by elevator/stabulator authority in the landing roundout. Aft CG limits are determined by the minimum acceptable longitudinal stability. It is contrary to the airplane's operating limitations and the Code of Federal Regulations, CFR, to exceed any weight and balance parameter. Some multi-engine airplanes may require ballast to remain within CG limits under certain loading conditions. Several models require ballast in the aft baggage compartment with only a student and instructor on board to avoid exceeding the forward CG limit. When passengers are seated in the aftmost seats of some models, ballast or baggage may be required in the nose baggage compartment to avoid exceeding the aft CG limit. The pilot must direct the seating of the passengers and placement of baggage and cargo to achieve a center of gravity within the approved envelope. Most multi-engine airplanes have general loading recommendations in the weight and balance section of the AFM POH. When ballast is added, it must be securely tied down, and it must not exceed the maximum allowable floor loading. Some airplanes make use of a special weight and balance plotter. It consists of several movable parts that can be adjusted over a plotting board on which the CG envelope is printed. The reverse side of the typical plotter contains general loading recommendations for the particular airplane. A pencil line plot can be made directly on the CG envelope imprinted on the working side of the plotting board. This plot can be easily erased and recalculated anew for each flight. This plotter is to be used only for the make and model airplane for which it was designed. Ground operation. Good habits learned with single-engine airplanes are directly applicable to multi-engine airplanes for pre-flight and engine start. Upon placing the airplane in motion to taxi, the new multi-engine pilot will notice several differences, however. The most obvious is the increased wingspan and the need for even greater vigilance while taxiing in close quarters. Ground handling may seem somewhat ponderous, and the multi-engine airplane will not be as nimble as the typical 2- or 4-place single-engine airplane. As always, use care not to ride the brakes by keeping the engine power to a minimum. One ground handling advantage of the multi-engine airplane over single-engine airplanes is the differential power capability. Turning with an assist from differential power minimizes the need for brakes during turns and the turning radius. The pilot should be aware, however, that making a sharp turn assisted by brakes and differential power can cause the airplane to pivot about a stationary inboard wheel and landing gear. This is abuse for which the airplane was not designed and should be guarded against. Unless otherwise directed by the AFM POH, all ground operations should be conducted with the cowl flaps fully open. The use of strobe lights is normally deferred until taxiing onto the active runway. Normal and crosswind takeoff and climb. With the before takeoff checklist complete and air traffic control ATC clearance received, the airplane should be taxied into position on the runway centerline. If departing from an airport without an operating control tower, a careful check for approaching aircraft should be made, along with a radio advisory on the appropriate frequency. Sharp turns onto the runway, combined with a rolling takeoff, are not a good operating practice and may be prohibited by the AFM POH due to the possibility of unporting a fuel tank pickup. The takeoff itself may be prohibited by the AFM-POH under any circumstances below certain fuel levels. The flight controls should be positioned for a crosswind if present. Exterior lights, such as landing and taxi lights and wingtip strobes, should be illuminated immediately prior to initiating the takeoff roll, day or night. If holding in takeoff position for any length of time, particularly at night, the pilot should activate all exterior lights upon taxiing into position. Takeoff power should be set as recommended in the AFM-POH. With normally aspirated, non-turbocharged engines, this will be full throttle. Full throttle is also used in most turbocharged engines. There are some turbocharged engines, however, that require the pilot to set a specific power setting, usually just below the red line manifold pressure. This yields takeoff power with less than full throttle travel. Turbocharged engines often require special consideration. Throttle motion with turbocharged engines should be exceptionally smooth and deliberate. It is acceptable, and may even be desirable, to hold the airplane in position with brakes as the throttles are advanced. Brake release customarily occurs after significant boost from the turbocharger is established. This prevents wasting runway with slow, partial throttle acceleration as the engine power is increased. If runway length or obstacle clearance is critical, full power should be set before brake release, as specified in the performance charts. As takeoff power is established, initial attention should be divided between tracking the runway centerline and monitoring the engine gauges. Many novice multi-engine pilots tend to fixate on the airspeed indicator just as soon as the airplane begins its takeoff roll. Instead, the pilot should confirm that both engines are developing full rated manifold pressure and RPM, and that the fuel flows, fuel pressures, exhaust gas temperatures, EGTs, and oil pressures are matched in their normal ranges. A directed, purposeful scan of the engine gauges can be accomplished well before the airplane approaches rotation speed. If a crosswind is present, the aileron displacement in the direction of the crosswind may be reduced as the airplane accelerates. The elevator/stabulator control should be held neutral throughout. Full rated takeoff power should be used for every takeoff. Partial power takeoffs are not recommended. There is no evidence to suggest that the life of modern reciprocating engines is prolonged by partial power takeoffs. Paradoxically, excessive heat and engine wear can occur with partial power, as the fuel metering system will fail to deliver the slightly overrich mixture vital for engine cooling during takeoff. There are several key airspeeds to be noted during the takeoff and climb sequence in any twin. The first speed to consider is VMC. If an engine fails below VMC while the airplane is on the ground, the takeoff must be rejected. Directional control can only be maintained by promptly closing both throttles and using the rudder and brakes as required. If an engine fails below VMC while airborne, directional control is not possible with the remaining engine producing takeoff power. On takeoffs, therefore, the airplane should never be airborne before the airspeed reaches and exceeds VMC. Pilots should use the manufacturer's recommended rotation speed, VR, or liftoff speed, VLOF. If no such speeds are published, a minimum of VMC plus 5 knots should be used for VR. The rotation to a takeoff pitch attitude is done smoothly. With a crosswind, the pilot should ensure that the landing gear does not momentarily touch the runway after the airplane has lifted off, as a side drift will be present. The rotation may be accomplished more positively and/or at a higher speed under these conditions. However, the pilot should keep in mind that the AFM-POH performance figures for accelerate stop distance, takeoff round roll, and distance to clear an obstacle were calculated at the recommended VR and/or VLOF speed. After liftoff, The next consideration is to gain altitude as rapidly as possible. After leaving the ground, altitude gain is more important than achieving an excess of airspeed. Experience has shown that excessive speed cannot be effectively converted into altitude in the event of an engine failure. Altitude gives the pilot time to think and react. Therefore, the airplane should be allowed to accelerate in a shallow climb to attain VY, the best all-engine rate of climb speed. VY should then be maintained until a safe single-engine maneuvering altitude, considering terrain and obstructions, is achieved. To assist the pilot in takeoff and initial climb profile, some AFM POHs give a 50-foot or 50-foot barrier speed to use as a target during rotation, liftoff, and acceleration to VY. Landing gear retraction should normally occur after a positive rate of climb is established. Some AFM POHs direct the pilot to apply the wheel brakes momentarily after liftoff to stop wheel rotation prior to landing gear retraction. If flaps were extended for takeoff, they should be retracted as recommended in the AFM POH. Once a safe single-engine maneuvering altitude has been reached, typically a minimum of 400 to 500 feet AGL, the transition to en route climb speed should be made. This speed is higher than VY and is usually maintained to cruising altitude. En route climb speed gives better visibility, increased engine cooling, and a higher ground speed. Takeoff power can be reduced if desired as the transition to en route climb speed is made. Some airplanes have a climb power setting published in the AFM POH as a recommendation, or sometimes as a limitation, which should be set for en route climb. If there is no climb power setting published, it is customary, but not a requirement, to reduce manifold pressure and RPM somewhat for en route climb. Propellers are usually synchronized after the first power reduction and the yaw damper, if installed, engaged. The AFM POH may also recommend leaning the mixture during climb. The climb checklist should be accomplished as traffic and workload allow. Figure 12-7. Level off and cruise. Upon leveling off at cruising altitude, the pilot should allow the airplane to accelerate at climb power until cruising airspeed is achieved. Then cruise power and RPM should be set. To extract the maximum cruise performance from any airplane, the power setting tables provided by the manufacturer should be closely followed. If the cylinder head and oil temperatures are within their normal ranges, the cowl flaps may be closed. When the engine temperatures have stabilized, the mixtures may be leaned per AFM POH recommendations. The remainder of the cruise checklist should be completed by this point. Fuel management in multi-engine airplanes is often more complex than in single-engine airplanes. Depending upon system design, the pilot may need to select between main tanks and auxiliary tanks, or even employ fuel transfer from one tank to another. In complex fuel systems, limitations are often found restricting the use of some tanks to level flight only, or requiring a reserve of fuel in the main tanks for descent and landing. Electric fuel pump operation can vary widely among different models also, particularly during tank switching or fuel transfer. Some fuel pumps are to be on for takeoff and landing. Others are to be off. There is simply no substitute for thorough systems and AFM POH knowledge when operating complex aircraft. End of Section 2 of Chapter 12.
Chapter 12, Part 3 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jairus Amar. Airplane Flying Handbook by the FAA. Normal approach and landing. Given the higher cruising speed and frequently altitude of multi-engine airplanes over most single-engine airplanes, the descent must be planned in advance. A hurried, last-minute descent with power at or near idle is inefficient and can cause excessive engine cooling. It may also lead to passenger discomfort, particularly if the airplane is unpressurized. As a rule of thumb, if terrain and passenger conditions permit, a maximum of a 500 FPM rate of descent should be planned. Pressurized airplanes can plan for higher descent rates if desired. In a descent, some airplanes require a minimum EGT, or may have a minimum power setting or cylinder head temperature to observe. In any case, combinations of very low manifold pressure and high RPM settings are strongly discouraged by engine manufacturers. If higher descent rates are necessary, the pilot should consider extending partial flaps or lowering the landing gear before retarding the power excessively. The descent checklist should be initiated upon leaving cruising altitude and completed before arrival in the terminal area. Upon arrival in the terminal area, pilots are encouraged to turn on their landing and recognition lights when operating below 10,000 feet, day or night, and especially when operating within 10 miles of any airport or in conditions of reduced visibility. The traffic pattern and approach are typically flown at somewhat higher indicated airspeeds in a multi-engine airplane contrasted to most single-engine airplanes. The pilot may allow for this through an early start on the before landing checklist. This provides time for proper planning, spacing, and thinking well ahead of the airplane. Many multi-engine airplanes have partial flap extension speeds above VFE, and partial flaps can be deployed prior to traffic pattern entry. Normally, the landing gear should be selected and confirmed down when abeam the intended point of landing as the downwind leg is flown. See Figure 12-8. The Federal Aviation Administration, FAA, recommends a stabilized approach concept. To the greatest extent practical, on final approach and within 500 feet AGL, the airplane should be on speed, in trim, configured for landing, tracking the extended centerline of the runway, and established in a constant angle of descent towards an aim point in the touchdown zone. Absent unusual flight conditions, only minor correction will be required to maintain this approach to the roundout and touchdown. The final approach should be made with power and the speed recommended by the manufacturer. If a recommended speed is not furnished, the speed should be no slower than the single-engine best rate of climb speed, VYSE, until short final with a landing assured, but in no case less than critical engine out minimum control speed, VMC. Some multi-engine pilots prefer to delay full flap extension to short final with a landing assured. This is an acceptable technique with appropriate experience and familiarity with the airplane. In the roundout for landing, residual power is gradually reduced to idle. With the higher wing loading of multi-engine airplanes and with the drag from two windmilling propellers, there will be minimal float. Full stall landings are generally undesirable in twins. The airplane should be held off as with a high-performance single-engine model, allowing touchdown of the main wheels prior to a full stall. Under favorable wind and runway conditions, the nose wheel can be held off for best aerodynamic braking. Even as the nose wheel is gently lowered to the runway centerline, continued elevator back pressure will greatly assist the wheel brakes in stopping the airplane. If runway length is critical, or with a strong crosswind, or if the surface is contaminated with water, ice, or snow, it is undesirable to rely solely on aerodynamic braking after touchdown. The full weight of the airplane should be placed on the wheels as soon as practicable. The wheel brakes will be more effective than aerodynamic braking alone in decelerating the airplane. Once on the ground, elevator back pressure should be used to place additional weight on the main wheels and to add additional drag. When necessary, wing flap retraction will also add additional weight to the wheels and improve braking effectivity. Flap retraction during the landing rollout is discouraged, however, unless there is a clear operational need. It should not be accomplished as routine with each landing. Some multi-engine airplanes, particularly those of the cabin class variety, can be flown through the round out and touch down with a small amount of power. This is an acceptable technique to prevent high sink rates and to cushion the touchdown. The pilot should keep in mind, however, that the primary purpose in landing is to get the airplane down and stopped. This technique should only be attempted when there is a generous margin of runway length. As propeller blast flows directly over the wings, lift as well as thrust is produced. The pilot should taxi clear of the runway as soon as speed and safety permit, and then accomplish the after-landing checklist. Ordinarily, no attempt should be made to retract the wing flaps or perform other checklist duties until the airplane has been brought to a halt when clear of the active runway. Exceptions to this would be the rare operational needs discussed above, to relieve the weight from the wings and place it on the wheels. In these cases, AFM/POH guidance should be followed. The pilot should not indiscriminately reach out for any switch or control on landing rollout. An inadvertent landing gear retraction while meaning to retract the wing flaps may result. Crosswind approach and landing. The multi-engine airplane is often easier to land in a crosswind than a single-engine airplane due to its higher approach and landing speed. In any event, the principles are no different between singles and twins. Prior to touchdown, the longitudinal axis must be aligned with the runway centerline to avoid landing gear side loads. The two primary methods, crab and wing low, are typically used in conjunction with each other. As soon as the airplane rolls out into final approach, the crab angle to track the extended runway centerline is established. This is coordinated flight with adjustments to heading to compensate for wind drift either left or right. Prior to touchdown, the transition to a side slip is made with the upwind wing lowered and the opposite rudder applied to prevent a turn. The airplane touches down on the landing gear of the upwind wing first, followed by that of the downwind wing, and then the nose gear. Follow through with the flight controls involves an increasing application of aileron into the wind until full control deflection is reached. The point at which the transition from the crab to the side slip is made is dependent upon pilot familiarity with the airplane and experience. With high skill and experience levels, the transition can be made during the round out just before touchdown. With lesser skill and experience levels, the transition is made at increasing distances from the runway. Some multi-engine airplanes, as some single-engine airplanes, have AFM/POH limitations against slips in excess of a certain time period. 30 seconds, for example. This is to prevent engine power loss from fuel starvation as the fuel in the tank of the lowered wing flows towards the wingtip, away from the fuel pickup point. This time limit must be observed if the wing low method is utilized. Some multi-engine pilots prefer to use differential power to assist in crosswind landings. The asymmetrical thrust produces a yawing moment, little different from that produced by the rudder. When the upwind wing is lowered, power on the upwind engine is increased to prevent the airplane from turning. This alternate technique is completely acceptable, but most pilots feel they can react to changing wind conditions quicker with rudder and aileron than throttle movement. This is especially true with turbocharged engines, where the throttle response may lag momentarily. The differential power technique should be practiced with an instructor familiar with it before being attempted alone. Short field takeoff and climb. The short field takeoff and climb differs from the normal takeoff and climb in the airspeeds and initial climb profile. Some AFM/POHs give separate short field takeoff procedures and performance charts that recommend specific flap settings and airspeeds. Other AFM/POHs do not provide separate short field procedures. In the absence of such specific procedures, the airplane should be operated only as recommended in the AFM/POH. No operation should be conducted contrary to the recommendations in the AFM/POH. On short field takeoffs in general, just after rotation and liftoff, the airplane should be allowed to accelerate to Vx, making the initial climb over obstacles at Vx and transitioning to Vy as obstacles are cleared. See Figures 12-9. When partial flaps are recommended for short field takeoffs, many light twins have a strong tendency to become airborne prior to VMC plus 5 knots. Attempting to prevent premature liftoff with forward elevator pressure results in wheelbarrowing. To prevent this, allow the airplane to become airborne, but only a few inches above the runway. The pilot should be prepared to promptly abort the takeoff and land in the event of engine failure on takeoff with landing gear and flaps extended at airspeeds below Vx. Engine failure on takeoff, particularly with obstructions, is compounded by the low airspeeds and steep climb attitudes utilized in short field takeoffs. Vx and Vxse are often perilously close to Vmc, leaving scant margin for error in the event of engine failure as Vxse is assumed. If flaps were used for takeoff, the engine failure situation becomes even more critical due to the additional drag incurred. If Vx is less than 5 knots higher than Vmc, give strong consideration to reducing useful load or using another runway in order to increase takeoff margins, so that a short field technique will not be required. Short field approach and landing. The primary elements of a short field approach and landing do not differ significantly from a normal approach and landing. Many manufacturers do not publish short field landing techniques or performance charts in the AFM/POH. In the absence of specific short field approach and landing procedures, the airplane should be operated as recommended in the AFM/POH. No operations should be conducted contrary to the AFM/POH recommendations. The emphasis in a short field approach is on configuration, full flaps, a stabilized approach with a constant angle of descent, and precise airspeed control. As part of a short field approach and landing procedure, some AFM/POHs recommend a slightly slower than normal approach airspeed. If no such slower speed is published, use the AFM/POH recommended normal approach speed. Full flaps are used to provide the steepest approach angle. If obstacles are present, the approach should be planned so that no drastic power reductions are required after they are cleared. The power should be smoothly reduced to idle in the roundout prior to touchdown. Pilots should keep in mind that the propeller blast blows over the wings, providing some lift in addition to thrust. Significantly reducing power just after obstacle clearance usually results in a sudden high sink rate that may lead to hard landing. After the short field touchdown, maximum stopping effort is achieved by retracting the wing flaps, adding back pressure to the elevator/stabilator, and applying heavy braking. However, if the runway length permits, the wing flaps should be left in the extended position until the airplane has been stopped clear of the runway. There is always a significant risk of retracting the landing gear instead of the wing flaps when flap retraction is attempted on the landing rollout. Landing conditions that involve either a short field, high winds, or strong crosswinds are just about the only situations where flap retraction on the landing rollout should be considered. When there is an operational need to retract the flaps just after touchdown, it must be done deliberately, with the flap handle positively identified before it is moved. Go around. When the decision to go around is made, the throttles should be advanced to takeoff power. With adequate airspeed, the airplane should be placed in a climb pitch attitude. These actions, which are accomplished simultaneously, will arrest the sink rate and place the airplane in the proper attitude for transition to a climb. The initial target airspeed will be Vy or Vx if obstructions are present. With sufficient airspeed, the flaps should be retracted from full to an intermediate position, and the landing gear retracted when there is a positive rate of climb and no chance of runway contact. The remaining flaps should then be retracted. See Figure 12-10. If the go-around was initiated due to conflicting traffic on the ground or aloft, the pilot should maneuver to the side so as to keep the conflicting traffic in sight. This may involve a shallow bank turn to offset and then parallel the runway/landing area. If the airplane was in trim for the landing approach when the go-around was commenced, it will soon require a great deal of forward elevator/stabilator pressure as the airplane accelerates away in a climb. The pilot should apply appropriate forward pressure to maintain the desired pitch attitude. Trim should be commenced immediately. The balked landing checklist should be reviewed as workload permits. Flaps should be retracted before the landing gear for two reasons. First, on most airplanes, full flaps produce more drag than the extended landing gear. Secondly, the airplane will tend to settle somewhat with flap retractions, and the landing gear should be down in the event of an inadvertent momentary touchdown. Many multi-engine airplanes have a landing gear retraction speed significantly less than the extension speed. Care should be exercised during the go-around not to exceed the retraction speed. If the pilot desires to return for a landing, it is essential to reaccomplish the entire before landing checklist. An interruption to a pilot's habit patterns, such as a go-around, is a classic scenario for a subsequent gear-up landing. The preceding discussion of go-arounds assumes that the maneuver was initiated from normal approach speeds or faster. If the go-around was initiated from a low airspeed, the initial pitch-up to a climb attitude must be tempered with the necessity of maintaining adequate flying speed throughout the maneuver. Examples of where this applies include go-arounds initiated from the landing roundout or recovery from a bad bounce, as well as a go-around initiated due to an inadvertent approach to a stall. The first priority is always to maintain control and obtain adequate flying speed. A few moments of level or near level flight may be required as the airplane accelerates to climb speed. Rejected takeoff. A takeoff can be rejected for the same reasons a takeoff in a single-engine airplane would be rejected. Once the decision to reject a takeoff is made, the pilot should promptly close both throttles and maintain directional control with the rudder, nose wheel steering, and brakes. Aggressive use of rudder, nose wheel steering, and brakes may be required to keep the airplane on the runway, particularly if an engine failure is not immediately recognized and accompanied by prompt closure of both throttles. However, the primary objective is not necessarily to stop the airplane in the shortest distance, but to maintain control of the airplane as it decelerates. In some situations, it may be preferable to continue into the overrun area under control, rather than risk directional control loss, landing gear collapse, or tire/brake failure in an attempt to stop the airplane in the shortest possible distance. Engine failure after liftoff. A takeoff or go-around is the most critical time to suffer an engine failure. The airplane will be slow, close to the ground, and may even have landing gear and flaps extended. Altitude and time will be minimal. Until feathered, the propeller of the failed engine will be windmilling, producing a great deal of drag and yawing tendency. Airplane climb performance will be marginal or even non-existent, and obstructions may lie ahead. Add the element of surprise, and the need for a plan of action before every takeoff is obvious. With loss of an engine, it is paramount to maintain airplane control and comply with the manufacturer's recommended emergency procedures. Complete failure of one engine shortly after takeoff can be broadly categorized into one of three following scenarios. 1. Landing gear down. See Figure 12-11. If the engine failure occurs prior to selecting the landing gear to the up position, close both throttles and land on the remaining runway or overrun. Depending upon how quickly the pilot reacts to the sudden yaw, the airplane may run off the side of the runway by the time action is taken. There are really no other practical options. As discussed earlier, the chances of maintaining directional control while retracting the flaps, if extended, landing gear, feathering the propeller, and accelerating are minimal. On some airplanes with a single engine-driven hydraulic pump, failure of that engine means the only way to raise the landing gear is to allow the engine to windmill, or to use a hand pump. This is not a viable alternative during takeoff. 2. Landing gear control selected up, single engine climb performance inadequate. See Figure 12-12. When operating near or above the single engine ceiling and an engine failure is experienced shortly after liftoff, a landing must be accomplished on whatever essentially lies ahead. There is also the option of continuing ahead in a descent as V, Y, SE with the remaining engine producing power, as long as the pilot is not tempted to remain airborne beyond the airplane's performance capability. Remaining airborne, bleeding off airspeed in a futile attempt to maintain altitude is almost invariably fatal. Landing under control is paramount. The greatest hazard in a single-engine takeoff is attempting to fly when it is not in the performance capability of the airplane to do so. An accident is inevitable. Analysis of engine failures on takeoff reveals a very high success rate of off-airport engine inoperative landings when the airplane is landed under control. Analysis also reveals a very high fatality rate in stall-spin accidents when the pilot attempts flight beyond the performance capability of the airplane. As mentioned previously, if the airplane's landing gear retraction mechanism is dependent upon hydraulic pressure from a certain engine-driven pump, failure of that engine can mean a loss of hundreds of feet of altitude, as the pilot either windmills the engine to provide hydraulic pressure to raise the gear, or raises it manually with a backup pump. 3. Landing gear control selected up, single engine climb performance adequate. See Figure 12-13. If the single engine rate of climb is adequate, the procedures for continued flight should be followed. There are 4 areas of concern: control, configuration, climb, and checklist. Control. The first consideration following engine failure during takeoff is control of the airplane. Upon detecting an engine failure, aileron should be used to bank the airplane and rudder pressure applied, aggressively if necessary, to counteract the yaw and roll from asymmetrical thrust. The control forces, particularly on the rudder, may be high. The pitch attitude for VYSE will have to be lowered from that of VY. At least 5 degrees of bank should be used, if necessary, to stop the yaw and maintain directional control. This initial bank input is held only momentarily, just long enough to establish or ensure directional control. Climb performance suffers when bank angles exceed approximately 2 or 3 degrees, but obtaining and maintaining VYSE and directional control are paramount. Trim should be adjusted to lower the control forces. Configuration. The memory items from the engine failure after takeoff checklist, see Figure 12-14, should be promptly executed to configure the airplane for climb. The specific procedures to follow will be found in the AFM/POH and checklist for the particular airplane. Most will direct the pilot to assume VYSE, set takeoff power, retract the flaps and landing gear, identify, verify, and feather the failed engine. On some airplanes, the landing gear is to be retracted before the flaps. The identify step is for the pilot to initially identify the failed engine. Confirmation on the engine gauges may or may not be possible, depending upon the failure mode. Identification should be primarily through the control inputs required to maintain straight flight, not the engine gauges. The verify step directs the pilot to retard the throttle of the engine thought to have failed. No change in performance when the suspected throttle is retarded is verification that the correct engine has been identified as failed. The corresponding propeller control should be brought fully aft to feather the engine. Climb. As soon as directional control is established and the airplane configured for climb, the bank angle should be reduced to that producing best climb performance. Without specific guidance for zero side slip, a bank of 2 degrees and 1/3 to 1/2 ball deflection on the slip/skid indicator is suggested. VYSE is maintained with pitch control. As turning flight reduces climb performance, climb should be made straight ahead, or with the shallow turns to avoid obstacles, to an altitude of at least 400 feet AGL, before attempting a return to the airport. Checklist. Having accomplished the memory items from the engine failure after takeoff checklist, the printed copy should be reviewed as time permits. The securing failed engine checklist, see Figure 12-15, should then be accomplished. Unless the pilot suspects an engine fire, the remaining items should be accomplished deliberately and without undue haste. Airplane control should never be sacrificed to execute the remaining checklists. The priority items have already been accomplished from memory. Other than closing the cowl flap of the failed engine, none of these items, if left undone, adversely affects airplane climb performance. There is a distinct possibility of actuating an incorrect switch or control if the procedure is rushed. The pilot should concentrate on flying the airplane and extracting maximum performance. If ATC facilities are available, an emergency should be declared. The memory items in the engine failure after takeoff checklist may be redundant with the airplane's existing configuration. For example, in the third takeoff scenario, the gear and flaps were assumed to already be retracted, yet the memory items include gear and flaps. This is not an oversight. The purpose of the memory items is to either initiate the appropriate action or to confirm that a condition exists. Action on each item may not be required in all cases. The memory items also apply to more than one circumstance. In an engine failure from a go-around, for example, the landing gear and flaps would likely be extended when the failure occurred. The three preceding takeoff scenarios all include the landing gear as a key element in the decision to land or continue. With the landing gear selector in the down position, for example, continued takeoff and climb is not recommended. This situation, however, is not justification to retract the landing gear the moment the airplane lifts off the surface on takeoff as a normal procedure. The landing gear should remain selected down as long as there is usable runway or overrun available to land on. The use of wing flaps for takeoff virtually eliminates the likelihood of a single engine climb until the flaps are retracted. There are two time-tested memory aids the pilot may find useful in dealing with engine out scenarios. The first, dead foot, dead engine, is used to assist in identifying the failed engine. Depending on the failure mode, the pilot won't be able to consistently identify the failed engine in a timely manner from the engine gauges. In maintaining directional control, however, rudder pressure will be exerted on the side, left or right, of the airplane with the operating engine. Thus, the dead foot is on the same side as the dead engine. Variations on this saying include idle foot, idle engine, and working foot, working engine. The second memory aid has to do with climb performance. The phrase, raise the dead, is a reminder that the best climb performance is obtained with a very shallow bank, about 2 degrees toward the operating engine. Therefore, the inoperative, or dead engine, should be raised with a very slight bank. Not all engine power losses are complete failures. Sometimes the failure mode is such that partial power may be available. If there is a performance loss when the throttle of the affected engine is retarded, the pilot should consider allowing it to run until altitude and airspeed permit safe single-engine flight, if this can be done without compromising safety. Attempts to save a malfunctioning engine can lead to a loss of the entire airplane. End of Chapter 12, Part 3. Recording by Jairus Amar.
Chapter 12, Part 4 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook by the FAA. Engine failure during flight. Engine failures well above the ground are handled differently than those occurring at lower speeds and altitudes. Cruise airspeed allows better airplane control, and altitude may permit time for a possible diagnosis and remedy of the failure. Maintaining airplane control, however, is still paramount. Airplanes have been lost at altitude due to an apparent fixation on the engine problem to the detriment of flying the airplane. Not all engine failures or malfunctions are catastrophic in nature. Catastrophic meaning a major mechanical failure that damages the engine and precludes further engine operation. Many cases of power loss are related to fuel starvation, where restoration of power may be made with the selection of another tank. An orderly inventory of gauges and switches may reveal the problem. Carburetor heat or alternate air can be selected. The affected engine may run smoothly on just one magneto or at a lower power setting. Altering mixture may help. If fuel vapor formation is suspected, fuel boost pump operation may be used to eliminate flow and pressure fluctuations. Although it is a natural desire among pilots to save an ailing engine, with a precautionary shutdown, the engine should be left running if there is any doubt as to needing it for further safe flight. Catastrophic failure, accompanied by heavy vibration, smoke, blistering paint, or large trails of oil, on the other hand, indicate a critical situation. The affected engine should be feathered and the securing failed engine checklist completed. The pilot should divert to the nearest suitable airport and declare an emergency with ATC for priority handling. Fuel cross-feed is a method of getting fuel from a tank on one side of the airplane to an operating engine on the other. Cross-feed is used for extended single-engine operation. If a suitable airport is close at hand, there is no need to consider cross-feed. If prolonged flight on a single engine is inevitable due to airport non-availability, then cross-feed allows use of fuel that would otherwise be unavailable to the operating engine. It also permits the pilot to balance the fuel consumption to avoid an out-of-balance wing heaviness. AFM/POH procedures for cross-feed vary widely. Thorough fuel system knowledge is essential if cross-feed is to be conducted. Fuel selector positions and fuel boost pump usage for cross-feed differ greatly among multi-engine airplanes. Prior to landing, cross-feed should be terminated and the operating engine returned to its main tank fuel supply. If the airplane is above its single-engine absolute ceiling at the time of engine failure, it will slowly lose altitude. The pilot should maintain VYSE to minimize the rate of altitude loss. This drift-down rate will be greatest immediately following the failure and will decrease as the single-engine ceiling is approached. Due to the performance variations caused by engine and propeller wear, turbulence, and pilot technique, the airplane may not maintain altitude even at its published single-engine ceiling. Any further rate of sink, however, would likely be modest. An engine failure in a descent or other low-power setting can be deceiving. The dramatic yaw and performance loss will be absent. At very low power settings, the pilot may not even be aware of a failure. If a failure is suspected, the pilot should advance both engine mixtures, propellers, and throttles significantly to the takeoff settings if necessary to correctly identify the failed engine. The power on the operative engine can always be reduced later. Engine inoperative approach and landing. The approach and landing with one engine inoperative is essentially the same as a two-engine approach and landing. The traffic pattern should be flown at similar altitudes, airspeeds, and key positions as a two-engine approach. The differences will be the reduced power available and the fact that the remaining thrust is asymmetrical. A higher than normal power setting will be necessary on the operative engine. With adequate airspeed and performance, the landing gear can still be extended on the downwind leg, in which case it should be confirmed down, no later than abeam the intended point of landing. Performance permitting, initial extension of wing flaps, 10 degrees typically, and descent from pattern altitude can also be initiated on the downwind leg. The airspeed should be no lower than VYSE. The direction of the traffic pattern, and therefore the turns, is of no consequence as far as airplane controllability and performance are concerned. It is perfectly acceptable to make turns toward the failed engine. On the base leg, if performance is adequate, the flaps may be extended to an intermediate setting, 25 degrees typically. If the performance is inadequate, as measured by decay in airspeed or high sink rate, delay further flap extension until closer to the runway. VYSE is still the minimum airspeed to maintain. On final approach, a normal 3-degree glide path to a landing is desirable. VASI or other vertical path lighting aids should be utilized if available. Slightly steeper approaches may be acceptable. However, a long, flat, low approach should be avoided. Large, sudden power applications or reductions should be avoided. Maintain VYSE until the landing is assured, then slow to 1.3 VSO or the AFM/POH recommended speed. The final flap setting may be delayed until the landing is assured, or the airplane may be landed with partial flaps. The airplane should remain in trim throughout. The pilot must be prepared, however, for a rudder trim change as the power of the operating engine is reduced to idle in the roundout just prior to touchdown. With drag from only one windmilling propeller, the airplane will tend to float more than on a two-engine approach. Precise airspeed control, therefore, is essential, especially when landing on a short, wet, or slippery surface. Some pilots favor resetting the rudder trim to neutral on final and compensating for yaw by holding rudder pressure for the remainder of the approach. This eliminates the rudder trim change close to the ground as the throttle is closed during the roundout for landing. This technique eliminates the need for groping for the rudder trim and manipulating it to neutral during final approach, which many pilots find to be highly distracting. AFM/POH recommendations or personal preference should be used. Single-engine go-arounds must be avoided. As a practical matter in single-engine approaches, once the airplane is on final approach with the landing gear and flaps extended, it is committed to land. If not on the intended runway, then on another runway, a taxiway, or grassy infield. The light twin does not have the performance to climb on one engine with landing gear and flaps extended. Considerable altitude will be lost while maintaining VYSE and retracting landing gear and flaps. Losses of 500 feet or more are not unusual. If the landing gear has been lowered with an alternate means of extension, retraction may not be possible, virtually negating any climb capability. Engine inoperative flight principles. Best single-engine climb performance is obtained at VYSE with maximum available power and minimum drag. After the flaps and landing gear have been retracted and the propeller of the failed engine feathered, a key element in best climb performance is minimizing side slip. With the single-engine airplane or a multi-engine airplane with both engines operative, side slip is eliminated when the ball of the turn and bank instrument is centered. This is a condition of zero side slip, and the airplane is presenting its smallest possible profile to the relative wind. As a result, drag is at its minimum. Pilots know this as coordinated flight. In a multi-engine airplane with an inoperative engine, the center ball is no longer the indicator of zero side slip due to asymmetrical thrust. In fact, there is no instrument at all that will directly tell the pilot the flight conditions for zero side slip. In the absence of a yaw string, minimizing side slip is a matter of placing the airplane at a predetermined bank angle and ball position. The AFM/POH performance charts for single-engine flight were determined at zero side slip. If this performance is even to be approximated, the zero side slip technique must be utilized. There are two different control inputs that can be used to counteract the asymmetrical thrust of a failed engine. One, yaw from the rudder, and two, the horizontal component of lift that results from bank with the ailerons. Used individually, neither is correct. Used together in the proper combination, zero side slip and best climb performance are achieved. 3 different scenarios of airplane control inputs are presented below. Neither of the first 2 is correct. They are presented to illustrate the reasons for the zero side slip approach to best climb performance. 1. Engine inoperative flight with the wings level and ball centered requires large rudder inputs towards the operative engine. See Figure 12-16. The result is a moderate side slip towards the inoperative engine. Climb performance will be reduced by the moderate side slip. With wings level, VMC will be significantly higher than published, as there is no horizontal component of lift available to help the rudder combat asymmetrical thrust. 2. Engine inoperative flight using ailerons alone requires an 8 to 10 degree bank angle towards the operative engine. See Figure 12-17. This assumes no rudder input. The ball will be displaced well towards the operative engine. The result is a large side slip towards the operative engine. Climb performance will be greatly reduced by the large side slip. 3. Rudder and ailerons used together in proper combination will result in a bank approximately 2 degrees towards the operative engine. The ball will be displaced approximately 1/3 to 1/2 towards the operative engine. The result is 0 side slip and maximum climb performance. See Figure 12-18. Any attitude other than 0 side slip increases drag, decreasing performance. VMC, under these circumstances, will be higher than published, as less than 5 degree bank certification limit is employed. The precise condition of 0 side slip, bank angle, and ball position varies slightly from model to model and with available power and airspeed. If the airplane is not equipped with counter-rotating propellers, it will also vary slightly with the engine failed due to P factor. The foregoing 0 side slip recommendations apply to reciprocating engine multi-engine airplanes flown at VYSE with the inoperative engine feathered. The 0 side slip ball position for straight flight is also the 0 side slip position for turning flight. When bank angle is plotted against climb performance for hypothetical twin, 0 side slip results in the best, however marginal, climb performance or the least rate of descent. 0 bank, all rudder to counteract yaw, degrades climb performance as a result of moderate side slip. Using bank angle alone, no rudder, severely degrades climb performance as a result of a large side slip. The actual bank angle for 0 side slip varies among airplanes from 1 1/2 to 2 1/2 degrees. The position of the ball varies from 1/3 to 1/2 of a ball width from instrument center. For any multi-engine airplane, 0 side slip can be confirmed through the use of a yaw string. A yaw string is a piece of string or yarn approximately 18 to 36 inches in length taped to the base of the windshield or to the nose near the windshield along the airplane centerline. In 2-engine coordinated flight, the relative wind will cause the string to align itself with the longitudinal axis of the airplane and will position itself straight up the center of the windshield. This is 0 side slip. Experimentation with slips and skids will vividly display the location of the relative wind. Adequate altitude and flying speed must be maintained while accomplishing these maneuvers. With an engine set to 0 thrust, or feathered, and the airplane slowed to VYSE, a climb with maximum power on the remaining engine will reveal the precise bank angle and ball deflection required for 0 side slip and best climb performance. 0 side slip will again be indicated by the yaw string when it aligns itself vertically on the windshield. There will be very minor changes from this attitude depending upon the engine failed, with non-counter-rotating propellers, power available, airspeed and weight, but without more sensitive testing equipment, these changes are difficult to detect. The only significant difference would be the pitch attitude required to maintain VYSE under different density altitude, power available, and weight conditions. If a yaw string is attached to the airplane at the time of a VMC demonstration, it will be noted that VMC occurs under conditions of side slip. VMC was not determined under conditions of zero side slip during aircraft certification, and zero side slip is not part of a VMC demonstration for pilot certification. To review, there are two different sets of bank angles used in one-engine inoperative flight. To maintain directional control of a multi-engine airplane suffering an engine failure at low speeds, such as climb, momentarily bank at least below 5 degrees and a maximum of 10 degrees towards the inoperative engine as the pitch attitude for VYSE is set. This maneuver should be instinctive to the proficient multi-engine pilot and take only 1 to 2 seconds to attain. It is held just long enough to assure directional control as the pitch attitude for VYSE is assumed. To obtain the best climb performance, the airplane must be flown at VYSE and zero side slip, with the failed engine feathered and maximum available power from the operating engine. Zero side slip is approximately 2 degrees of bank toward the operating engine and a 1/3 to 1/2 ball deflection, also toward the operating engine. The precise bank angle and ball position will vary somewhat with make and model and power available. If above the airplane's single-engine ceiling, this attitude and configuration will result in the minimum rate of sink. In OEI flight at low altitudes and airspeeds such as the initial climb after takeoff, pilots must operate the airplane so as to guard against the 3 major accident factors. 1. Loss of directional control. 2. Loss of performance. And 3. Loss of flying speed. All have equal potential to be lethal. Loss of flying speed will not be a factor, however, when the airplane is operated with due regard for directional control and performance. Slow flight. There's nothing unusual about maneuvering during a slow flight in a multi-engine airplane. Slow flight may be conducted in straight and level flight, turns, in the clean configuration, landing configuration, or at any other combination of landing gear and flaps. Pilots should closely monitor cylinder head and oil temperatures during slow flight. Some high-performance multi-engine airplanes tend to heat up fairly quickly under some conditions of slow flight, particularly in the landing configuration. Simulated engine failure should not be conducted during slow flight. The airplane will be well below VSSE and very close to VMC. Stability, stall warning, or stall avoidance devices should not be disabled while maneuvering during slow flight. Stalls. Stall characteristics vary among multi-engine airplanes just as they do with single-engine airplanes, and therefore it is important to be familiar with them. The application of power upon stall recovery, however, has a significantly greater effect during stalls in a twin than a single-engine airplane. In the twin, an application of power blows large masses of air from the propellers directly over the wings, producing a significant amount of lift in addition to the expected thrust. The multi-engine airplane, particularly at light operating weights, typically has a higher thrust-to-weight ratio, making it quicker to accelerate out of a stalled condition. In general, stall recognition and recovery training in twins is performed similar to any high-performance single-engine airplane. However, for twins, all stall maneuvers should be planned so as to be completed at least 3,000 feet AGL. Single-engine stalls, or stalls with significantly more power on one engine than the other, should not be attempted due to the likelihood of a departure from controlled flight and possible spin entry. Similarly, simulated engine failures should not be performed during stall entry and recovery. Power off stalls, approach and landing. Power off stalls are practiced to simulate typical approach and landing scenarios. To initiate a power off stall maneuver, the area surrounding the airplane should first be cleared for possible traffic. The airplane should then be slowed and configured for an approach and landing. A stabilized descent should be established, approximately 500 FPM, and trim adjusted. The pilot should then transition smoothly from the stabilized descent attitude to a pitch attitude that will induce a stall. Power is reduced further during this phase, and trimming should cease at speeds slower than takeoff. When the airplane reaches a stalled condition, the recovery is accomplished by simultaneously reducing the angle of attack with coordinated use of the flight controls and smoothly applying takeoff or specified power. The flap setting should be reduced from full to approach, or as recommended by the manufacturer. Then, with the positive rate of climb, the landing gear is selected up. The remaining flaps are then retracted as climb has commenced. This recovery process should be completed with a minimum loss of altitude appropriate to the aircraft characteristics. The airplane should be accelerated to Vx if simulated obstacles are present, or Vy during recovery and climb. Considerable forward elevator, stabilator, pressure will be required after the stall recovery as the airplane accelerates to Vx or Vy. Appropriate trim input should be anticipated. Power off stalls may be performed with wings level or from shallow and medium bank turns. When recovering from a stall performed from turning flight, the angle of attack should be reduced prior to leveling the wings. Flight control inputs should be coordinated. It is usually not advisable to execute full stalls in multi-engine airplanes because of their relatively high wing loading. Stall training should be limited to approaches to stalls and when a stall condition occurs. Recoveries should be initiated at the onset or decay of control effectiveness or when the first physical indication of the stall occurs. Power on stalls, takeoff and departure. Power on stalls are practiced to simulate typical takeoff scenarios. To initiate a power on stall maneuver, the area surrounding the airplane should always be cleared to look for potential traffic. The airplane is slowed to the manufacturer's recommended liftoff speed. The airplane should be configured in the takeoff configuration. Trim should be adjusted for this speed. Engine power is then increased to that recommended in the AFM/POH for the practice of power on stalls. In the absence of a recommended setting, use approximately 65% of maximum available power while placing the engine in a pitch attitude that will induce a stall. Other specified, reduced, power settings may be used to simulate performance at higher gross weights and density altitudes. When the airplane reaches a stalled condition, the recovery is made by simultaneously lowering the angle of attack with coordinated use of the flight controls and applying power as appropriate. However, if simulating limited power available for high gross weight and density altitude situations, the power during the recovery should be limited to that specified. The recovery should be completed with a minimum loss of altitude appropriate to aircraft characteristics. The landing gear should be retracted when a positive rate of climb is attained and flaps retracted if flaps were set for takeoff. The target airspeed on recovery is Vx if simulated obstructions are present, or Vy. The pilot should anticipate the need for nose-down trim as the airplane accelerates to Vx or Vy after recovery. Power on stalls may be performed from straight flight or from shallow and medium banked turns. When recovering from the power on stall performed from turning flight, the angle of attack should be reduced prior to leveling the wings and the flight control inputs should be coordinated. Spin awareness. No multi-engine airplane is approved for spins, and their spin recovery characteristics are generally very poor. It is therefore necessary to practice spin avoidance and maintain a high awareness of situations that can result in an inadvertent spin. In order to spin any airplane, it must first be stalled. At the stall, a yawing moment must be introduced. In a multi-engine airplane, the yawing moment may be generated by rudder input or asymmetrical thrust. It follows, then, that spin awareness be at its greatest during VMC demonstrations, stall practice, slow flight, or any condition of high asymmetrical thrust, particularly at low speed, high angle of attack. Single-engine stalls are not part of any multi-engine training curriculum. A situation that may inadvertently degrade into a spin entry is a simulated engine failure introduced at an inappropriately low speed. No engine failure should ever be introduced below safe, intentional one-engine inoperative speed, VSSE. If no VSSE is published, use VYSE. The necessity of simulating engine failures at low airspeeds is erroneous. Other than training situations, the multi-engine airplane is only operated below VSSE for mere seconds, just after liftoff, or during the last few dozen feet of altitude in preparation for a landing. For spin avoidance, when practicing engine failures, the flight instructor should pay strict attention to the maintenance of proper airspeed and bank angle as the student executes the appropriate procedure. The instructor should also be particularly alert during the stall and slow flight practice. Forward center of gravity positions result in favorable stall and spin avoidance characteristics, but do not eliminate the hazard. When performing a VMC demonstration, the instructor should also be alert for any sign of an impending stall. The student may be highly focused on the directional control aspect of the maneuver to the extent that impending stall indications go unnoticed. If a VMC demonstration cannot be accomplished under existing conditions of density altitude, it may, for training purposes, be done utilizing the rudder blocking technique described in the following section. As very few twins have ever been spin tested, none are required to, the recommended spin recovery techniques are based only on the best information available. The departure from controlled flight may be quite abrupt and possibly disorienting. The direction of an upright spin can be confirmed from the turn needle or the symbolic airplane of the turn coordinator if necessary. Do not rely on the ball position or other instruments. If a spin is entered, most manufacturers recommend immediately retarding both throttles to idle, applying full rudder opposite the direction of rotation, and applying full forward elevator stabilator pressure with ailerons neutral. These actions should be taken as near simultaneously as possible. The controls should then be held in that position. Recovery, if possible, will take considerable altitude. The longer the delay from entry until taking corrective action, the less likely that recovery will be successful. End Chapter 12, Part 4. Recording by Dale Latham.
Chapter 12, Part 5 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Steve Vito, www.stevevito.com. Airplane Flying Handbook by the FAA. Chapter 12, Engine Inoperative Loss of Directional Control Demonstration. An engine inoperative loss of directional control demonstration, often referred to as a VMC demonstration, is a required task on the practical tests for a multi-engine class rating. A thorough knowledge of the factors that affect VMC, as well as its definition, is essential for multi-engine pilots, and as such, an essential part of that required task. VMC is a speed established by the manufacturer, published in the AFM-POH, and marked on most airspeed indicators with a red radial line. The multi-engine pilot must understand that VMC is not a fixed airspeed under all conditions. VMC is a fixed airspeed only for the very specific set of circumstances under which it was determined during aircraft certification. See Figure 12-19. In reality, VMC varies with a variety of factors as outlined below. The VMC noted in practice and demonstration, or in actual single-engine operation, could be less or even greater than the published value, depending upon conditions and technique. In aircraft certification, VMC is the sea-level calibrated airspeed at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the airplane with that engine still inoperative, and then maintain straight flight at the same speed with an angle of bank of not more than 5 degrees. The foregoing refers to the determination of VMC under dynamic conditions. This technique is only used by highly experienced flight test pilots during aircraft certification. It is never to be attempted outside of these circumstances. In aircraft certification, there is also a determination of VMC under static or steady-state conditions. If there is a difference between the dynamic and static speeds, the higher of the two is published as VMC. The static determination is simply the ability to maintain straight flight at VMC with a bank angle of not more than 5 degrees. This more closely resembles the VMC demonstration required in the practical tests for a multi-engine class rating. The AFM-POH published VMC is determined with the critical engine inoperative. The critical engine is the engine whose failure has the most adverse effect on directional control. On twins with each engine rotating in conventional clockwise rotation as viewed from the pilot's seat, the critical engine will be the left engine. Multi-engine airplanes are subject to the P factor, just as single-engine airplanes are. The descending propeller blade of each engine will produce greater thrust than the ascending blade when the airplane is operated under power and at positive angles of attack. The descending propeller blade of the right engine is also a greater distance from the center of gravity, and therefore has a longer moment arm than the descending propeller blade of the left engine. As a result, failure of the left engine will result in the most asymmetrical thrust, adverse yaw, as the right engine will be providing the remaining thrust. See Figure 12-19. Many twins are designed with a counter-rotating right engine. With this design, the degree of asymmetrical thrust is the same with either engine inoperative. No engine is more critical than the other, and a VMC demonstration may be performed with either engine windmilling. In aircraft certification, dynamic VMC is determined under the following conditions. Maximum available takeoff power. VMC increases as power is increased on the operating engine. With normally aspirated engines, VMC is highest at takeoff power and sea level, and decreases with altitude. With turbocharged engines, takeoff power, and therefore VMC, remains constant with increases in altitude up to the engine's critical altitude, the altitude where the engine can no longer maintain 100% power. Above the critical altitude, VMC decreases just as it would with a normally aspirated engine, whose critical altitude is sea level. VMC tests are conducted at a variety of altitudes. The results of those tests are then extrapolated to a single sea level value. Windmilling propeller. VMC increases with increased drag on the inoperative engine. VMC is highest, therefore, when the critical engine propeller is windmilling at a low pitch, high RPM blade angle. VMC is determined with the critical engine propeller windmilling in the takeoff position, unless the engine is equipped with an auto feather system. Most unfavorable weight and center of gravity position. VMC increases as the center of gravity is moved aft. The moment arm of the rudder is reduced, and therefore its effectivity is reduced as the center of gravity is moved aft. At the same time, the moment arm of the propeller blade is increased, aggravating asymmetrical thrust. Invariably, the aftmost CG limit is the most unfavorable CG position. Currently, 14 CFR Part 23 calls for VMC to be determined at the most unfavorable weight. For twin certification under CAR 3 or early 14 CFR Part 23, the weight at which VMC was determined was not specified. VMC increases as weight is reduced. See Figure 12-20. Landing gear retracted. VMC increases when the landing gear is retracted. Extending landing gear aids directional stability, which tends to decrease VMC. Wing flaps in the takeoff position. For most twins, this will be 0 degrees of flaps. Cowl flaps in the takeoff position. Airplane trimmed for takeoff. Airplane airborne and ground effect negligible. Maximum of 5-degree angle of bank. VMC is highly sensitive to bank angle. To prevent claims of an unrealistically low VMC speed in aircraft certification, the manufacturer is permitted to use a maximum of a 5-degree bank angle toward the operative engine. The horizontal component of lift generated by the bank assists the rudder in counteracting the asymmetrical thrust of the operative engine. The bank angle works in the manufacturer's favor in lowering VMC. VMC is reduced significantly with increases in bank angle. Conversely, VMC increases significantly with decreases in bank angle. Tests have shown that VMC may increase more than 3 knots for each degree of bank angle less than 5 degrees. Loss of directional control may be experienced at speeds almost 20 knots above published VMC when the wings are held level. The 5-degree bank angle maximum is a regulatory limit imposed upon manufacturers in aircraft certification. The 5-degree bank angle does not inherently establish zero side slip or best single-engine climb performance. Zero side slip, and therefore best single-engine climb performance, occurs at bank angles significantly less than 5 degrees. The determination of VMC in certification is solely concerned with the minimum speed for directional control under a very specific set of circumstances, and has nothing to do with climb performance, nor is it the optimum airplane attitude or configuration for climb performance. During dynamic VMC determination in aircraft certification, cuts of the critical engine using the mixture control are performed by flight test pilots while gradually reducing the speed with each attempt. VMC is the minimum speed at which directional control could be maintained within 20 degrees of the original entry heading when a cut of the critical engine was made. During such tests, the climb angle with both engines operating was high, and the pitch attitude following the engine cut had to be quickly lowered to regain the initial speed. Pilots should never attempt to demonstrate VMC with an engine cut from high power, and never intentionally fail an engine at speeds less than VSSE. The actual demonstration of VMC and recovery in flight training more closely resembles static VMC determination in aircraft certification. For a demonstration, the pilot should select an altitude that will allow completion of the maneuver at least 3,000 feet AGL. The following description assumes a twin with non-counter rotating engines, where the left engine is critical. With the landing gear retracted and the flaps set to the takeoff position, the airplane should be slowed to approximately 10 knots above VSSE or VYSE, whichever is higher, and trimmed for takeoff. For the remainder of the maneuver, the trim setting should not be altered. An entry heading should be selected and high RPM set on both propeller controls. Power on the left engine should be throttled back to idle as the right engine power is advanced to the takeoff setting. The landing gear warning horn will sound as long as the throttle is retarded. The pilot should continue to carefully listen, however, for the stall warning horn, if so equipped, or watch for the stall warning light. The left yawing and rolling movement of the asymmetrical thrust is counteracted primarily with the right rudder. A bank angle of 5 degrees, a right bank in this case, should also be established. While maintaining entry heading, The pitch attitude is slowly increased to decelerate at a rate of 1 knot per second, no faster. As the airplane slows and control effectivity decays, the increasing yawing tendency should be counteracted with additional rudder pressure. Aileron displacement will also increase in order to maintain 5 degrees of bank. An airspeed is soon reached where full right rudder travel and a 5-degree right bank can no longer counteract the asymmetrical thrust, and the airplane will begin to yaw uncontrollably to the left. The moment the pilot first recognizes the uncontrollable yaw, or experiences any symptom associated with a stall, the operating engine throttle should be sufficiently retarded to stop the yaw as the pitch attitude is decreased. Recovery is made with a minimum loss of altitude to straight flight on the entry heading at VSSE or VYSE before setting symmetrical power. The recovery should not be attempted by increasing power on the windmilling engine alone. To keep the foregoing description simple, there were several important background details that were not covered. The rudder pressure during the demonstration can be quite high. In certification, 150 pounds of force is permitted before the limiting factor becomes rudder pressure, not rudder travel. Most twins will run out of rudder travel long before 150 pounds of pressure is required. Still, it will seem considerable. Maintaining altitude is not a criterion in accomplishing this maneuver. This is a demonstration of controllability, not performance. Many airplanes will lose or gain altitude during the demonstration. Begin the maneuver at an altitude sufficient to allow completion by 3,000 feet AGL. As discussed earlier, with normally aspirated engines, VMC decreases with altitude. Stalling speed, VS, however, remains the same. Except for a few models, published VMC is almost always higher than VS. At sea level, there is usually a margin of several knots between VMC and VS, but the margin decreases with altitude, and at some altitude, VMC and VS are the same. See Figure 12-21. Should a stall occur while the airplane is under asymmetrical power, particularly high asymmetrical power, a spin entry is likely. The yawing moment induced from asymmetrical thrust is little different from that induced by full rudder in an intentional spin in the appropriate model of a single-engine airplane. In this case, however, the airplane will depart controlled flight in the direction of the idle engine, not in the direction of the applied rudder. Twins are not required to demonstrate recoveries from spins, and their spin recovery characteristics are generally very poor. Where VS is encountered at or before VMC, the departure from controlled flight may be quite sudden, with strong yawing and rolling tendencies to the inverted position and a spin entry. Therefore, during a VMC demonstration, if there are any symptoms of an impending stall, such as a stall warning light or horn, airframe or elevator buffet, or rapid decay in control effectiveness, the maneuver should be terminated immediately, the angle of attack reduced as the throttle is retarded, and the airplane returned to the entry airspeed. It should be noted that if the pilots are wearing headsets, the sound of a stall warning horn will tend to be masked. The VMC demonstration only shows the earliest onset of a loss of directional control. It is not a loss of control of the airplane when performed in accordance with the foregoing procedures. A stalled condition should never be allowed to develop. Stalls should never be performed with asymmetrical thrust, and the VMC demonstration should never be allowed to degrade into a single-engine stall. A VMC demonstration that is allowed to degrade into a single-engine stall with high asymmetrical thrust is very likely to result in the loss of control of the airplane. An actual demonstration of VMC may not be possible under certain conditions of density altitude, or with airplanes whose VMC is equal to or less than VS. Under those circumstances, as a training technique, a demonstration of VMC may be safely conducted by artificially limiting rudder travel to simulate maximum available rudder. Limiting rudder travel should be accomplished at a speed well above VS, approximately 20 knots. The rudder limiting technique avoids the hazard of spinning as a result of stalling with high asymmetrical power, yet is effective in demonstrating the loss of directional control. The VMC demonstration should never be performed from a high-pitch attitude with both engines operating and then reducing power on one engine. The preceding discussion should also give ample warning as to why engine failures are never to be performed at low airspeeds. An unfortunate number of airplanes and pilots have been lost from unwarranted simulated engine failures at low airspeeds that degenerated into loss of control of the airplane. VSSE is the minimum airspeed at which any engine failure should be simulated. Multi-engine training considerations. Flight training in a multi-engine airplane can be safely accomplished if both the instructor and the student are cognizant of the following factors. No flight should ever begin without a thorough pre-flight briefing of the objectives, maneuvers, expected student actions, and completion standards. A clear understanding must be reached as to how the simulated emergencies will be introduced and what action the student is expected to take. The introduction, practice, and testing of emergency procedures has always been a sensitive subject. Surprising a multi-engine student with an emergency without a thorough briefing beforehand has no place in flight training. Effective training must be carefully balanced with safety considerations. Simulated engine failures, for example, can very quickly become actual emergencies or lead to loss of the airplane when approached carelessly. Pulling circuit breakers can lead to a subsequent gear-up landing. Stall spin accidents in training for emergencies rival the number of stall spin accidents from actual emergencies. All normal, abnormal, and emergency procedures can and should be introduced and practiced in the airplane as it sits on the ground, power off. In this respect, the airplane is used as a cockpit procedures trainer, CPT, ground trainer, or simulator. The value of this training should never be underestimated. The engines do not have to be operating for real learning to occur. Upon completion of a training session, care should be taken to return items such as switches, valves, trim, fuel selectors, and circuit breakers to their normal positions. Pilots who do not use a checklist effectively will be at a significant disadvantage in multi-engine airplanes. Use of a checklist is essential to safe operation of airplanes, and no flight should ever be conducted without one. The manufacturer's checklist or an aftermarket checklist for the specific make, model, and model year should be used. If there is a procedural discrepancy between the checklist and AFM-POH, then the AFM-POH always takes precedence. Certain immediate action items, such as a response to an engine failure in a critical phase of flight, should be committed to memory. After they are accomplished, and as workload permits, the pilot should verify the action taken with a printed checklist. Simulated engine failures during the takeoff ground roll should be accomplished with the mixture control. The simulated failure should be introduced at a speed no greater than 50% of VMC. If the student does not react promptly by retarding both throttles, the instructor can always pull the other mixture. The FAA recommends that all in-flight simulated engine failures below 3,000 feet AGL be introduced with a smooth reduction of the throttle. Thus, the engine is kept running and is available for instant use if necessary. Throttle reduction should be smooth rather than abrupt to avoid abusing the engine and possibly causing damage. All in-flight engine failures must be conducted at VSSE or above. If the engines are equipped with dynamic crankshaft counterweights, it is essential to make throttle reductions for simulated failures smoothly. Other areas leading to dynamic counterweight damage include high RPM and low manifold pressure combinations, overboosting, and propeller feathering. Severe damage or repetitive abuse to counterweights will eventually lead to engine failure. Dynamic counterweights are found on larger, more complex engines. Instructors should check with the maintenance personnel or the engine manufacturer to determine if their engines are so equipped. When an instructor simulates an engine failure, the student should respond with the appropriate memory items and retard the propeller control towards the feather position. Assuming zero thrust will be set, the instructor should promptly move the propeller control forward and set the appropriate manifold pressure and RPM. It is vital that the student be kept informed of the instructor's intentions. At this point, the instructor may state words to the effect, "I have the right engine, you have the left. I have set zero thrust and the right engine is simulated feathered. There should never be any ambiguity as to who is operating what systems or controls. Following a simulated engine failure, the instructor should continue to care for the failed engine, just as a student cares for the operative engine. If zero thrust is set to simulate a feathered propeller, the cowl flap should be closed and the mixture leaned. An occasional clearing of the engine is also desirable. If possible, avoid high-power applications immediately following a prolonged cooldown at a zero-thrust power setting. The flight instructor must impress on the student multi-engine pilot the critical importance of feathering the propeller in a timely manner should an actual engine failure situation be encountered. A windmilling propeller, in many cases, has given the improperly trained multi-engine pilot the mistaken perception that the failed engine is still developing useful thrust, resulting in a psychological reluctance to feather, as feathering results in the cessation of propeller rotation. The flight instructor should spend ample time demonstrating the difference in the performance capabilities of the airplane with a simulated feather propeller, zero thrust, as opposed to a windmilling propeller. All actual propeller feathering should be performed at altitudes and positions where safe landings on established airports could be readily accomplished. Feathering and restart should be planned so as to be completed no lower than 3,000 feet AGL. At certain elevations, and with many popular multi-engine training airplanes, this may be above the single-engine service ceiling, and level flight will not be possible. Repeated feathering and unfeathering is hard on the engine and airframe, and should be done only as absolutely necessary to ensure adequate training. The FAA's practical test standards for a multi-engine class rating requires the feathering and unfeathering of one propeller during flight in airplanes in which it is safe to do so. While much of this chapter has been devoted to the unique flight characteristics of the multi-engine airplane with one engine inoperative, the modern well-maintained reciprocating engine is remarkably reliable. Simulated engine failures at extremely low altitudes, such as immediately after liftoff and or below VSSE, are undesirable in view of the non-existent safety margins involved. The high risk of simulating an engine failure below 200 feet AGL does not warrant practicing such maneuvers. For training in maneuvers that would be hazardous in flight, or for initial and recurrent qualification in an advanced multi-engine airplane, a simulator training center or manufacturer's training course should be given consideration. Comprehensive training manuals and classroom instruction are available along with system training aids, audio visuals, and flight training devices and simulators. Training under a wide variety of environmental and aircraft conditions is available through simulation. Emergency procedures that would be either dangerous or impossible to accomplish in an airplane can be done safely and effectively in a flight training device or simulator. The flight training device or simulator need not necessarily duplicate the specific make and model of an airplane to be useful. Highly effective instruction can be obtained in training devices for other makes and models, as well as generic training devices. The majority of multi-engine training is conducted in 4 to 6 place airplanes at weights significantly less than maximum. Single-engine performance, particularly at low-density altitudes, may be deceptively good. To experience the performance expected at higher weights, altitudes, and temperatures, the instructor should occasionally artificially limit the amount of manifold pressure available on the operative engine. Airport operations above the single-engine ceiling can also be simulated in this manner. Loading the airplane with passengers to practice emergencies at maximum takeoff weight is not appropriate. The use of the touch-and-go landing and takeoff in flight training has always been somewhat controversial. The value of the learning experience must be weighted against the hazards of reconfiguring the airplane for takeoff in an extremely limited time, as well as the loss of the follow-through ordinarily experienced in a full-stop landing. Touch-and-goes are not recommended during initial aircraft familiarization in multi-engine airplanes. If touch-and-goes are to be performed at all, the student and instructor responsibilities need to be carefully briefed prior to each flight. Following touchdown, the student will ordinarily maintain directional control while keeping the left hand on the yoke and the right hand on the throttles. The instructor resets the flaps and trim and announces when the airplane has been reconfigured. The multi-engine airplane needs considerably more runway to perform a touch-and-go than a single-engine airplane. A full-stop taxi-back landing is preferable during initial familiarization. Solo touch-and-goes and twins are strongly discouraged. End of Chapter 12. This has been read by Steve Vito, www.stevevito.com.
Chapter 13 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook by the FAA. Transition to tailwheel airplanes. Tailwheel airplanes. Tailwheel airplanes are often referred to as conventional gear airplanes. Due to their design and structure, tailwheel airplanes exhibit operational and handling characteristics that are different from those of tricycle gear airplanes. Tailwheel airplanes are not necessarily more difficult to take off, land, and/or taxi than tricycle gear airplanes. In fact, under certain conditions, they may even handle with less difficulty. This chapter will focus on the operational differences that occur during ground operations, takeoffs, and landings. Landing gear. The main landing gear forms the principal support of the airplane on the ground. The tailwheel also supports the airplane, but steering and directional control are its primary functions. With the tailwheel type airplane, the two main struts are attached to the airplane slightly ahead of the airplane's center of gravity, CG. The rudder pedals are the primary directional controls while taxiing. Steering with the pedals may be accomplished through the forces of airflow or propeller slipstream acting on the rudder surface, or through a mechanical linkage to the steerable tailwheel. Initially, the pilot should taxi with the heels of the feet resting on the cockpit floor, and the balls of the feet on the bottom of the rudder pedals. The feet should be slid up onto the brake pedals only when it is necessary to depress the brakes. This permits the simultaneous application of rudder and brake whenever needed. Some models of tailwheel airplanes are equipped with heel brakes rather than toe brakes. In either configuration, the brakes are used primarily to stop the airplane at a desired point, to slow the airplane, or as an aid in making a sharp, controlled turn. Whenever used, they must be applied smoothly, evenly, and cautiously at all times. Taxiing. When beginning to taxi, the brakes should be tested immediately for proper operation. This is done by first applying power to start the airplane moving slowly forward, then retarding the throttle and simultaneously applying pressure smoothly to both brakes. If braking action is unsatisfactory, the engine should be shut down immediately. To turn the airplane on the ground, the pilot should apply rudder in the desired direction of turn and use whatever power or brake that is necessary to control the taxi speed. The rudder should be held in the direction of the turn until just short of the point where the turn is to be stopped. Then the rudder pressure released or slight opposite pressure applied as needed. While taxiing, the pilot will have to anticipate the movements of the airplane and adjust rudder pressure accordingly. Since the airplane will continue to turn slightly even as the rudder pressure is being released, the stopping of the turn must be anticipated and the rudder pedals neutralized before the desired heading is reached. In some cases, it may be necessary to apply opposite rudder to stop the turn, depending on the taxi speed. The presence of moderate to strong headwinds and/or strong propeller slipstream makes the use of the elevator necessary to maintain control of the pitch attitude while taxiing. This becomes apparent when considering the lifting action that may be created on the horizontal tail surfaces by either of those two factors. The elevator control should be held in the aft position, stick or yoke back, to hold the tail down. When taxiing in a quartering headwind, the wing on the upwind side will usually tend to be lifted by the wind unless the aileron control is held in that direction. Upwind aileron, up. Moving the aileron into the up position reduces the effect of wind striking that wing, thus reducing the lifting action. This control movement will also cause the opposite aileron to be placed in the down position, thus creating drag and possibly some lift on the downwind wing, further reducing the tendency of the upwind wing to rise. When taxiing with a quartering tailwind, the elevator should be held in the full down position, stick or yoke full forward, and the upwind aileron down. Since the wind is striking the airplane from behind, these control positions reduce the tendency of the wind to get under the tail and the wing, possibly causing the airplane to nose over. The application of these crosswind taxi corrections also helps to minimize the weather vaning tendency and ultimately results in increased controllability. An airplane with a tailwheel has a tendency to weather vane or turn into the wind while it is being taxied. The tendency of the airplane to weather vane is greatest while taxiing directly crosswind. Consequently, directional control is somewhat difficult. Without brakes, it is almost impossible to keep the airplane from turning into any wind of considerable velocity, since the airplane's rudder control capability may be inadequate to counteract the crosswind. In taxiing downwind, the tendency to weather vane is increased due to the tailwind decreasing the effectiveness of the flight controls. This requires a more positive use of the rudder and the brakes, particularly if the wind velocity is above that of a light breeze. Unless the field is soft or very rough, it is best when taxiing downwind to hold the elevator control in the forward position. Even on soft fields, the elevator should be raised only as much as is absolutely necessary to maintain a safe margin of control in case there is a tendency of the airplane to nose over. On most tailwheel-type airplanes, directional control while taxiing is facilitated by the use of a steerable tailwheel, which operates along with the rudder. The tailwheel steering mechanism remains engaged when the tailwheel is operated through an arc of about 16 to 18 degrees, each side of neutral, and then automatically becomes full swiveling when turned to a greater angle. On some models, the tailwheel may also be locked in place. The airplane may be pivoted within its own length if desired, yet is fully steerable for slight turns while taxiing forward. While taxiing, the steerable tailwheel should be used for making normal turns and the pilot's feet kept off the brake pedals to avoid unnecessary wear on the brakes. Since a tailwheel-type airplane rests on the tailwheel as well as on the main landing wheels, it assumes a nose-high attitude when on the ground. In most cases, this places the engine cowling high enough to restrict the pilot's vision of the area directly ahead of the airplane. Consequently, objects directly ahead of the airplane are difficult, if not impossible, to see. To observe and avoid colliding with any objects or hazardous surface conditions, the pilot should alternately turn the nose from one side to the other, that is, zigzag or make a series of short S-turns while taxiing forward. This should be done slowly, smoothly, positively, and cautiously. Normal takeoff roll. After taxiing onto the runway, the airplane should be carefully aligned with the intended takeoff direction and the tailwheel positioned straight or centered. In airplanes equipped with a locking device, the tailwheel should be locked in the centered position. After releasing the brakes, the throttle should be smoothly and continuously advanced to takeoff power. As the airplane starts to roll forward, the pilot should slide both feet down on the rudder pedals so that the toes or balls of the feet are on the rudder portions, not on the brake portions. An abrupt application of power may cause the airplane to yaw sharply to the left because of the torque effects of the engine and propeller. Also, precession will be particularly noticeable during takeoff in a tailwheel airplane if the tail is rapidly raised from a 3-point to a level flight attitude. The abrupt change of attitude tilts the horizontal axis of the propeller, and the resulting precession produces a forward force on the right side, 90 degrees ahead in the direction of rotation, yawing the airplane's nose to the left. The amount of force created by this precession is directly related to the rate the propeller axis is tilted when the tail is raised. With this in mind, the throttle should always be advanced smoothly and continuously to prevent any sudden swerving. Smooth, gradual advancement of the throttle is very important in tailwheel-type airplanes, since peculiarities in their takeoff characteristics are accentuated in proportion to how rapidly the takeoff power is applied. As speed is gained, the elevator control will tend to assume a neutral position if the airplane is correctly trimmed. At the same time, directional control should be maintained with smooth, prompt, positive rudder corrections throughout the takeoff roll. The effects of torque and P-factor at the initial speeds tend to pull the nose to the left. The pilot must use what rudder pressure is needed to correct for these effects, or for existing wind conditions to keep the nose of the airplane headed straight down the runway. The use of brakes for steering purposes should be avoided, since they will cause slower acceleration of the airplane's speed, lengthen the takeoff distance, and possibly result in severe swerving. When the elevator trim is set for takeoff, on application of maximum allowable power, the airplane will, when sufficient speed has been attained, normally assume the correct takeoff pitch attitude on its own. The tail will rise slightly. This attitude can then be maintained by applying slight back elevator pressure. If the elevator control is pushed forward during the takeoff roll to prematurely raise the tail, its effectiveness will rapidly build up as the speed increases, making it necessary to apply back elevator pressure to lower the tail to the proper takeoff attitude. This erratic change in attitude will delay the takeoff and lead to directional control problems. Rudder pressure must be used promptly and smoothly to counteract yawing forces so that the airplane continues straight down the runway. While the speed of the takeoff roll increases, more and more pressure will be felt on the flight controls, particularly the elevators and rudder. Since the tail surfaces receive the full effect of the propeller slipstream, they become effective first. As the speed continues to increase, all of the flight controls will gradually become effective enough to maneuver the airplane about its three axes. It is at this point in the taxi to flight transition that the airplane is being flown more than taxied. As this occurs, progressively smaller rudder deflections are needed to maintain direction. Takeoff. Since a good takeoff depends on the proper takeoff attitude, it is important to know how this attitude appears and how it is attained. The ideal takeoff attitude requires only minimum pitch adjustments shortly after the airplane lifts off to attain the speed for the best rate of climb. The tail should first be allowed to rise off the ground slightly to permit the airplane to accelerate more rapidly. At this point, the position of the nose in relation to the horizon should be noted. Then elevator pressure applied as necessary to hold this attitude. The wings are kept level by applying aileron pressure as necessary. The airplane may be allowed to fly off the ground while in normal takeoff attitude. Forcing it into the air by applying excessive back elevator pressure would result in an excessively high pitch attitude and may delay the takeoff. As discussed earlier, excessive and rapid changes in pitch attitude result in proportionate changes in the effects of torque, making the airplane more difficult to control. Although the airplane can be forced into the air, this is considered an unsafe practice and should be avoided under normal circumstances. If the airplane is forced to leave the ground by using too much back elevator pressure before adequate flying speed is attained, the wing's angle of attack may be excessive, causing the airplane to settle back to the runway or even to stall. On the other hand, if sufficient back elevator pressure is not held to maintain the correct takeoff attitude after becoming airborne, or the nose is allowed to lower excessively, the airplane may also settle back to the runway. This occurs because the angle of attack is decreased and lift is diminished to the degree where it will not support the airplane. It is important to hold the attitude constant after rotation or liftoff. As the airplane leaves the ground, the pilot must continue to maintain straight flight as well as holding the proper pitch attitude. During takeoffs in strong, gusty wind, it is advisable that an extra margin of speed be obtained before the airplane is allowed to leave the ground. A takeoff at the normal takeoff speed may result in a lack of positive control, or a stall, when the airplane encounters a sudden lull in strong, gusty wind or other turbulent air currents. In this case, the pilot should hold the airplane on the ground longer to attain more speed, then make a smooth, positive rotation to leave the ground. Crosswind takeoff. It is important to establish and maintain the proper amount of crosswind correction prior to liftoff. That is, apply aileron pressure towards the wind to keep the upwind wing from rising and apply rudder pressure as needed to prevent weather vaning. As the tailwheel is raised off the runway, the holding of aileron control into the wind may result in the downwind wing rising and the downwind main wheel lifting off the runway first, with the remainder of the takeoff roll being made on one main wheel. This is acceptable and is preferable to side skipping. If a significant crosswind exists, the main wheels should be held on the ground slightly longer than in a normal takeoff so that a smooth but definite liftoff can be made. This procedure will allow the airplane to leave the ground under more positive control so that it will definitely remain airborne while the proper amount of drift correction is being established. More importantly, it will avoid imposing excessive side loads on the landing gear and prevent possible damage that would result from the airplane settling back to the runway while drifting. As both main wheels leave the runway and ground friction no longer resists drifting, the airplane will be slowly carried sideways with the wind until adequate drift correction is maintained. Short field takeoff. Wing flaps should be lowered prior to takeoff if recommended by the manufacturer. Takeoff power should be applied smoothly and continuously. There should be no hesitation to accelerate the airplane as rapidly as possible. As the takeoff roll progresses, the airplane's pitch attitude and angle of attack should be adjusted to that which results in the minimum amount of drag and the quickest acceleration. The tail should be allowed to rise off the ground slightly, then held in this tail-low flight attitude until the proper liftoff or rotation airspeed is attained. For the steepest climb-out and best obstacle clearance, the airplane should be allowed to roll with its full weight on the main wheels and accelerated to the liftoff speed. Soft field takeoff. Wing flaps may be lowered prior to starting the takeoff, if recommended by the manufacturer, to provide additional lift and transfer the airplane's weight from the wheels to the wings as early as possible. The airplane should be taxied onto the takeoff surface without stopping on a soft surface. Stopping on a soft surface, such as mud or snow, might bog the airplane down. The airplane should be kept in continuous motion with sufficient power while lining up for the takeoff roll. As the airplane is aligned with the proposed takeoff path, takeoff power is applied smoothly and as rapidly as the power plant will accept it without faltering. The tail should be kept low to maintain the inherent positive angle of attack and to avoid any tendency of the airplane to nose over as a result of soft spots, tall grass, or deep snow. When the airplane is held at a nose-high attitude throughout the takeoff run, the wings will, as speed increases and lift develops, progressively relieve the wheels of more and more of the airplane's weight, thereby minimizing the drag caused by surface irregularities or adhesion. If this attitude is accurately maintained, the airplane will virtually fly itself off the ground. The airplane should be allowed to accelerate to climb speed in ground effect. Touchdown. The touchdown is the gentle settling of the airplane onto the landing surface. The roundout and touchdown should be made with the engine idling and the airplane at minimum controllable airspeed, so that the airplane will touch down at approximately stalling speed. As the airplane settles, the proper landing attitude must be attained by applying whatever back elevator pressure is necessary. The roundout and touchdown should be timed so that the wheels of the main landing gear and tailwheel touch down simultaneously, 3-point landing. This requires proper timing, technique, and judgment of distance and altitude. See Figure 13-1. When the wheels make contact with the ground, the elevator control should be carefully eased fully back to hold the tail down and to keep the tailwheel on the ground. This provides more positive directional control of the airplane equipped with a steerable tailwheel and prevents any tendency for the airplane to nose over. If the tailwheel is not on the ground, easing back on the elevator control may cause the airplane to become airborne again because the change in attitude will increase the angle of attack and produce enough lift for the airplane to fly. It is extremely important that the touchdown occur with the airplane's longitudinal axis exactly parallel to the direction the airplane is moving along the runway. Failure to accomplish this not only imposes severe side loads on the landing gear, but imparts ground looping, swerving tendencies. To avoid these side stresses or a ground loop, the pilot must never allow the airplane to touch down while in a crab or while drifting. After landing roll. The landing process must never be considered complete until the airplane decelerates to the normal taxi speed during the landing roll or has been brought to a complete stop when clear of the landing area. The pilot must be alert for directional control difficulties immediately upon and after touchdown due to the ground friction on the wheels. The friction creates a pivot point on which a moment arm can act. This is because the CG is behind the main wheels. See Figure 13-2. Any difference between the direction the airplane is traveling and the direction it is headed will produce a moment about the pivot point of the wheels, and the airplane will tend to swerve. Loss of directional control may lead to an aggravated, uncontrolled, tight turn on the ground or a ground loop. The combination of inertia acting on the CG and ground friction of the main wheels resisting it during the ground loop may cause the airplane to tip or lean enough for the outside wingtip to contact the ground and may even impose a sideward force that could collapse the landing gear. The airplane can ground loop late in the after landing roll because rudder effectiveness decreases with the decreasing flow of air along the rudder surface as the airplane slows. As the airplane speed decreases and the tailwheel has been lowered to the ground, the steerable tailwheel provides more positive directional control. To use the brakes, the pilot should slide the toes or feet up from the rudder pedals to the brake pedals or apply heel pressure in airplanes equipped with heel brakes. If rudder pressure is being held at the time braking action is needed, that pressure should not be released as the feet or toes are being slid up to the brake pedals, because control may be lost before brakes can be applied. During the ground roll, the airplane's direction of movement may be changed by carefully applying pressure on one brake or uneven pressures on each brake in the desired direction. Caution must be exercised when applying brakes to avoid over-controlling. If a wing starts to rise, aileron control should be applied toward that wing to lower it. The amount required will depend on speed because as the forward speed of the airplane decreases, the ailerons will become less effective. The elevator control should be held back as far as possible and as firmly as possible until the airplane stops. This provides more positive control with tailwheel steering, tends to shorten the after landing roll, and prevents bouncing and skipping. If available runway permits, the speed of the airplane should be allowed to dissipate in a normal manner by the friction and drag of the wheels on the ground. Brakes may be used if needed to help slow the airplane. After the airplane has been slowed sufficiently and has been turned onto a taxiway or clear of the landing area, it should be brought to a complete stop. Only after this is done should the pilot retract the flaps and perform other checklist items. Crosswind landing. If the crab method of drift correction has been used throughout the final approach and round out, the crab must be removed before touchdown by applying rudder to align airplane's longitudinal axis with its direction of movement. This requires timely and accurate action. Failure to accomplish this results in severe side loads being imposed on the landing gear and imparts ground looping tendencies. If the wing-low method is used, the crosswind correction, aileron into the wind and opposite rudder, should be maintained throughout the round-out and the touchdown made on the upwind main wheel. During gusty or high wind conditions, prompt adjustments must be made in the crosswind correction to assure that the airplane does not drift as it touches down. As the forward speed decreases after initial contact, the weight of the airplane will cause the downwind main wheel to gradually settle onto the runway. An adequate amount of power should be used to maintain the proper airspeed throughout the approach, and the throttle should be retarded to idling position after the main wheels contact the landing surface. Care must be exercised in closing the throttle before the pilot is ready for touchdown, because the sudden or premature closing of the throttle may cause a sudden increase in the descent rate that could result in a hard landing. Crosswind after landing roll. Particularly during the after landing roll, special attention must be given to maintaining directional control by the use of rudder and tailwheel steering, while keeping the upwind wing from rising by the use of aileron. Characteristically, an airplane has a greater profile or side area behind the main landing gear than forward of it. See Figure 13-3. With the main wheels acting as a pivot point and the greater surface area exposed to the crosswind behind that pivot point, the airplane will tend to turn or weather vane into the wind. This weather vaning tendency is more prevalent in the tailwheel type because the airplane's surface area behind the main landing gear is greater than in nosewheel type airplanes. Pilots should be familiar with the crosswind component of each airplane they fly and avoid operations in wind conditions that exceed the capability of the airplane as well as their own limitations. While the airplane is decelerating during the after landing roll, more aileron must be applied to keep the upwind wing from rising. Since the airplane is slowing down, there is less airflow around the ailerons and they become less effective. At the same time, the relative wind is becoming more of a crosswind and exerting a greater lifting force on the upwind wing. Consequently, when the airplane is coming to a stop, the aileron control must be held fully toward the wind. Wheel landing. Landings from power approaches in turbulence or in crosswinds should be such that the touchdown is made with the airplane in approximately level flight attitude. The touchdown should be made smoothly on the main wheels with the tailwheel held clear of the runway. This is called a wheel landing and requires careful timing and control usage to prevent bouncing. These wheel landings can be best accomplished by holding the airplane in level flight attitude until the main wheels touch, then immediately but smoothly retarding the throttle and holding sufficient forward elevator pressure to hold the main wheels on the ground. The airplane should never be forced onto the ground by excessive forward pressure. If the touchdown is made at too high a rate of descent as the main wheels strike the landing surface, the tail is forced down by its own weight. In turn, when the tail is forced down, the wing's angle of attack increases, resulting in a sudden increase in lift, and the airplane may become airborne again. Then, as the airplane's speed continues to decrease, the tail may again lower onto the runway. If the tail is allowed to settle too quickly, the airplane may again become airborne. This process, often called porpoising, usually intensifies even though the pilot tries to stop it. The best corrective action is to execute a go-around procedure. Short field landing. Upon touchdown, the airplane should be firmly held in a three-point attitude. This will provide aerodynamic braking by the wings. Immediately upon touchdown and closing the throttle, the brakes should be applied evenly and firmly to minimize the after landing roll. The airplane should be stopped within the shortest possible distance consistent with safety. Soft field landing. The tailwheels should touch down simultaneously with or just before the main wheels, and should then be held down by maintaining firm back elevator pressure throughout the landing roll. This will minimize any tendency for the airplane to nose over and will provide aerodynamic braking. The use of brakes on a soft field is not needed because the soft or rough surface itself will provide sufficient reduction in the airplane's forward speed. Often it will be found that upon landing on a very soft field, the pilot will need to increase power to keep the airplane moving and from becoming stuck in the soft surface. Ground loop. A ground loop is an uncontrolled turn during ground operation that may occur while taxiing or taking off, but especially during the after landing roll. It is not always caused by drift or weather vaning, although these things may cause the initial swerve. Careless use of the rudder, an uneven ground surface, or a soft spot that retards one main wheel of the airplane may also cause a swerve. In any case, the initial swerve tends to cause the airplane to ground loop. Due to the characteristics of an airplane equipped with a tailwheel, the forces that cause a ground loop increase as the swerve increases. The initial swerve develops inertia, and this, acting at the CG, which is located behind the main wheels, swerves the airplane even more. If allowed to develop, the force produced may become great enough to tip the airplane until one wing strikes the ground. If the airplane touches down while drifting or in a crab, the pilot should apply aileron toward the high wing and stop the swerve with the rudder. Brakes should be used to correct for turns or swerves only when the rudder is inadequate. The pilot must exercise caution when applying corrective brake action because it is very easy to over-control and aggravate the situation. If brakes are used, sufficient brake should be applied on the low wing wheel, outside of the turn, to stop the swerve. When the wings are approximately level, the new direction must be maintained until the airplane has slowed to taxi speed or has stopped. End of Chapter 13.
Chapter 14, Part 1 of Volume 2 of Airplane Flying Handbook, FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Airplane Flying Handbook by the FAA. Transition to Turbopropeller-Powered Airplanes. Part 1, General. The turbopropeller-powered airplane flies and handles just like any other airplane of comparable size and weight. The aerodynamics are the same. The major differences between flying a turboprop and other non-turbine-powered airplanes are found in the power plant and systems. The power plant is different and requires operating procedures that are unique to gas turbine engines. But so too are other systems such as the electrical system, hydraulics, environmental, flight control, rain and ice protection, and avionics. The turbopropeller-powered airplane also has the advantage of being equipped with a constant speed, full feathering, and reversing propeller, something normally not found on piston-powered airplanes. The gas turbine engine. Both piston, reciprocating engines and gas turbine engines are internal combustion engines. They have a similar cycle of operation that consists of induction, compression, combustion, expansion, and exhaust. In a piston engine, each of these events is a separate distinct occurrence in each cylinder. Also, in a piston engine, an ignition event must occur during each cycle, in each cylinder. Unlike reciprocating engines, in gas turbine engines, these phases of power occur simultaneously and continuously, instead of one cycle at a time. Additionally, ignition occurs during the starting cycle and is continuous thereafter. The basic gas turbine engine contains 4 sections: intake, compression, combustion, and exhaust. See Figure 14-1. To start the engine, the compressor section is rotated by an electrical starter on small engines or an air-driven starter on large engines. As compressor RPM accelerates, air is brought in through the inlet duct, compressed to a high pressure, and delivered to the combustion section, combustion chambers. Fuel is then injected by a fuel controller through spray nozzles and ignited by igniter plugs. Not all of the compressed air is used to support combustion. Some of the compressed air bypasses the burner section and circulates within the engine to provide internal cooling. The fuel-air mixture in the combustion chamber is then burned in a continuous combustion process and produces a very high temperature, typically around 4,000 degrees Fahrenheit, which heats the entire air mass to 1,600 to 2,400 degrees Fahrenheit. The mixture of hot air and gases expands and is directed to the turbine blades, forcing the turbine section to rotate, which in turn drives the compressor by means of a direct shaft. After powering the turbine section, the high-velocity excess exhaust exits the tailpipe or exhaust section. Once the turbine section is powered by gases from the burner section, the starter is disengaged, and the igniters are turned off. Combustion continues until the engine is shut down by turning off the fuel supply. High-pressure exhaust gases can be used to provide jet thrust, as in a turbojet engine, or the gases can be directed through an additional turbine to drive a propeller through reduction gearing, as in a turbopropellor, turboprop engine. Turboprop engines. The turbojet engine excels the reciprocating engine in top speed and altitude performance. On the other hand, the turbojet engine has limited takeoff and initial climb performance, as compared to that of a reciprocating engine. In the matter of takeoff and initial climb performance, the reciprocating engine is superior to the turbojet engine. Turbojet engines are most efficient at high speeds and high altitudes, while propellers are most efficient at slow and medium speeds, less than 400 miles per hour. Propellers also improve takeoff and climb performance. The development of the turboprop engine was an attempt to combine in one engine the best characteristics of both the turbojet and propeller-driven reciprocating engine. The turboprop engine offers several advantages over other types of engines, such as lightweight, mechanical reliability due to relatively few moving parts, simplicity of operation, minimum vibration, high power per unit of weight, use of propeller for takeoff and landing. Turboprop engines are most efficient at speeds between 250 and 400 miles per hour, and altitudes between 18,000 and 30,000 feet. They also perform well at the slow speeds required for takeoff and landing, and are fuel efficient. The minimum specific fuel consumption of the turboprop engine is normally available in the altitude range of 25,000 feet up to the tropopause. The power output of a piston engine is measured in horsepower, and is determined primarily by RPM and manifold pressure. The power of a turboprop engine, however, is measured in shaft horsepower, SHP. Shaft horsepower is determined by the RPM and the torque, twisting moment, applied to the propeller shaft. Since turboprop engines are gas turbine engines, some jet thrust is produced by exhaust leaving the engine. This thrust is added to the shaft horsepower to determine the total engine power, or equivalent shaft horsepower, ESHP. Jet thrust usually accounts for less than 10% of the total engine power. Although the turboprop engine is more complicated and heavier than a turbojet engine of equivalent size and power, it will deliver more thrust at low subsonic air speeds. However, the advantages decrease as flight speed increases. In normal cruising speed ranges, the propulsive efficiency, output divided by input, of a turboprop decreases as speed increases. The propeller of a typical turboprop engine is responsible for roughly 90% of the total thrust under sea-level conditions on a standard day. The excellent performance of a turboprop during takeoff and climb is the result of the ability of the propeller to accelerate a large mass of air while the airplane is moving at a relatively low ground and flight speed. Turboprop, however, should not be confused with turbo-supercharged or similar terminology. All turbine engines have a similarity to normally aspirated, non-supercharged reciprocating engines, in that maximum available power decreases almost as a direct function of increased altitude. Although power will decrease as the airplane climbs to higher altitudes, engine efficiency in terms of specific fuel consumption, expressed as pounds of fuel consumed per horsepower per hour, will be increased. Decreased specific fuel consumption plus the increased true airspeed at higher altitudes is a definite advantage of a turboprop engine. All turbine engines, turboprop or turbojet, are defined by limiting temperatures, rotational speeds, and, in the case of turboprops, torque. Depending on the installation, the primary parameter for power setting might be temperature, torque, fuel flow, or RPM, either propeller RPM, gas generator, compressor RPM, or both. In cold weather conditions, torque limits can be exceeded, while temperature limits are still within acceptable range. While in hot weather conditions, temperature limits may be exceeded without exceeding torque limits. In any weather, the maximum power setting of a turbine engine is usually obtained with the throttles positioned somewhat aft of the full forward position. The transitioning pilot must understand the importance of knowing and observing limits on turbine engines. An over-temp or over-torque condition that lasts for more than a very few seconds can literally destroy internal engine components. Turboprop engine types. Fixed shaft. One type of turboprop engine is the fixed shaft constant speed type, such as the Garrett TPE 331. See Figure 14-2. In this type engine, ambient air is directed to the compressor section through the engine inlet. An acceleration-diffusion process in the two-stage compressor increases air pressure and directs it rearward to a combustor. The combustor is made up of a combustion chamber, a transition liner, and a turbine plenum. Atomized fuel is added to the air in the combustion chamber. Air also surrounds the combustion chamber to provide for cooling and insulation of the combustor. The gas mixture is initially ignited by high-energy igniter plugs, and the expanding combustion gases flow to the turbine. The energy of the hot, high-velocity gases is converted to torque on the main shaft by the turbine rotors. The reduction gear converts the high RPM, low torque of the main shaft to low RPM, high torque to drive the accessories and the propeller. The spent gases leaving the turbine are directed to the atmosphere by the exhaust pipe. Only about 10% of the air which passes through the engine is actually used in the combustion process. Up to approximately 20% of the compressed air may be bled off for the purpose of heating, cooling, cabin pressurization, and pneumatic systems. Over half the engine power is devoted to driving the compressor, and it is the compressor which can potentially produce very high drag in the case of a failed windmilling engine. In the fixed shaft constant speed engine, the engine RPM may be varied within a narrow range of 96% to 100%. During ground operation, the RPM may be reduced to 70%. In flight, the engine operates at a constant speed, which is maintained by the governing section of the propeller. Power changes are made by increasing fuel flow and propeller blade angle rather than engine speed. An increase in fuel flow causes an increase in temperature and a corresponding increase in energy available to the turbine. The turbine absorbs more energy and transmits it to the propeller in the form of torque. The increased torque forces the propeller blade angle to be increased to maintain the constant speed. Turbine temperature is a very important factor to be considered in power production. It is directly related to fuel flow and thus to the power produced. It must be limited because of strength and durability of the material in the combustion and turbine section. The control system schedules fuel flow to produce specific temperatures and to limit those temperatures so that the temperature tolerances of the combustion and turbine sections are not exceeded. The engine is designed to operate for its entire life at 100%. All of its components, such as compressors and turbines, are most efficient when operated at or near the RPM design point. Power plant, engine, and propeller control is achieved by means of a power lever and a condition lever for each engine. See Figure 14-3. There is no mixture control and/or RPM lever as found on piston engine airplanes. On the fixed shaft, constant speed turboprop engine, the power lever is advanced or retarded to increase or decrease forward thrust. The power lever is also used to provide reverse thrust. The condition lever sets the desired engine RPM within a narrow range between that appropriate for ground operations and flight. Power plant instrumentation in a fixed shaft turboprop engine typically consists of the following basic indicator. See Figure 14-4. Torque or horsepower, ITT, interturbine temperature, fuel flow, RPM. Torque developed by the turbine section is measured by a torque sensor. The torque is then reflected on a cockpit horsepower gauge, calibrated in horsepower times 100. Interturbine temperature, ITT, is a measurement of the combustion gas temperature between the first and second stages of the turbine section. The gauge is calibrated in degrees Celsius. propeller RPM is reflected on a cockpit tachometer as a percentage of maximum RPM. Normally, a vernier indicator on the gauge dial indicates RPM in 1% graduations as well. The fuel flow indicator indicates fuel flow rate in pounds per hour. Propeller feathering in a fixed-shaft constant-speed turboprop engine is normally accomplished with the condition lever. An engine failure in this type engine, however, will result in a serious drag condition due to the large power requirements of the compressor being absorbed by the propeller. This could create a serious airplane control problem in twin-engine airplanes unless the failure is recognized immediately and the affected propeller feathered. For this reason, the fixed-shaft turboprop engine is equipped with negative torque sensing, NTS. Negative torque sensing is a condition wherein propeller torque drives the engine and the propeller is automatically driven to high pitch to reduce drag. The function of the negative torque sensing system is to limit the torque the engine can extract from the propeller during windmilling and thereby prevent large drag forces on the airplane. The NTS system causes a movement of the propeller blades automatically toward their feathered position, should the engine suddenly lose power while in flight. The NTS system is an emergency backup system in the event of sudden engine failure. It is not a substitution for the feathering device controlled by the condition lever. Split-shaft, free turbine engine. In a free-power turbine engine, such as a Pratt & Whitney PT6 engine, the propeller is driven by a separate turbine through reduction gearing. The propeller is not on the same shaft as a basic engine turbine and compressor. See Figure 14-5. Unlike the fixed-shaft engine, in the split-shaft engine, the propeller can be feathered in flight or on the ground with the basic engine still running. The free-power turbine design allows the pilot to select a desired propeller governing RPM, regardless of basic engine RPM. A typical free-power turbine engine has two independent counter-rotating turbines. One turbine drives the compressor, while the other drives the propeller through a reduction gearbox. The compressor in the basic engine consists of 3 axial flow compressor stages combined with a single centrifugal compressor stage. The axial and centrifugal stages are assembled on the same shaft and operate as a single unit. Inlet air enters the engine via a circular plenum near the rear of the engine and flows forward through the successive compressor stages. The flow is directed outward by the centrifugal compressor stage through radial diffusers before entering the combustion chamber, where the flow direction is actually reversed. The gases produced by combustion are once again reversed to expand forward through each turbine stage. After leaving the turbines, the gases are collected in a peripheral exhaust scroll and are discharged to the atmosphere through 2 exhaust ports near the front of the engine. A pneumatic fuel control system schedules fuel flow to maintain the power set by the gas generator power lever. Except in the beta range, propeller speed within the governing range remains constant at any selected propeller control lever position through the action of a propeller governor. The accessory drive at the aft end of the engine provides power to drive fuel pumps, fuel control, oil pumps, a starter generator, and a tachometer transmitter. At this point, the speed of the drive, N1, is the true speed of the compressor side of the engine, approximately 37,500 RPM. Power plant, engine, and propeller operation is achieved by 3 sets of controls for each engine: the power lever, propeller lever, and condition lever. See Figure 14-6. The power lever serves to control engine power in the range from idle through takeoff power. Forward or aft motion of the power lever increases or decreases gas generator RPM, N1, and thereby increases or decreases engine power. The propeller lever is operated conventionally and controls the constant-speed propellers through the primary governor. The propeller RPM range is normally from 1,500 to 1,900. The condition lever controls the flow of fuel to the engine. Like the mixture lever in a piston-powered airplane, the condition lever is located at the far right of the power quadrant. But the condition lever on a turboprop engine is really just an on-off valve for delivering fuel. There are high idle and low idle positions for ground operations, but condition levers have no metering function. Leaning is not required in turbine engines. This function is performed automatically by a dedicated fuel control unit. Engine instruments in a split-shaft free-turbine engine typically consist of the following basic indicators. See Figure 14-7. ITT, Interstage Turbine Temperature Indicator, Torque Meter, Propeller Tachometer, N1, Gas Generator Tachometer, Fuel Flow Indicator, Oil Temperature Pressure Indicator. The ITT indicator gives an instantaneous reading of engine gas temperature between the compressor turbine and the power turbines. The torque meter responds to power lever movement and gives an indication in foot-pounds, Ft/lb, of the torque being applied to the propeller. Because in the free turbine engine, the propeller is not attached physically to the shaft of the gas turbine engine, two tachometers are justified, one for the propeller and one for the gas generator. The propeller tachometer is read directly in revolutions per minute. The N1, or gas generator, is read in percent of RPM. In the Pratt & Whitney PT6 engine, it is based on a figure of 37,000 RPM at 100%. Maximum continuous gas generator is limited to 38,100 RPM, or 101.5% N1. The ITT indicator and torque meter are used to set takeoff power. Climb and cruise power are established with the torque meter and propeller tachometer while observing ITT limits. Gas generator N1 operation is monitored by the gas generator tachometer. Proper observation and interpretation of these instruments provide an indication of engine performance and condition. End of Chapter 14, Part 1. Chapter 14, Part 2 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Airplane Flying Handbook by the FAA. Transition to turbopropeller-powered airplanes. Part 2. Reverse thrust and beta range operations. The thrust that a propeller provides is a function of the angle of attack at which the air strikes the blades and the speed at which this occurs. The angle of attack varies with the pitch angle of the propeller. So-called flat pitch is the blade position offering minimum resistance to rotation and no net thrust for moving the airplane. Forward pitch produces forward thrust, higher pitch angles being required at higher airplane speeds. The feathered position is the highest pitch angle obtainable. See Figure 14-8. The feathered position produces no forward thrust. The propeller is generally placed in feather only in case of in-flight engine failure to minimize drag and prevent the air from using the propeller as a turbine. In the reverse pitch position, the engine/propeller turns in the same direction as in the normal forward pitch position, but the propeller blade angle is positioned to the other side of flat pitch. See Figure 14-8. In reverse pitch, air is pushed away from the airplane rather than being drawn over it. Reverse pitch results in braking action rather than forward thrust of the airplane. It is used for backing away from obstacles when taxiing, controlling taxi speed, or to aid in bringing the airplane to a stop during the landing roll. Reverse pitch does not mean reverse rotation of the engine. The engine delivers power just the same, no matter which side of flat pitch the propeller blades are positioned. With a turboprop engine, in order to obtain enough power for flight, the power lever is placed somewhere between flight idle, in some engines referred to as high idle, and maximum. The power lever directs signals to a fuel control unit to manually select fuel. The propeller governor selects the propeller pitch needed to keep the propeller/engine on speed. This is referred to as the propeller governing or alpha mode of operation. When positioned aft of flight idle, however, the power lever directly controls propeller blade angle. This is known as the beta range of operation. The beta range of operation consists of power lever positions from flight idle to maximum reverse. Beginning at power lever positions just aft of flight idle, propeller blade pitch angles become progressively flatter with aft movement of the power lever until they go beyond maximum flat pitch and into negative pitch, resulting in reverse thrust. While in a fixed shaft, constant speed engine, the engine speed remains largely unchanged as the propeller blade angles achieve their negative values. On the split shaft PT6 engine, as the negative 5-degree position is reached, further aft movement of the power lever will also result in a progressive increase in engine N1 RPM, until a maximum value of about negative 11 degrees of blade angle and 85% N1 are achieved. Operating in the beta range and/or with reverse thrust requires specific techniques and procedures depending on the particular airplane make and model. There are also specific engine parameters and limitations for operations within this area that must be adhered to. It is essential that a pilot transitioning to turboprop airplanes become knowledgeable and proficient in these areas, which are unique to turbine engine-powered airplanes. Turboprop airplane electrical systems. The typical turboprop airplane electrical system is a 28-volt direct current DC system, which receives power from one or more batteries and a starter/generator for each engine. The batteries may either be of the lead-acid type, commonly used on piston-powered airplanes, or they may be of the nickel-cadmium NiCad type. The NiCad battery differs from the lead-acid type in that its output remains at relatively high power levels for longer periods of time. When the NiCad battery is depleted, however, its voltage drops off very suddenly. When this occurs, its ability to turn the compressor for engine start is greatly diminished, and the possibility of engine damage due to a hot start increases. Therefore, it is essential to check the battery's condition before every engine start. Compared to lead-acid batteries, high-performance NiCad batteries can be recharged very quickly. But the faster the battery is recharged, the more heat it produces. Therefore, NiCad battery-equipped airplanes are fitted with battery overheat annunciator lights, signifying maximum safe and critical temperature thresholds. The DC generators used in turboprop airplanes double as starter motors and are called starter/generators. The starter/generator uses electrical power to produce mechanical torque to start the engine and then uses the engine's mechanical torque to produce electrical power after the engine is running. Some of the DC power produced is changed to 28-volt 400-cycle alternating current AC power for certain avionic, lighting, and indicator synchronization functions. This is accomplished by an electrical component called an inverter. The distribution of DC and AC power throughout the system is accomplished through the use of power distribution buses. These buses, as they are called, are actually common terminals from which individual electrical circuits get their power. See Figure 14-9. Buses are usually named for what they power. Avionics bus, for example, or for where they get their power. Right generator bus, battery bus. The distribution of DC and AC power is often divided into functional groups, buses, that give priority to certain equipment during normal and emergency operations. Main buses serve most of the airplane's electrical equipment. Essential buses feed power to equipment having top priority. See Figure 14-10. Multi-engine turboprop airplanes normally have several power sources, a battery, and at least one generator per engine. The electrical systems are usually designed so that any bus can be energized by any of the power sources. For example, a typical system might have a right and left generator buses powered normally by the right and left engine-driven generators. These buses will be connected by a normally open switch, which isolates them from each other. If one generator fails, power will be lost to its bus, but power can be restored to that bus by closing a bus tie switch. Closing this switch connects the buses and allows the operating generator to power both. Power distribution buses are protected from short circuits and other malfunctions by a type of fuse called a current limiter. In the case of excessive current supplied by any power source, the current limiter will open the circuit and thereby isolate that power source and allow the affected bus to become separated from the system. The other buses will continue to operate normally. Individual electrical components are connected to the buses through circuit breakers. A circuit breaker is a device which opens an electrical circuit when an excess amount of current flows. Operational considerations. As previously stated, a turboprop airplane flies just like any other piston engine airplane of comparable size and weight. It is in the operation of the engines and airplane systems that makes a turboprop airplane different from its piston engine counterpart. Pilot errors in engine and/or systems operation are the most common cause of aircraft damage or mishap. The time of maximum vulnerability to pilot error in any gas turbine engine is during the engine start sequence. Turbine engines are extremely heat sensitive. They cannot tolerate an over-temperature condition for more than a very few seconds without serious damage being done. Engine temperatures get hotter during starting than at any other time. Thus, turbine engines have minimum rotational speeds for introducing fuel into the combustion chambers during startup. Hypervigilant temperature and acceleration monitoring on the part of the pilot remain crucial until the engine is running at a stable speed. Successful engine starting depends on assuring the correct minimum battery voltage before initiating start, or employing a ground power unit, GPU, of adequate output. After fuel is introduced to the combustion chamber during the start sequence, light off and its associated heat rise occur very quickly. Engine temperatures may approach the maximum in a matter of 2 or 3 seconds before the engine stabilizes and temperatures fall into the normal operating range. During this time, the pilot must watch for any tendency of the temperatures to exceed limitations and be prepared to cut off fuel to the engine. An engine tendency to exceed maximum starting temperature limits is termed a hot start. The temperature rise may be preceded by unusually high initial fuel flow, which may be the first indication the pilot has that the engine start is not proceeding normally. Serious engine damage will occur if the hot start is allowed to continue. A condition where the engine is accelerating more slowly than normal is termed a hung start or false start. During a hung start/false start, the engine may stabilize at an engine RPM that is not high enough for the engine to continue to run without help from the starter. This is usually the result of low battery power, or the starter not turning the engine fast enough for it to start properly. Takeoffs in turboprop airplanes are not made by automatically pushing the power lever full forward to the stops. Depending on conditions, takeoff power may be limited by either torque or by engine temperature. Normally, the power lever position on takeoff will be somewhat aft of full forward. Takeoff and departure in a turboprop airplane, especially a twin-engine, cabin-class airplane, should be accomplished in accordance with a standard takeoff and departure profile developed for the particular make and model. See Figure 14-11. The takeoff and departure profile should be in accordance with the airplane manufacturer's recommended procedures as outlined in the FAA-approved Airplane Flight Manual and/or the Pilot's Operating Handbook, AFM/POH. The increased complexity of turboprop airplanes makes the standardization of procedures a necessity for safe and efficient operation. The transitioning pilot should review the profile procedures before each takeoff to form a mental picture of the takeoff and departure process. For any given high horsepower operation, the pilot can expect that the engine temperature will climb as altitude increases at a constant power. On a warm or hot day, maximum temperature limits may be reached at a rather low altitude, making it impossible to maintain high horsepower to higher altitudes. Also, the engine's compressor section has to work harder with decreased air density. Power capability is reduced by high-density altitude, and power use may have to be modulated to keep engine temperature within limits. In a turboprop airplane, the pilot can close the throttle or throttles at any time, without concern for cooling the engine too rapidly. Consequently, rapid descents with the propellers in low pitch can be dramatically steep. Like takeoffs and departures, approach and landing should be accomplished in accordance with a standard approach and landing profile. See Figure 14-12. A stabilized approach is an essential part of the approach and landing process. In a stabilized approach, the airplane, depending on design and type, is placed in a stabilized descent on a glide path ranging from 2.5 to 3.5 degrees. The speed is stabilized at some reference from the AFM/POH. usually 1.25 to 1.30 times the stall speed in approach configuration. The descent rate is stabilized from 500 feet per minute to 700 feet per minute until the landing flare. Landing some turboprop airplanes, as well as some piston twins, can result in a hard, premature touchdown if the engines are idled too soon. This is because large propellers spinning rapidly in low pitch create considerable drag. In such airplanes, it may be preferable to maintain power throughout the landing flare and touchdown. Once firmly on the ground, propeller beta range operation will dramatically reduce the need for braking in comparison to piston airplanes of similar weights. Training considerations. The medium and high altitudes at which turboprop airplanes are flown provide an entirely different environment in terms of regulatory requirements, airspace structure, physiological requirements, and even meteorology. The pilot transitioning to turboprop airplanes, particularly those who are not familiar with operations in the high/medium altitude environment, should approach turboprop transition training with this in mind. Thorough ground training should cover all aspects of high/medium altitude flight, including the flight environment, weather, flight planning and navigation, physiological aspects of high-altitude flight, oxygen and pressurization system operation, and high-altitude emergencies. Flight training should prepare the pilot to demonstrate a comprehensive knowledge of airplane performance, systems, emergency procedures, and operating limitations, along with a high degree of proficiency in performing all flight maneuvers and in-flight emergency procedures. The training outline below covers the minimum information needed by pilots to operate safely at high altitudes. A. Ground training. 1. The high-altitude flight environment. A. Airspace. B. Title 14 of the Code of Federal Regulations, 14 CFR, Section 91.211, Requirements for use of supplemental oxygen. 2. Weather. A. The atmosphere. B. Winds and clear air turbulence. C. Icing. 3. Flight planning and navigation. A. Flight planning. B. Weather charts. C. Navigation. D. Navaids. 4. Physiological training. A. Respiration. B. Hypoxia. C. Effects of prolonged oxygen use. D. Decompression sickness. E. Vision. F. Altitude chamber, optional. 5. High-altitude systems and components. A. Oxygen and oxygen equipment. B. Pressurization systems. C. High-altitude components. 6. Aerodynamics and performance factors. A. Acceleration. B. G-forces. C. Mach tuck and Mach critical, turbojet airplanes. 7. Emergencies. A. Decompression. B. Donning of oxygen masks. C. Failure of oxygen mask or complete loss of oxygen supply/system. D. In-flight fire. E. Flight into severe turbulence or thunderstorms. B. Flight training. 1. Pre-flight briefing. 2. Pre-flight planning. A. Weather briefing and considerations. B. Course plotting. C. Airplane flight manual. D. Flight plan. 3. Pre-flight inspection. A. Functional test of oxygen system, including the verification of supply and pressure, regulator operation, oxygen flow, mask fit, and cockpit and air traffic control, ATC communication using mask microphones. 4. Engine start procedures, run-up, takeoff, and initial climb. 5. Climb to high altitude and normal cruise operations while operating above 25,000 feet MSL. 6. Emergencies. A. Simulated rapid decompression, including the immediate donning of oxygen masks. B. Emergency descent. 7. Planned descents. 8. Shutdown procedures. 9. Post-flight discussion. End of Chapter 14, Part 2.
Chapter 15, Part 1 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook by the FAA. Transition to Jet-Powered Airplanes, Part 1. General. This chapter contains an overview of jet-powered airplane operations. It is not meant to replace any portion of a formal jet airplane qualification course. Rather, the information contained in this chapter is meant to be a useful preparation for and a supplement to formal and structured jet airplane qualification training. The intent of this chapter is to provide information on the major differences a pilot will encounter when transitioning to jet-powered airplanes. In order to achieve this in a logical manner, the major differences between jet-powered airplanes and piston-powered airplanes have been approached by addressing two distinct areas: differences in technology, or how the airplane itself differs, and differences in pilot technique, or how the pilot deals with the technological differences through the application of different techniques. If any of the information in this chapter conflicts with information contained in the FAA-approved Airplane Flight Manual for a particular airplane, the Airplane Flight Manual takes precedence. Jet engine basics. A jet engine is a gas turbine engine. A jet engine develops thrust by accelerating a relatively small mass of air to very high velocity, as opposed to a propeller, which develops thrust by accelerating a much larger mass of air to a much slower velocity. As stated in Chapter 14, both piston and gas turbine engines are internal combustion engines and have a similar basic cycle of operation, that is, induction, compression, combustion, expansion, and exhaust. Air is taken in and compressed, and fuel is injected and burned. The hot gases then expand and supply a surplus of power over that required for compression, and are finally exhausted. In both piston and jet engines, the efficiency of the cycle is improved by increasing the volume of air taken in and the compression ratio. Part of the expansion of the burned gases takes place in the turbine section of the jet engine, providing the necessary power to drive the compressor, while the remainder of the expansion takes place in the nozzle of the tailpipe in order to accelerate the gas to a high-velocity jet, thereby producing thrust. See Figure 15-1. In theory, the jet engine is simpler and more directly converts thermal energy, the burning and expansion of gases, into mechanical energy, thrust. The piston, or reciprocating engine, with all of its moving parts, must convert the thermal energy into mechanical energy and then finally into thrust by rotating a propeller. One of the advantages of the jet engine over the piston engine is the jet engine's capability of producing much greater amounts of thrust horsepower at the high altitudes and high speeds. In fact, turbojet engine efficiency increases with altitude and speed. Although the propeller-driven airplane is not nearly as efficient as the jet, particularly at the higher altitudes and cruising speeds required in modern aviation, one of the few advantages the propeller-driven airplane has over the jet is that maximum thrust is available almost at the start of the takeoff roll. Initial thrust output of the jet engine on takeoff is relatively lower and does not reach peak efficiency until the higher speeds. The fanjet or turbofan engine was developed to help compensate for this problem and is, in effect, a compromise between the pure jet engine, turbojet, and the propeller engine. Like other gas turbine engines, the heart of the turbofan engine is the gas generator, the part of the engine that produces the hot, high-velocity gases. Similar to turboprops, turbofans have a low-pressure turbine section that uses most of the energy produced by the gas generator. The low-pressure turbine is mounted on a concentric shaft that passes through the hollow shaft of the gas generator, connecting it to a ducted fan at the front of the engine. See Figure 15-2. Air enters the engine, passes through the fan, and splits into two separate paths. Some of it flows around, bypasses, the engine core, hence its name, bypass air. The air drawn into the engine for the gas generator is the core airflow. The amount of air that bypasses the core compared to the amount drawn into the gas generator determines a turbofan's bypass ratio. Turbofans efficiently convert fuel into thrust because they produce low-pressure energy spread over a large fan disk area. While a turbo engine uses all of the gas generator's output to produce thrust in the form of a high-velocity exhaust gas jet, cool, low-velocity bypass air produces between 30% and 70% of the thrust produced by a turbofan engine. The fan jet concept increases the total thrust of the jet engine, particularly at the lower speeds and altitudes. Although efficiency at the higher altitudes is lost, turbofan engines are subject to a large lapse in thrust with increasing altitude. The turbofan engine increases acceleration, decreases the takeoff roll, improves initial climb performance, and often has the effect of decreasing specific fuel consumption. Operating the jet engine. In a jet engine, thrust is determined by the amount of fuel injected into the combustion chamber. The power controls on most turbojet and turbofan-powered airplanes consist of just one thrust lever for each engine because most engine control functions are automatic. The thrust lever is linked to a fuel control and/or electronic engine computer that meters fuel flow based upon RPM, internal temperatures, ambient conditions, and other factors. See Figure 15-3. In a jet engine, each major rotating section usually has a separate gauge devoted to monitoring its speed of rotation. Depending on the make and model, a jet engine may have an N1 gauge that monitors the low-pressure compressor section and/or fan speed in turbofan engines. The gas generator section may be monitored by an N2 gauge, while triple spool engines may have an N3 gauge as well. Each engine section rotates at many thousands of RPM. Their gauges, therefore, are calibrated in percent of RPM rather than actual RPM for ease of display and interpretation. See Figure 15-4. The temperature of turbine gases must be closely monitored by the pilot. As in any gas turbine engine, exceeding temperature limits, even for a very few seconds, may result in serious heat damage to turbine blades and other components. Depending on the make and model, gas temperatures can be measured at a number of different locations within the engine. The associated engine gauges, therefore, have different names according to their location. For instance, exhaust gas temperature, EGT, the temperature of the exhaust gases as they enter the tailpipe after passing through the turbine. Turbine inlet temperature, TIT, the temperature of the gases from the combustion section of the engine as they enter the first stage of the turbine. TIT is the highest temperature inside a gas turbine engine and is one of the limiting factors of the amount of power the engine can produce. TIT, however, is difficult to measure. EGT, therefore, which relates to TIT, is normally the parameter measured. Interstage turbine temperature, ITT, the temperature of the gases between the high-pressure and low-pressure turbine wheels. Turbine outlet temperature, TOT. Like EGT, turbine outlet temperature is taken aft of the turbine wheel, or wheels. Jet engine ignition. Most jet engine ignition systems consist of two igniter plugs, which are used during the ground or air starting of the engine. Once the start is completed, this ignition either automatically goes off or is turned off, and from this point on, the combustion in the engine is a continuous process. Continuous ignition. An engine is sensitive to the flow characteristics of the air that enters the intake of the engine nacelle. So long as the flow of air is substantially normal, the engine will continue to run smoothly. However, particularly with rear-mounted engines that are sometimes in a position to be affected by disturbed airflow from the wings, there are some abnormal flight situations that could cause a compressor stall or flame-out of the engine. These abnormal flight conditions would usually be associated with abrupt pitch changes, such as might be encountered in severe turbulence or a stall. In order to avoid the possibility of engine flame-out from the above conditions, or from other conditions that might cause ingestion problems, such as heavy rain, ice, or possible bird strike, most jet engines are equipped with a continuous ignition system. This system can be turned on and used continuously whenever the need arises. In many jets, as an added precaution, this system is normally used during takeoffs and landings. Many jets are also equipped with an automatic ignition system that operates both igniters whenever the airplane's stall warning or stick shaker is activated. Fuel heaters. Because of the high altitudes and extremely cold outside air temperatures in which the jet flies, it is possible to supercool the jet fuel to the point that the small particles of water suspended in the fuel can turn to ice crystals and clog the fuel filters leading to the engine. For this reason, jet engines are normally equipped with fuel heaters. The fuel heater may be of the automatic type, which constantly maintains the fuel temperature above freezing, or they may be manually controlled by the pilot from the cockpit. Setting power. On some jet airplanes, thrust is indicated by an engine pressure ratio, EPR, gauge. Engine pressure ratio can be thought of as being equivalent to the manifold pressure on the piston engine. Engine pressure ratio is the difference between turbine discharge pressure and engine inlet pressure. It is an indication of what the engine has done with the raw air scooped in. For instance, an EPR setting of 2.24 means that the discharge pressure relative to the inlet pressure is 2.24 to 1. On these airplanes, the EPR gauge is the primary reference used to establish power settings. See Figure 15-5. Fan speed, N1, is the primary indication of thrust on most turbofan engines. Fuel flow provides a secondary thrust indication, and cross-checking for proper fuel flow can help in spotting a faulty N1 gauge. Turbofans also have a gas generator turbine tachometer, N2. They are used mainly for engine starting and some system functions. In setting power, it is usually the primary power reference, EPR or N1, that is most critical and will be the gauge that will first limit the forward movement of the thrust levers. However, there are occasions where the limits of either RPM or temperature can be exceeded. The rule is, movement of the thrust levers must be stopped and power set at whichever the limits of EPR, RPM, or temperature is reached first. Thrust-to-thrust lever relationship. In a piston engine propeller-driven airplane, thrust is proportional to RPM, manifold pressure, and propeller blade angle, with manifold pressure being the most dominant factor. At a constant RPM, thrust is proportional to throttle lever position. In a jet engine, however, thrust is quite disproportional to thrust lever position. This is an important difference that the pilot transitioning into jet-powered airplanes must become accustomed to. On a jet engine, thrust is proportional to RPM, mass flow, and temperature, fuel/air ratio. These are matched, and a further variation of thrust results from the compressor efficiency at varying RPM. The jet engine is most efficient at high RPM, where the engine is designed to be operated most of the time. As RPM increases, mass flow, temperature, and efficiency also increase. Therefore, much more thrust is produced per increment of throttle movement near the top of the range than near the bottom. One thing that will seem different to the piston pilot transitioning into jet-powered airplanes is the rather large amount of thrust lever movement between the flight idle position and full power as compared to the small amount of movement of the throttle in the piston engine. For instance, an inch of throttle movement on a piston may be worth 400 horsepower wherever the throttle may be. On a jet, an inch of thrust lever movement at a low RPM may be worth only 200 pounds of thrust, but at a high RPM, that same inch of movement might amount to closer to 2,000 pounds of thrust. Because of this, in a situation where significantly more thrust is needed and the jet engine is at low RPM, it will not do much good to merely inch the thrust lever forward. Substantial thrust lever movement is in order. This is not to say that rough or abrupt thrust lever action is standard operating procedure. If the power setting is already high, it may take only a small amount of movement. However, there are two characteristics of the jet engine that work against the normal habits of the piston engine pilot. One is the variation of thrust with RPM, and the other is the relatively slow acceleration of the jet engine. Variation of thrust with RPM. Whereas piston engines normally operate in the range of 40% to 70% of available RPM, jets operate most efficiently in the 85% to 100% range, with a flight idle RPM of 50% to 60%. The range from 90% to 100% in jets may produce as much thrust as the total available at 70%. See Figure 15-6. Slow acceleration of the jet engine. In a propeller-driven airplane, the constant-speed propeller keeps the engine turning at a constant RPM within the governing range, and power is changed by varying the manifold pressure. Acceleration of the piston from idle to full power is relatively rapid, somewhere on the order of 3 to 4 seconds. The acceleration on the different jet engines can vary considerably, but is usually much slower. Efficiency in a jet engine is higher at high RPM, where the compressor is working closest to its optimum conditions. At low RPM, the operating cycle is generally inefficient. If the engine is operating at normal approach RPM, and there is a sudden requirement for increased thrust, the jet engine will respond immediately, and full thrust can be achieved in about 2 seconds. However, at low RPM, sudden full power application will tend to overfuel the engine, resulting in possible compressor surge, excessive turbine temperatures, compressor stall, and/or flame out. To prevent this, various limiters, such as compressor bleed valves, are contained in the system and serve to restrict the engine until it is at an RPM at which it can respond to a rapid acceleration demand without distress. This critical RPM is most noticeable when the engine is at idle RPM and the thrust lever is rapidly advanced to a high power position. Engine acceleration is initially very slow, but changes to very fast after about 78% RPM is reached. See Figure 15-7. Even though engine acceleration is nearly instantaneous after about 78% RPM, total time to accelerate from idle RPM to full power may take as much as 8 seconds. For this reason, most jets are operated at a relatively high RPM during the final approach to landing or at any other time that immediate power may be needed. Jet engine efficiency. Maximum operating altitudes for general aviation turbojet airplanes now reach 51,000 feet. The efficiency of the jet engine at high altitudes is the primary reason for operating in the high-altitude environment. The specific fuel consumption of jet engines decreases as the outside air temperature decreases for constant engine RPM and true airspeed, TAS. Thus, by flying at a high altitude, the pilot is able to operate at flight levels where fuel economy is best and with the most advantageous cruise speed. For efficiency, jet airplanes are typically operated at high altitudes where cruise is usually very close to RPM or exhaust gas temperature limits. At high altitudes, little excess thrust may be available for maneuvering. Therefore, it is often impossible for the jet airplane to climb and turn simultaneously, and all maneuvering must be accomplished within the limits of available thrust and without sacrificing stability and controllability. Absence of propeller effect. The absence of a propeller has a significant effect on the operation of jet-powered airplanes that the transitioning pilot must become accustomed to. The effect is due to the absence of lift from the propeller slipstream and the absence of propeller drag. Absence of propeller slipstream. A propeller produces thrust by accelerating a large mass of air rearwards, and, especially with wing-mounted engines, this air passes over a comparatively large percentage of the wing area. On a propeller-driven airplane, the lift that the wing develops is the sum of the lift generated by the wing area not in the wake of the propeller, as a result of airplane speed, and the lift generated by the wing area influenced by the propeller slipstream. By increasing or decreasing the speed of the slipstream air, therefore, it is possible to increase or decrease the total lift on the wing without changing airspeed. For example, a propeller-driven airplane that is allowed to become too low and too slow on an approach is very responsive to a quick blast of power to salvage the situation. In addition to increasing lift at a constant airspeed, stalling speed is reduced with power on. A jet engine, on the other hand, also produces thrust by accelerating a mass of air rearward, but this air does not pass over the wings. There is therefore no lift bonus at increased power at constant airspeed, and no significant lowering of power on stall speed. In not having propellers, the jet-powered airplane is minus two assets. It is not possible to produce increased lift instantly by simply increasing power. It is not possible to lower stall speed by simply increasing power. The 10-knot margin, roughly the difference between power off and power on stall speed on a propeller-driven airplane for a given configuration, is lost. Add the poor acceleration response of the jet engine, and it becomes apparent that there are three ways in which the jet pilot is worse off than the propeller pilot. For these reasons, there is a marked difference between the approach qualities of a piston engine airplane and a jet. In a piston engine airplane, there is some room for error. Speed is not too critical, and a burst of power will salvage an increasing sink rate. In a jet, however, there is little room for error. If an increasing sink rate develops in a jet, the pilot must remember 2 points in the proper sequence. 1. Increased lift can be gained only by accelerating airflow over the wings, and this can be accomplished only by accelerating the entire airplane. 2. The airplane can be accelerated, assuming altitude loss cannot be afforded, only by a rapid increase in thrust, and here the slow acceleration of the jet engine, possibly up to 8 seconds, becomes a factor. Salvaging an increasing sink rate on an approach in a jet can be a very difficult maneuver. The lack of ability to produce instant lift in the jet, along with the slow acceleration of the engine, necessitates a stabilized approach to a landing where full landing configuration, constant airspeed, controlled rate of descent, and relatively high power settings are maintained until over the threshold of the runway. This allows for almost immediate response from the engine in making minor changes in the approach speed or rate of descent, and makes it possible to initiate an immediate go-around or missed approach if necessary. Absence of propeller drag. When the throttles are closed on a piston-powered airplane, the propellers create a vast amount of drag, and airspeed is immediately decreased or altitude is lost. The effect of reducing power to idle on the jet engine, however, produces no such drag effect. In fact, at an idle power setting, the jet engine still produces forward thrust. The main advantage is that the jet pilot is no longer faced with a potential drag penalty of a runaway propeller or a reversed propeller. A disadvantage, however, is the freewheeling effect forward thrust at idle has on the jet. While this occasionally can be used to advantage, such as in a long descent, it is a handicap when it is necessary to lose speed quickly, such as when entering a terminal area or when in a landing flare. The lack of propeller drag, along with the aerodynamically clean airframe of the jet, are new to most pilots, and slowing the airplane down is one of the initial problems encountered by pilots transitioning into jets. End of Chapter 15, Part 1.
Chapter 15, Part 2 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jairus Amar. Airplane Flying Handbook by the FAA. Chapter 15. Speed Margins. The typical piston-powered airplane had to deal with two maximum operating speeds, V and O, maximum structural cruising speed, represented on the airspeed indicator by the upper limit of the green arc. It is, however, permissible to exceed V and O and to operate in the caution range, yellow arc, in certain flight conditions. V and E. Never exceed speed, represented by a red line on the airspeed indicator. These speed margins in the piston airplanes were never of much concern during normal operations because the high drag factors and relatively low cruise power settings kept speeds well below these maximum limits. Maximum speeds in jet airplanes are expressed differently and always define the maximum operating speed of the airplane, which is comparable to the VNE of the piston airplane. These maximum speeds in a jet airplane are referred to as VMO, maximum operating speed expressed in terms of knots; MMO, maximum operating speed expressed in terms of a decimal of Mach speed, speed of sound. To observe both limits VMO and MMO, the pilot of a jet airplane needs both an airspeed indicator and a Mach meter, each with appropriate red lines. In some general aviation jet airplanes, these are combined into a single instrument that contains a pair of concentric indicators, one for the indicated airspeed and the other for indicated Mach number. Each is provided with an appropriate red line. See Figure 15-8. A more sophisticated indicator is used on most jetliners. It looks much like a conventional airspeed indicator, but has a barber pole that automatically moves so as to display the applicable speed limit at all times. Because of the higher available thrust and very low drag design, the jet airplane can very easily exceed its speed margin, even in cruising flight, and in fact in some airplanes, in a shallow climb. The handling qualities in a jet can change drastically when the maximum operating speeds are exceeded. High-speed airplanes designed for subsonic flight are limited to some Mach number below the speed of sound to avoid the formation of shock waves that begin to develop as the airplane nears Mach 1.0. These shock waves, and the adverse effects associated with them, can occur when the airplane speed is substantially below Mach 1.0. The Mach speed at which some portion of the airflow over the wing first equals Mach 1.0 is termed the critical Mach number, Mach crit. This is also the speed at which a shock wave first appears on the airplane. There is no particular problem associated with the acceleration of the airflow up to the point where Mach 1.0 is encountered. However, a shock wave is formed at the point where the airflow suddenly returns to subsonic flow. This shock wave becomes more severe and moves aft on the wing as speed of the wing is increased, and eventually flow separation occurs behind the well-developed shock wave. See Figure 15-9. If allowed to progress well beyond the MMO for the airplane, this separation of air behind the shock wave can result in severe buffeting and possible loss of control, or upset. Because of the changing center of lift of the wing, resulting from the movement of the shock wave, the pilot will experience pitch change tendencies as the airplane moves through the transonic speeds up to and exceeding MMO. See Figure 15-10. For example, as the graph in Figure 15-10 illustrates, initially as speed is increased up to Mach 0.72, the wing develops an increasing amount of lift, requiring a nose-down force or trim to maintain level flight. With increased speed and the aft movement of the shock wave, the wing's center of pressure also moves aft, causing the start of a nose-down tendency, or tuck. By Mach 0.83, the nose-down forces are well developed to a point where a total of 70 pounds of back pressure are required to hold the nose up. If allowed to progress unchecked, Mach tuck may eventually occur. Although Mach tuck develops gradually, if it is allowed to progress significantly, the center of pressure can move so far rear-wind that there is no longer enough elevator authority available to counteract it, and the airplane could enter a steep, sometimes unrecoverable dive. An alert pilot would have observed the high airspeed indications, experienced the onset of buffeting and responded to aural warning devices long before encountering the extreme stick forces shown. However, in the event that corrective action is not taken and the nose allowed to drop, increasing airspeed even further, the situation could rapidly become dangerous. As the Mach speed increases beyond the airplane's MMO, the effects of flow separation and turbulence behind the shockwave become more severe. Eventually, the most powerful forces causing Mach tuck are a result of the buffeting and lack of effective downwash on the horizontal stabilizer because of the disturbed airflow over the wing. This is the primary reason for the development of the T-tail configuration on some jet airplanes, which places the horizontal stabilizer as far as practical from the turbulence of the wings. Also, because of the critical aspects of high altitude/high Mach flight, most jet airplanes capable of operating in the Mach speed ranges are designed with some form of trim and autopilot Mach compensating device, stick puller, to alert the pilot to inadvertent excursions beyond its certificated MMO. Recovery from overspeed conditions. The simplest remedy for an overspeed condition is to ensure that the situation never occurs in the first place. For this reason, the pilot must be aware of all the conditions that could lead to exceeding the airplane's maximum operating speeds. Good attitude instrument flying skills and good power control are essential. The pilot should be aware of the symptoms that will be experienced in the particular airplane as the VMO or MMO is being approached. These may include nose-down tendency and need for back pressure or trim, mild buffeting as airflow separation begins to occur after critical Mach speed, actuation of an aural warning device/stick puller at or just slightly beyond VMO or MMO. The pilot's response to an overspeed condition should be to immediately slow the airplane by reducing the power to flight idle. It will also help to smoothly and easily raise the pitch attitude to help dissipate speed. In fact, this is done automatically through the stick puller device when the high-speed warning system is activated. The use of speed brakes can also aid in slowing the airplane. If, however, the nose-down stick forces have progressed to the extent that they are excessive, some speed brakes will tend to further aggravate the nose-down tendency. Under most conditions, this additional pitch downforce is easily controllable, and since speed brakes can normally be used at any speed, they are a very real asset. A final option would be to extend the landing gear. This will create enormous drag and possibly some nose-up pitch, but there is usually little risk of damage to the gear itself. The pilot transitioning into jet airplanes must be familiar with the manufacturer's recommended procedures for dealing with overspeed conditions, contained in the FAA-approved Airplane Flight Manual for the particular make and model airplane. Mach buffet boundaries. Thus far, only the Mach buffet that results from excessive speed has been addressed. The transitioning pilot, however, should be aware that the Mach buffet is a function of the speed of the airflow over the wing, not necessarily the airspeed of the airplane. Any time that too great a lift demand is made on the wing, whether from too fast an airspeed or from too high an angle of attack near the MMO, the high-speed buffet will occur. However, there are occasions when the buffet can be experienced at much slower speeds, known as low-speed Mach buffet. The most likely situations that could cause the low-speed buffet would be when an airplane is flown at too slow a speed for its weight and altitude, causing a high angle of attack. This very high angle of attack would have the same effect of increasing airflow over the upper surface of the wing, to the point that all of the same effects of the shock waves and buffet would occur as in the high-speed buffet situation. The angle of attack of the wing has the greatest effect on inducing the Mach buffet at either the high or low speed boundaries for the airplane. the conditions that increase the angle of attack, hence the speed of the airflow over the wing and chances of Mach buffet, are high altitudes. The higher the airplane flies, the thinner the air, and the greater the angle of attack required to produce the lift needed to maintain level flight. Heavy weights. The heavier the airplane, the greater the lift required of the wing, and all other things being equal, the greater the angle of attack. G-loading. An increase in the G-loading of the wing results in the same situation as increasing the weight of the airplane. It makes no difference whether the increase in G-forces is caused by a turn, rough control usage, or turbulence. The effect of increasing the wing's angle of attack is the same. An airplane's indicated airspeed decreases in relation to the true airspeed as altitude increases. As the indicated airspeed decreases with altitude, it progressively merges with the low-speed buffet boundary, where pre-stall buffet occurs for the airplane at a load factor of 1.0 g. The point where the high-speed Mach indicated airspeed and low-speed buffet boundary indicated airspeed merge is the airplane's absolute or aerodynamic ceiling. Once an airplane has reached its aerodynamic ceiling, which is higher than the altitude stipulated in the FAA-approved Airplane Flight Manual, the airplane could neither be made to go faster without activating the design stick puller at Mach limit, nor can it be made to go slower without activating the stick shaker or stick pusher. This critical area of the airplane's flight envelope is known as coffin corner. Mach buffet occurs as a result of supersonic airflow on the wing. Stall buffet occurs at angles of attack that produce airflow disturbances, burbling, over the upper surface of the wing, which decreases lift. As density altitude increases, the angle of attack that is required to produce an airflow disturbance over the top of the wing is reduced until the density altitude is reached, where Mach buffet and stall buffet converge. Coffin corner. When this phenomenon is encountered, serious consequences may result, causing loss of airplane control. Increasing either gross weight or load factor, G factor, will increase the low-speed buffet and decrease Mach buffet speeds. A typical jet airplane flying at 51,000 feet altitude at 1.0 g may encounter Mach buffet slightly above the airplane's MMO, 0.82 Mach, and low-speed buffet at 0.60 Mach. However, only 1.4 g, an increase of only 0.4 g, may bring on buffet at the optimum speed of 0.73 Mach, and any change in airspeed, bank angle, or gust loading may reduce this straight and level flight 1.4 g protection to no protection at all. Consequently, a maximum cruising flight altitude must be selected which will allow sufficient buffet margins for necessary maneuvering and for gust conditions likely to be encountered. Therefore, it is important for pilots to be familiar with the use of charts showing cruise maneuver and buffet limits. See Figure 15-11. The transitioning pilot must bear in mind that the maneuverability of the jet airplane is particularly critical, especially at the high altitudes. Some jet airplanes have a very narrow span between the high and low speed buffets. One airspeed that the pilot should have firmly fixed in memory is the manufacturer's recommended gust penetration speed for the particular make and model airplane. This speed is normally the speed that would give the greatest margin between the high and low speed buffets, and may be considerably higher than design maneuvering speed, VA. This means that, unlike piston airplanes, there are times when a jet airplane should be flown in excess of VA during encounters with turbulence. Pilots operating airplanes at high speeds must be adequately trained to operate them safely. This training cannot be complete until pilots are thoroughly educated in the critical aspects of the aerodynamic factors pertinent to mock flight at high altitudes. End of Chapter 15, Part 2. Recording by Jairus Amar. Chapter 15, Part 3 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jairus Amar. Airplane Flying Handbook by the FAA. Low Speed Flight. The jet airplane wing, designed primarily for high-speed flight, has relatively poor low-speed characteristics. As opposed to the normal piston-powered airplane, the jet wing has less area, a lower aspect ratio, long chord/short span, and thin airfoil shape, all of which amount to less lift. The swept wing is additionally penalized at low speeds because the effective lift, which is perpendicular to the leading edge, is always less than the airspeed of the airplane itself. In other words, the airflow on the swept wing has the effect of persuading the wing into believing that it is flying slower than it actually is. But the wing consequently suffers a loss of lift for a given airspeed at a given angle of attack. The first real consequence of poor lift at low speeds is a high stall speed. The second consequence of poor lift at low speeds is the manner in which lift and drag vary with speed in the lower ranges. As a jet airplane is slowed toward its minimum drag speed, VMD or L/D max, total drag increases at a much greater rate than lift, resulting in a sinking flight path. If the pilot attempts to increase lift by increasing pitch attitude, airspeed will be further reduced, resulting in a further increase in drag and sink rate as the airplane slides up the backside of the power curve. The sink rate can be arrested in one of two ways. Pitch attitude can be substantially reduced to reduce the angle of attack and allow the airplane to accelerate to a speed above VMD, where steady flight conditions can be reestablished. This procedure, however, will invariably result in a substantial loss of altitude. Thrust can be increased to accelerate the airplane to a speed above VMD to reestablish steady flight conditions. It should be remembered that the amount of thrust required will be quite large. The amount of thrust must be sufficient to accelerate the airplane and regain altitude lost. Also, if the airplane has slid a long way up the backside of the power required drag curve, drag will be very high and a very large amount of thrust will be required. In a typical piston engine airplane, VMD in the clean configuration is normally at a speed of about 1.3 Vs. See Figure 15-12. Flight below VMD on a piston engine airplane is well identified and predictable. In contrast, in a jet airplane, flight in the area of VMD, typically 1.5 to 1.6 Vs, does not normally produce any noticeable changes in flying qualities, other than a lack of speed stability, a condition where a decrease in speed leads to an increase in drag, which leads to a further decrease in speed and hence a speed divergence. A pilot who is not cognizant of a developing speed divergence may find a serious sink rate developing at a constant power setting, and a pitch attitude that appears to be normal. The fact that drag increases more rapidly than lift, causing a sinking flight path, is one of the most important aspects of jet airplane flying qualities. Stalls. The stalling characteristics of the swept-wing jet airplane can vary considerably from those of the normal straight-wing airplane. The greatest difference that will be noticeable to the pilot is the lift developed versus angle of attack. An increase in angle of attack of the straight wing produces a substantial and constantly increasing lift vector, up to its maximum coefficient of lift, and soon thereafter, flow separation, stall, occurs with a rapid deterioration of lift. By contrast, the swept wing produces a much more gradual buildup of lift, with no well-defined maximum coefficient, and has the ability to fly well beyond this maximum buildup, even though lift is lost. The drag curves, which are not depicted in Figure 15-13, are approximately the reverse of the lift curves shown, in that a rapid increase in drag component may be expected with an increase in the angle of attack of a swept-wing airplane. The differences in the stall characteristics between a conventional straight-wing / low tailplane non-T-tail airplane and the swept-wing T-tail airplane center around two main areas: the basic pitching tendency of the airplane at the stall, tail effectiveness in stall recovery. On a conventional straight-wing / low tailplane airplane, the weight of the airplane acts downwards, forward of the lift acting upwards, producing a need for balancing force acting downwards from the tailplane. As speed is reduced by gentle up elevator deflection, the static stability of the airplane causes a nose-down tendency. This is countered by further up elevator to keep the nose coming up and the speed decreasing. As the pitch attitude increases, the low-set tail is immersed in the wing wake, which is slightly turbulent, low-energy air. The accompanying aerodynamic buffeting serves as a warning of impending stall. The reduced effectiveness of the tail prevents the pilot from forcing the airplane into a deeper stall. See Figure 15-14. The conventional straight-wing airplane conforms to the familiar nose-down pitching tendency at the stall and gives the entire airplane a fairly pronounced nose-down pitch. At the moment of stall, the wing wake passes more or less straight rear wind and passes above the tail. The tail is now immersed in high-energy air, where it experiences a sharp increase in positive angle of attack, causing upward lift. This lift then assists the nose-down pitch and decrease in wing angle of attack, essential to stall recovery. In a swept-wing jet with a T-tail and rear fuselage-mounted engines, the two qualities that are different from its straight-wing, low tailplane counterpart are the pitching tendency of the airplane as the stall develops, and the loss of tail effectiveness at the stall. The handling qualities down to the stall are much the same as the straight-wing airplane, except that the high T-tail remains clear of the wing wake and provides little or no warning in the form of a pre-stall buffet. Also, the tail is fully effective during the speed reduction towards the stall, and remains effective even after the wing has begun to stall. This enables the pilot to drive the wing into a deeper stall at a much greater angle of attack. At the stall, two distinct things happen. After the stall, the swept-wing T-tail airplane tends to pitch up rather than down, and the T-tail is immersed in the wing wake, which is low-energy turbulent air. This greatly reduces tail effectiveness and the airplane's ability to counter the nose-up pitch. Also, the disturbed, relatively slow air behind the wing may sweep across the tail at such a large angle that the tail itself stalls. If this occurs, the pilot loses all pitch control and will be unable to lower the nose. The pitch up just after the stall is worsened by large reduction in lift and a large increase in drag, which causes a rapidly increasing descent path, thus compounding the rate of increase of the wing's angle of attack. See Figure 15-15. The pitch-up tendency after the stall is a characteristic of a swept and/or tapered wings. With these types of wings, there's a tendency for the wing to develop a strong span-wise airflow towards the wingtip when the wing is at high angles of attack. This leads to a tendency for separation of airflow, and the subsequent stall to occur at the wingtips first. See Figure 15-16. The tip-first stall results in a shift of the center of lift of the wing in a forward direction relative to the center of gravity of the airplane, causing the nose to pitch up. Another disadvantage of a tip-first stall is that it can involve the ailerons and the road roll control. As previously stated, when flying at a speed in the area of VMD, an increase in angle of attack causes drag to increase faster than lift, and the airplane begins to sink. It is essential to understand that this increasing sinking tendency at a constant pitch attitude results in a rapid increase in angle of attack as the flight path becomes deflected downwards. See Figure 15-17. Furthermore, once the stall has developed and a large amount of lift has been lost, the airplane will begin to sink rapidly, and this will be accompanied by a corresponding rapid increase in angle of attack. This is the beginning of what is termed a deep stall. As an airplane enters a deep stall, increasing drag reduces forward speed to well below normal stall speed. The sink rate may increase to many thousands of feet per minute. The airplane eventually stabilizes in a vertical descent. The angle of attack may approach 90 degrees, and the indicated airspeed may be reduced to 0. At a 90-degree angle of attack, none of the airplane's control surfaces are effective. It must be emphasized that this situation can occur without an excessively nose-high pitch attitude. On some airplanes, it can occur at an apparently normal pitch attitude, and it is this quality that can mislead the pilot because it appears similar to the beginning of a normal stall recovery. Deep stalls are virtually unrecoverable. Fortunately, they are easily avoided as long as published limitations are observed. On those airplanes susceptible to deep stalls, not all swept and/or tapered wing airplanes are. Sophisticated stall warning systems such as stick shakers and stick pushers are standard equipment. A stick pusher, as its name implies, acts to automatically reduce the airplane's angle of attack before the airplane reaches a fully stalled condition. Unless the airplane flight manual procedures stipulate otherwise, a fully stalled condition in a jet airplane is to be avoided. Pilots undergoing training in jet airplanes are taught to recover at the first sign of an impending stall. Normally, this is indicated by aural stall warning devices and/or activation of the airplane stick shaker. Stick shakers normally activate around 107% of the actual stall speed. At such slow speeds, very high sink rates can develop if the airplane's pitch attitude is decreased below the horizon, as is normal recovery procedure in most piston-powered straight-wing, light airplanes. Therefore, at the lower altitudes where plenty of engine thrust is available, the recovery technique in many swept-wing jets involves applying full available power, rolling the wings level, and holding a slightly positive pitch attitude. The amount of pitch attitude should be sufficient enough to maintain altitude or begin a slight climb. At high altitudes, where there may be little excess thrust available to effect a recovery using power alone, it may be necessary to lower the nose below the horizon in order to accelerate away from an impending stall. This procedure may require several thousand feet or more of altitude loss to effect a recovery. Stall recovery techniques may vary considerably from airplane to airplane. The stall recovery procedures for a particular make and model airplane, as recommended by the manufacturer, are contained in the FAA-approved Airplane Flight Manual for that airplane. Drag devices. To the pilot transitioning into jet airplanes, going faster is seldom a problem. It is getting the airplane to slow down that seems to cause the most difficulty. This is because of the extremely clean aerodynamic design and fast momentum of the jet airplane, and also because the jet lacks the propeller drag effects that the pilot has been accustomed to. Additionally, even with the power reduced to flight idle, the jet engine still produces thrust, and deceleration of the jet airplane is a slow process. Jet airplanes have a glide performance that is double that of piston-powered airplanes, and jet pilots often cannot comply with an air traffic control request to go down and slow down at the same time. Therefore, jet airplanes are equipped with drag devices such as spoilers and speed brakes. The primary purpose of spoilers is to spoil lift. The most common type of spoiler consists of one or more rectangular plates that lie flush with the upper surface of each wing. They are installed approximately parallel to the lateral axis of the airplane and are hinged along the leading edges. When deployed, spoilers deflect up against the relative wind, which interferes with the flow of the air about the wing. See Figure 15-18. This both spoils lift and increases drag. Spoilers are usually installed forward of the flaps, but not in front of the ailerons, so as not to interfere with roll control. Deploying spoilers results in a substantial sink rate with little decay in airspeed. Some airplanes will exhibit a nose-up pitch tendency when the spoilers are deployed, which the pilot must anticipate. When spoilers are deployed on landing, most of the wing's lift is destroyed. This action transfers the airplane's weight to the landing gear, so that the wheel brakes are more effective. Another beneficial effect of deploying spoilers on landing is that they create considerable drag, adding to the overall aerodynamic braking. The real value of spoilers on landing, however, is creating the best circumstances for using wheel brakes. The primary purpose of speed brakes is to produce drag. Speed brakes are found in many sizes, shapes, and locations on different airplanes, but they all have the same purpose: to assist in rapid deceleration. The speed brake consists of a hydraulically operated board that, when deployed, extends into the airstream. Deploying speed brakes results in a rapid decrease in airspeed. Typically, speed brakes can be deployed at any time during flight in order to help control airspeed, but they are most often used only when a rapid deceleration must be accomplished to slow down to landing gear and flap speeds. There is usually a certain amount of noise and buffeting associated with the use of speed brakes, along with an obvious penalty in fuel consumption. Procedures for the use of spoilers and/or speed brakes in various situations are contained in the FAA-approved Airplane Flight Manual for the particular airplane. Thrust reversers. Jet airplanes have high kinetic energy during the landing roll because of weight and speed. This energy is difficult to dissipate because a jet airplane has low drag with the nose wheel on the ground, and the engines continue to produce forward thrust with the power levers at idle. While wheel brakes normally can cope, there is an obvious need for another speed retarding method. This need is satisfied by the drag provided by reverse thrust. A thrust reverser is a device fitted in the engine exhaust system which effectively reverses the flow of the exhaust gases. The flow does not reverse through 180 degrees. However, the final path of the exhaust gases is about 45 degrees from straight ahead. This, together with the losses in the reverse flow paths, results in a net efficiency of about 50%. It will produce even less if the engine RPM is less than maximum in reverse. Normally, a jet engine will have one or two types of thrust reversers, either a target reverser or a cascade reverser. See Figure 15-19. Target reversers are simple clamshell doors that swivel from the stowed position at the engine tailpipe to block all of the outflow and redirect some component of the thrust forward. Cascade reversers are more complex. They are normally found on turbofan engines, and are often designed to reverse only the fan air portion. Blocking doors in the shroud obstructs forward fan thrust and redirects it through cascade vanes for some reverse component. Cascades are generally less effective than target reversers, particularly those that reverse only fan air, because they do not affect the engine core, which will continue to produce forward thrust. On most installations, reverse thrust is obtained with the thrust lever at idle, by pulling up the reverse level to a detent. Doing so positions the reversing mechanisms for operation, but leaves the engine at idle RPM. Further upward and backward movement of the reverse lever increases engine power. Reverse is cancelled by closing the reverse lever to the idle reverse position, then dropping it fully back to the forward idle position. This last movement operates the reverser back to the forward thrust position. Reverse thrust is much more effective at high airplane speed than at low airplane speeds, for two reasons. First, the net amount of reverse thrust increases with speed. Second, the power produced is higher at higher speeds, because of the increased rate of doing work. In other words, the kinetic energy of the airplane is being destroyed at a higher rate at the higher speeds. To get maximum efficiency from reverse thrust, therefore, it should be used as soon as is prudent after touchdown. When considering the proper time to apply reverse thrust after touchdown, the pilot should remember that some airplanes tend to pitch nose up when reverse is selected on landing, and this effect, particularly when combined with the nose-up pitch effect from the spoilers, can cause the airplane to leave the ground again momentarily. On these types, the airplane must be firmly on the ground with the nose wheel down before reverse is selected. Other types of airplanes have no change in pitch, and reverse idle may be selected after the main gear is down and before the nose wheel is down. Specific procedures for reverse thrust operation for a particular airplane/engine combination are contained in the FAA-approved Airplane Flight Manual for that airplane. There is a significant difference between reverse pitch on a propeller and reverse thrust on a jet. Idle reverse on a propeller produces about 60% of the reverse thrust available at full power reverse, and is therefore very effective at this setting when full reverse is not needed. On a jet engine, however, selecting idle reverse produces very little actual reverse thrust. In a jet airplane, the pilot must not only select reverse as soon as reasonable, but then must go up to full power reverse as soon as possible. Within airplane flight manual limitations, full power reverse should be held until the pilot is certain the landing roll will be contained within the distance available. Inadvertent deployment of thrust reversers is a very serious emergency situation. Therefore, thrust reverser systems are designed with this prospect in mind. The systems normally contain several lock systems, one to keep reversers from operating in the air, another to prevent operation with the thrust levers out of idle detent, and/or an auto stow circuit to command reverser stowage at any time unwanted motion is detected. It is essential that pilots understand not only the normal procedures and limitations of thrust reverser use, but also the procedures for coping with uncommanded reverse. Those emergencies demand immediate and accurate response. End of Chapter 15, Part 3. Recording by Jairus Amar.
Chapter 15, Part 4 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook by the FAA. Pilot sensations in jet flying. There are usually three general sensations that the pilot transitioning into jets will immediately become aware of. These are inertial response differences, increased control sensitivity, and a much increased tempo of flight. The varying of power settings from flight idle to full takeoff power has a much slower effect on the change of airspeed in a jet airplane. This is commonly called lead and lag, and is as much a result of the extremely clean aerodynamic design of the airplane as it is the slower response of the engine. The lack of propeller effect is also responsible for the lower drag increment at the reduced power settings and results in other changes that the pilot will have to become accustomed to. These include the lack of effective slipstream over the lifting surfaces and control surfaces and lack of propeller torque effect. The aft-mounted engines will cause a different reaction to the power application and may result in a slightly nose-down pitching tendency with the application of power. On the other hand, power reduction will not cause the nose of the airplane to drop to the same extent the pilot is used to in a propeller airplane. Although neither of these characteristics are radical enough to cause transitioning pilots much of a problem, they must be compensated for. Power settings required to attain a given performance are almost impossible to memorize in the jets, and the pilot who feels the necessity for having an array of power settings for all occasions will initially feel at a loss. The only way to answer the question of how much power is needed is by saying, whatever is required to get the job done. The primary reason that power settings vary so much is because of the great changes in weight as fuel is consumed during flight. Therefore, the pilot will have to learn to use power as needed to achieve the desired performance. In time, the pilot will find that the only reference to power instruments will be that required to keep from exceeding the limits of maximum power settings or to synchronize RPM. Proper power management is one of the initial problem areas encountered by the pilot transitioning into jet airplanes. Although smooth power applications are still the rule, the pilot will be aware that a greater physical movement of the power levers is required as compared to the throttle movement in the piston engines. The pilot will also have to learn to anticipate and lead the power changes more than in the past and must keep in mind that the last 30% of engine RPM represents the majority of the engine thrust, and below that, the application of power has very little effect. In slowing the airplane, power reduction must be made sooner because there is no longer any propeller drag and the pilot should anticipate the need for drag devices. Control sensitivity will differ between various airplanes, but in all cases, the pilot will find that they are more sensitive to any change in control displacement, particularly pitch control, than are the conventional propeller airplanes. Because of the higher speeds flown, the control surfaces are more effective, and the variation of just a few degrees in pitch attitude in a jet can result in over twice the rate of altitude change that would be experienced in a slower airplane. The sensitive pitch control in jet airplanes is one of the first flight differences that the pilot will notice. Invariably, the pilot will have a tendency to over-control pitch during initial training flights. The importance of accurate and smooth control cannot be overemphasized, however, and it is one of the first techniques the transitioning pilot must master. The pilot of a swept-wing jet airplane will soon become adjusted to the fact that it is necessary and normal to fly at higher angles of attack. It is not unusual to have about 5 degrees of nose-up pitch on an approach to a landing. During an approach to a stall at a constant altitude, the nose-up angle may be as high as 15 degrees to 20 degrees. The higher deck angles, pitch angle relative to the ground, on takeoff, which may be as high as 15 degrees, will also take some getting used to, although this is not the actual angle of attack relative to the airflow over the wing. The greater variation of pitch attitudes flown in a jet airplane are a result of greater thrust available and the flight characteristics of the low aspect ratio and swept wing. Flight at the higher pitch attitudes requires a greater reliance on the flight instruments for airplane control since there is not much in the way of a useful horizon or other outside reference to be seen. Because of the high rates of climb and descent, high airspeeds, high altitudes, and a variety of attitudes flown, the jet airplane can only be precisely flown by applying proficient instrument flight techniques. Proficiency in attitude instrument flying, therefore, is essential to successful transition to jet airplane flying. Most jet airplanes are equipped with a thumb-operated pitch trim button on the control wheel, which the pilot must become familiar with as soon as possible. The jet airplane will differ regarding pitch tendencies with the lowering of flaps, landing gear, and drag devices. With experience, the jet airplane pilot will learn to anticipate the amount of pitch change required for a particular operation. The usual method of operating the trim button is to apply several small, intermittent applications of trim in the direction desired rather than holding the trim button for longer periods of time, which can lead to over-controlling. Jet airplane takeoff and climb. All FAA-certificated jet airplanes are certificated under Title 14 of the Code of Federal Regulations, 14 CFR, Part 25, which contains the airworthiness standards for transport category airplanes. The FAA-certificated jet airplane is a highly sophisticated machine with proven levels of performance and guaranteed safety margins. The jet airplane's performance and safety margins can only be realized, however, if the airplane is operated in strict compliance with the procedures and limitations contained in the FAA-approved Airplane Flight Manual for that particular airplane. The following information is generic in nature, and since most civilian jet airplanes require a minimum flight crew of 2 pilots, assumes a 2-pilot crew. If any of the following information conflicts with FAA-approved Airplane Flight Manual procedures for a particular airplane, the Airplane Flight Manual procedures take precedence. Also, if any of the following procedures differ from the FAA-approved procedures developed for use by a specific air operator and/or for use in an FAA-approved training center or pilot school curriculum, the FAA-approved procedures for that operator and/or training center, pilot school, take precedence. V speeds. The following are speeds that will affect the jet airplane's takeoff performance. The jet airplane pilot must be thoroughly familiar with each of these speeds and how they are used in planning the takeoff. VS. Stall speed. V1. Critical engine failure speed or decision speed. Engine failure below this speed should result in an aborted takeoff. Above this speed, the takeoff run should be continued. VR. Speed at which the rotation of the airplane is initiated to takeoff attitude. This speed cannot be less than V1 or less than 1.05 times VMCA, minimum control speed in the air. On a single engine takeoff, it must also allow for the acceleration to V2 at the 35-foot height at the end of the runway. VLO, the speed at which the airplane first becomes airborne. This is an engineering term used when the airplane is certificated and must meet certain requirements. If it is not listed in the Airplane Flight Manual, it is within requirements and does not have to be taken into consideration by the pilot. V2, The takeoff safety speed, which must be attained at the 35-foot height at the end of the required runway distance. This is essentially the best single-engine angle of climb speed for the airplane and should be held until clearing obstacles after takeoff, or at least 400 feet above the ground. Pre-takeoff procedures. Takeoff data, including V1 over VR and V2 speeds, takeoff power settings, and required field length should be computed prior to each takeoff and recorded on a takeoff data card. These data will be based on airplane weight, runway length available, runway gradient, field temperature, field barometric pressure, wind, icing conditions, and runway condition. Both pilots should separately compute the takeoff data and cross-check it in the cockpit with the takeoff data card. A captain's briefing is an essential part of cockpit resource management, CRM, procedures and should be accomplished just prior to takeoff. See Figure 15-20. The captain's briefing is an opportunity to review crew coordination procedures for takeoff, which is always the most critical portion of a flight. Figure 15-20 text. Captain's briefing. I will advance the thrust levers. Follow me through on the thrust levers. Monitor all instruments and warning lights on the takeoff roll and call out any discrepancies or malfunctions observed prior to V1, and I will abort the takeoff. Stand by to arm thrust reversers on my command. Give me a visual and oral signal for the following. 80 knots, and I will disengage nose wheel steering. V1, and I will move my hand from thrust to yoke. VR, and I will rotate. In the event of engine failure at or after V1, I will continue the takeoff roll to VR, rotate, and establish V2 climb speed. I will identify the inoperative engine, and we will both verify, and I will accomplish the shutdown, or have you do it on my command. I will expect you to stand by on the appropriate emergency checklist. I will give you a visual and oral signal for gear retraction and for power settings after the takeoff. Our VFR emergency procedure is to. Our IFR emergency procedure is to. End of Figure 15-20 text. The takeoff and climb out should be accomplished in accordance with the standard takeoff and departure profile developed for the particular make and model of airplane. See Figure 15-21. Takeoff roll. The entire runway length should be available for takeoff, especially if the pre-calculated takeoff performance shows the airplane to be limited by runway length or obstacles. After taxiing into position at the end of the runway, the airplane should be aligned in the center of the runway, allowing equal distance on either side. The brakes should be held while the thrust levers are brought to power setting beyond the bleed valve range, normally the vertical position, and the engines allowed to stabilize. The engine instrument should be checked for proper operation before the brakes are released or the power increased further. This procedure assures symmetrical thrust during the takeoff roll and aids in preventing overshooting the desired takeoff thrust setting. The brakes should then be released, and during the start of the takeoff roll, the thrust lever smoothly advanced to the pre-computed takeoff power setting. All final takeoff thrust adjustments should be made prior to reaching 60 knots. The final engine power adjustments are normally made by the pilot not flying. Once the thrust levers are set for takeoff power, they should not be readjusted after 60 knots. Retarding a thrust lever would only be necessary in case an engine exceeds a limitation such as ITT, fan, or turbine RPM. If sufficient runway length is available, a rolling takeoff may be made without stopping at the end of the runway. Using this procedure, as the airplane rolls onto the runway, the thrust lever should be smoothly advanced to the vertical position and the engines allowed to stabilize, and then proceed as in the static takeoff outlined above. Rolling takeoffs can also be made from the end of the runway by advancing the thrust levers from idle as the brakes are released. During the takeoff roll, the pilot flying should concentrate on directional control of the airplane. This is made somewhat easier because there's no torque produced yawing in a jet as there is in a propeller-driven airplane. The airplane must be maintained exactly on centerline with the wings level. This will automatically aid the pilot when contending with an engine failure. If a crosswind exists, the wings should be kept level by displacing the control wheel into the crosswind. During the takeoff roll, the primary responsibility of the pilot not flying is to closely monitor the aircraft systems and to call out the proper V speeds as directed in the captain's briefing. Slight forward pressure should be held on the control column to keep the nose wheel rolling firmly on the runway. If nose wheel steering is being utilized, the pilot flying should monitor the nose wheel steering to about 80 knots, or VMCG for the particular airplane, while the pilot not flying applies the forward pressure. After reaching VMCG, the pilot flying should bring his or her left hand up to the control wheel. The pilot's other hand should be on the thrust levers until at least V1 speed is attained. Although the pilot not flying maintains a check on the engine instruments throughout the takeoff roll, the pilot flying, pilot in command, makes the decision to continue or reject a takeoff for any reason. A decision to reject a takeoff will require immediate retarding of the thrust levers. The pilot not flying should call out V1. After passing V1 speed on the takeoff roll, it is no longer mandatory for the pilot flying to keep a hand on the thrust levers. The point for abort has passed, and both hands may be placed on the control wheel. As the airspeed approaches VR, the control column should be moved to a neutral position. As the pre-computed VR speed is attained, the pilot not flying should make the appropriate call-out, and the pilot flying should smoothly rotate the airplane to the appropriate takeoff pitch attitude. Rotation and liftoff. Rotation and liftoff in a jet airplane should be considered a maneuver unto itself. It requires planning, precision, and a fine control touch. The objective is to initiate the rotation to takeoff pitch attitude exactly at VR, so that the airplane will accelerate through VLOF and attain V2 speed at 35 feet at the end of the runway. Rotation to the proper takeoff attitude too soon may extend the takeoff roll or cause an early liftoff, which will result in a lower rate of climb, and the predicted flight path will not be followed. A late rotation, on the other hand, will result in a longer takeoff roll, exceeding V2 speed, and a takeoff and climb path below the predicted path. Each airplane has its own specific takeoff pitch attitude, which remains constant regardless of weight. The takeoff pitch attitude in a jet airplane is normally between 10 degrees and 15 degrees nose up. The rotation to takeoff pitch attitude should be made smoothly but deliberately and at a constant rate. Depending on the particular airplane, the pilot should plan on a rate of pitch attitude increase of approximately 2.5 degrees to 3 degrees per second. In training, it is common for a pilot to overshoot VR and then overshoot V2 because the pilot not flying will call for rotation at or just past VR. The reaction of the pilot flying is to visually verify VR and then rotate. The airplane then leaves the ground at or above V2. The excess airspeed may be of little concern on the normal takeoff, but a delayed rotation can be critical when runway length or obstacle clearance is limited. It should be remembered that on some airplanes the all-engine takeoff can be more limiting than an engine-out takeoff in terms of obstacle clearance in the initial part of the climb-out. This is because of the rapidly increasing airspeed causing the achieved flight path to fall below the engine-out scheduled flight path unless care is taken to fly the correct speeds. The transitioning pilot should remember that rotation at the right speed and rate to the right attitude will get the airplane off the ground at the right speed and within the right distance. Initial climb. Once the proper pitch attitude is attained, it must be maintained. The initial climb after liftoff is done at this constant pitch attitude. Takeoff power is maintained and the airspeed allowed to accelerate. Landing gear retraction should be accomplished after a positive rate of climb has been established and confirmed. Remember that in some airplanes, gear retraction may temporarily increase the airplane drag while the landing gear doors open. Premature gear retraction may cause the airplane to settle back towards the runway surface. Remember also that because of ground effect, the vertical speed indicator and altimeter may not show a positive climb until the airplane is 35 to 50 feet above the runway. The climb pitch attitude should continue to be held and the airplane allowed to accelerate to flap retraction speed. However, the flaps should not be retracted until obstruction clearance altitude or 400 feet AGL has been passed. Ground effect and landing gear drag reduction results in a rapid acceleration during this phase of the takeoff and climb. Airspeed, altitude, climb rate, attitude, and heading must be monitored carefully. When the airplane settles down to a steady climb, longitudinal stick forces can be trimmed out. If a turn must be made during this phase of flight, no more than 15 degrees to 20 degrees of bank should be used. Because of the spiral instability and because at this point an accurate trim state on rudder and aileron has not yet been achieved, the bank angle should be carefully monitored throughout the turn. If a power reduction must be made, pitch attitude should be reduced simultaneously and the airplane monitored carefully so as to preclude entry into an inadvertent descent. When the airplane has attained a steady climb at the appropriate en route climb speed, it can be trimmed about all axes and the autopilot engaged. End Chapter 15, Part 4. Recording by Dale Latham. Chapter 15, Part 5 of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook by the FAA. Chapter 15, Part 5. Jet airplane approach and landing. Landing requirements. The FAA landing field length requirements for jet airplanes are specified in 14 CFR Part 25. It defines the minimum field length and therefore minimum margins that can be scheduled. The regulation describes the landing profile as the distance required from a point 50 feet above the runway threshold through the flare to touchdown and then stopping using the maximum stopping capability on a dry runway surface. The actual demonstrated distance is increased by 67% and published in the FAA-approved Airplane Flight Manual as the FAR Dry Runway Landing Distance. See Figure 15-22. For wet runways, the FAR Dry Runway Distance is increased by an additional 15%. Thus, the minimum dry runway field length will be 1.67 times the actual minimum air and ground distance needed, and the wet runway minimum landing field length will be 1.92 times the minimum dry air and ground distance needed. Certified landing field length requirements are computed for the stop made with speed brakes deployed and maximum wheel braking. Reverse thrust is not used in establishing the certified FAR landing distances. However, reversers should definitely be used in service. Landing speeds. As in the takeoff planning, there are certain speeds that must be taken into consideration during any landings in a jet airplane. The speeds are as follows. VSO, stall speed in the landing configuration. VREF, 1.3 times the stall speed in the landing configuration. Approach climb, the speed which guarantees adequate performance in a go-around situation with an inoperative engine. The airplane's weight must be limited so that a twin-engine airplane will have a 2.1% climb gradient capability. The approach climb gradient requirements for 3 and 4 engine airplanes are 2.4% and 2.7%, respectively. These criteria are based on an airplane configured with approach flaps, landing gear up, and takeoff thrust available from the operative engines. Landing climb. The speed which guarantees adequate performance in arresting the descent and making a go-around from the final stages of landing with the airplane in a full landing configuration and maximum takeoff power available on all engines. The appropriate speeds should be pre-computed prior to every landing and posted where they are visible to both pilots. The VREF speed, or threshold speed, is used as a reference speed throughout the traffic pattern. For example, downwind leg, VREF, plus 20 knots. Base leg, VREF, plus 10 knots. Final approach, VREF, plus 5 knots. 50 feet over threshold, VREF. The approach and landing sequence in a jet airplane should be accomplished in accordance with an approach and landing profile developed for the particular airplane. See Figure 15-23. Significant differences. A safe approach in any type of airplane culminates in a particular position, speed, and height over the runway threshold. That final flight condition is the target window at which the entire approach aims. Propeller-powered airplanes are able to approach that target from wider angles, greater speed differentials, and a larger variety of glide path angles. Jet airplanes are not as responsive to power and course corrections, so the final approach must be more stable, more deliberate, more constant, in order to reach the window accurately. The transitioning pilot must understand that, in spite of their impressive performance capabilities, there are 6 ways in which a jet airplane is worse than a piston engine airplane in making an approach and in correcting errors on the approach. The absence of propeller slipstream in producing immediate extra lift at constant airspeed. There is no such thing as salvaging a misjudged glide path with a sudden burst of immediate available power. Added lift can only be achieved by accelerating the airframe. Not only must the pilot wait for added power, but even when the engines do respond, added lift will only be available when the airframe has responded with speed. The absence of the propeller slipstream in significantly lowering the power on stall speed. There's virtually no difference between power on and power off stall speed. It is not possible in a jet airplane to jam the thrust levers forward to avoid a stall. Poor acceleration response in a jet engine from low RPM. This characteristic requires that the approach be flown in a high-drag, high-power configuration so that sufficient power will be available quickly if needed. The increased momentum of the jet airplane making sudden changes in the flight path impossible. Jet airplanes are consistently heavier than comparable-sized propeller airplanes. The jet airplane, therefore, will require more indicated airspeed during the final approach due to a wing design that is optimized for higher speeds. These 2 factors combine to produce higher momentum for the jet airplane. Since force is required to overcome momentum for speed changes or course corrections, the jet will be far less responsive than the propeller airplane and require careful planning and stable conditions throughout the approach. The lack of speed stability being an inducement to a low-speed condition. The drag curve for many jet airplanes is much flatter than for propeller airplanes, so speed changes do not produce nearly as much drag change. Further, jet thrust remains nearly constant with small speed changes. The result is far less speed stability. When the speed does increase or decrease, there is little tendency for the jet airplane to reacquire the original speed. The pilot, therefore, must remain alert to the necessity of making speed adjustments and then make them aggressively in order to remain on speed. drag increasing faster than lift, producing a high sink rate at low speeds. Jet airplane wings typically have a large increase in drag in the approach configuration. When a sink rate does develop, the only immediate remedy is to increase pitch attitude, angle of attack. Because drag increases faster than lift, that pitch change will rapidly contribute to an even greater sink rate, unless a significant amount of power is aggressively applied. These flying characteristics of jet airplanes make a stabilized approach an absolute necessity. The stabilized approach. The performance charts and the limitations contained in the FAA-approved airplane flight manual are predicated on momentum values that result from programmed speeds and weights. Runway length limitations assume an exact 50-foot threshold height at an exact speed of 1.3 times VSO. That window is critical and is a prime reason for the stabilized approach. Performance figures also assume that once through the target threshold window, the airplane will touch down in a target touchdown zone approximately 1,000 feet down the runway, after which maximum stopping capability will be used. There are 5 basic elements to a stabilized approach. The airplane should be in the landing configuration early in the approach. The landing gear should be down, landing flaps selected, trim set, and fuel balanced. Ensuring that these tasks are completed will help keep the number of variables to a minimum during the final approach. The airplane should be on profile before descending below 1,000 feet. Configuration, trim, speed, and glide path should be at or near the optimum parameters early in the approach to avoid distractions and conflicts as the airplane nears the threshold window. An optimum glide path angle of 2.5 degrees to 3 degrees should be established and maintained. Indicated airspeed should be within 10 knots of the target airspeed. There are strong relationships between trim, speed, and power in most jet airplanes, and it is important to stabilize the speed in order to minimize those other variables. The optimum descent rate should be 500 to 700 feet per minute. The descent rate should not be allowed to exceed 1,000 feet per minute at any time during the approach. The engine speed should be at an RPM that allows best response when and if a rapid power increase is needed. Every approach should be evaluated at 500 feet. In a typical jet airplane, this is approximately 1 minute from touchdown. If the approach is not stabilized at that height, a go-around should be initiated. See Figure 15-24 on the next page. Approach speed. On final approach, the airspeed is controlled with power. Any speed diversion from VREF on final approach must be detected immediately and corrected. With experience, the pilot will be able to detect the very first tendency of an increasing or decreasing airspeed trend, which normally can be corrected with a small adjustment in thrust. The pilot must be attentive to poor speed stability leading to a low speed condition with its attendant risk of high drag increasing the sink rate. Remember that with an increasing sink rate, an apparently normal pitch attitude is no guarantee of normal angle of attack value. If an increasing sink rate is detected, it must be countered by increasing the angle of attack and simultaneously increasing thrust to counter the extra drag. The degree of correction required will depend on how much the sink rate needs to be reduced. For small amounts, smooth and gentle, almost anticipatory corrections will be sufficient. For large sink rates, drastic corrective measures may be required that, even if successful, would destabilize the approach. A common error in the performance of approaches in jet airplanes is excess approach speed. Excess approach speed carried through the threshold window and onto the runway will increase the minimum stopping distance required by 20 to 30 feet per knot of excess speed for a dry runway and 40 to 50 feet for a wet runway. Worse yet, the excess speed will increase the chances of an extended flare, which will increase the distance to touchdown by approximately 250 feet for each excess knot in speed. Proper speed control on final approach is of primary importance. The pilot must anticipate the need for speed adjustments so that only small adjustments are required. It is essential that the airplane arrive at the approach threshold window exactly on speed. Glide path control. On final approach, at a constant airspeed, the glide path angle and rate of descent is controlled with pitch attitude and elevator. The optimum glide path angle is 2.5 degrees to 3 degrees whether or not an electronic glide path reference is being used. On visual approaches, pilots may have a tendency to make flat approaches. A flat approach, however, will increase landing distance and should be avoided. For example, an approach angle of 2 degrees instead of a recommended 3 degree will add 500 feet to landing distance. The more common error is excessive height over the threshold. This could be the result of an unstable approach or stable but high approach. It may also occur during an instrument approach where the missed approach point is close to or at the runway threshold. Regardless of cause, excessive height over the threshold will most likely result in a touchdown beyond the normal aiming point. An extra 50 feet of height over the threshold will add approximately 1,000 feet to the landing distance. It is essential that the airplane arrive at the approach threshold window exactly on altitude, 50 feet above the runway. The flare. The flare reduces the approach rate of descent to a more acceptable rate for touchdown. Unlike light airplanes, a jet airplane must be flown onto the runway rather than held off the surface as speed dissipates. A jet airplane is aerodynamically clean even in the landing configuration, and its engines still produce residual thrust at idle RPM. Holding it off during the flare in an attempt to make a smooth landing will greatly increase landing distance. A firm landing is normal and desirable. A firm landing does not mean a hard landing, but rather a deliberate or positive landing. For most airports, the airplane will pass over the end of the runway with landing gear 30 to 45 feet above the surface, depending on the landing flap setting and the location of the touchdown zone. It will take 5 to 7 seconds from the time the airplane passes the end of the runway until touchdown. The flare is initiated by increasing the pitch attitude just enough to reduce the sink rate to 100 to 200 feet per minute when landing gear is approximately 15 feet above the runway surface. In most jet airplanes, this will require a pitch attitude increase of only 1 degree to 3 degrees. The thrust is smoothly reduced to idle as the flare progresses. The normal speed bleed-off during the time between passing the end of the runway and touchdown is 5 knots. Most of the decrease occurs during the flare when thrust is reduced. If the flare is extended, held off, while additional speed is bled off, hundreds or even thousands of feet of runway may be used up. See Figure 15-25. The extended flare will also result in additional pitch attitude, which may lead to a tail strike. It is therefore essential to fly the airplane onto the runway at the target touchdown point, even if speed is excessive. A deliberate touchdown should be planned and practiced on every flight. A positive touchdown will help prevent an extended flare. Pilots must learn the flare characteristics of each model of airplane they fly. The visual reference cues observed from each cockpit are different because the window geometry and visibility are different. The geometric relationship between the pilot's eye and the landing gear will be different for each make and model. It is essential that the flare maneuver be initiated at the proper height, not too high and not too low. Beginning the flare too high or reducing the thrust too early may result in the airplane floating beyond the target touchdown point, or may include a rapid pitch-up as the pilot attempts to prevent a high sink rate touchdown. This can lead to a tail strike. The flare that is initiated too late may result in a hard touchdown. Proper thrust management through the flare is also important. In many jet airplanes, the engines produce a noticeable effect on the pitch trim when the thrust setting is changed. A rapid change in the thrust settings requires a quick elevator response. If the thrust levers are moved to idle too quickly during the flare, the pilot must make rapid changes in pitch control. If the thrust levers are moved more slowly, the elevator input can be more easily coordinated. Touchdown and rollout. A proper approach and flare positions the airplane to touch down in the touchdown target zone, which is usually about 1,000 feet beyond the runway threshold. Once the main wheels have contacted the runway, the pilot must maintain directional control and initiate the stopping process. The stop must be made on the runway that remains in front of the airplane. The runway distance available to stop is longest if the touchdown was on target. The energy to be dissipated is least if there is no excess speed. The stop that begins with a touchdown that is on the numbers will be the easiest stop to make for any set of conditions. At the point of touchdown, the airplane represents a very large mass that is moving at a relatively high speed. The large total energy must be dissipated by the brakes, the aerodynamic drag, and the thrust reversers. The nose wheel should be flown onto the ground immediately after touchdown because the jet airplane decelerates poorly when held in a nose-high attitude. Placing the nose wheel tires on the ground will assist in maintaining directional control. Also, lowering the nose gear decreases the wing angle of attack, decreasing the lift, placing more load on the tires, thereby increasing tire-to-ground friction. Landing distance charts for jet airplanes assume that the nose wheel is lowered onto the runway within 4 seconds of touchdown. There are only 3 forces available for stopping the airplane. They are wheel braking, reverse thrust, and aerodynamic braking. Of the 3, the brakes are the most effective and therefore the most important stopping force for most landings. When the runway is very slippery, reverse thrust and drag may be the dominant forces. Both reverse thrust and aerodynamic drag are most effective at high speeds. Neither is affected by runway surface condition. Brakes, on the other hand, are most effective at low speed. The landing rollout distance will depend on the touchdown speed and what forces are applied and when they are applied. The pilot controls the watt and when factors, but the maximum braking force may be limited by tire-to-ground friction. The pilot should begin braking as soon after touchdown and wheel spin up as possible, and to smoothly continue the braking until stopped or a safe taxi speed is reached. However, caution should be used if the airplane is not equipped with a functioning anti-skid system. In such a case, heavy braking can cause the wheels to lock and the tires to skid. Both directional control and braking utilize tire-ground friction. They share the maximum friction force the tires can provide. Increasing either will subtract from the other. Understanding tire-ground friction, how runway contamination affects it, and how to use the friction available to maximum advantage is important to a jet pilot. Spoilers should be deployed immediately after touchdown because they are most effective at high speed. Timely deployment of spoilers will increase drag by 50 to 60%, but more importantly, they will spoil much of the lift the wing is creating, thereby causing more of the weight of the airplane to be loaded onto the wheels. The spoilers increase wheel loading by as much as 200% in the landing flap configuration. This increases the tire-ground friction force, making the maximum tire braking and cornering forces available. Like spoilers, thrust reversers are most effective at high speeds and should be deployed quickly after touchdown. However, the pilot should not command significant reverse thrust until the nose wheel is on the ground. Otherwise, the reversers might be deployed asymmetrically, resulting in an uncontrollable yaw towards the side on which the most reverse thrust is being developed, in which case the pilot will need whatever nose wheel steering is available to maintain directional control. End Chapter 15, Part 5. Recording by Dale Latham. End of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A. AVIATION-8083-3A by Federal Aviation Administration.